Hello there, my name is Michael J. Shannon, and I want to welcome you to the TCP/IP Fundamentals Live Lessons video series from Pearson. First off, let me tell you about myself just a little bit. I have over 25 years of IT and information systems security experience, and I've worked as an employee, a contractor, and a consultant for companies like MCI, Platinum Technologies, Fujitsu, IBM, State Farm, MindSharp, Skillsoft, and of course, Pearson. This is a very exciting and special course in several ways. First, it'll help you understand exactly what's happening under the hood when you use that corporate PC or laptop or that mobile device or even your web-enabled alarm or HVAC system to access the internet, more specifically, the global World Wide Web. Second, this course is a great first step in the process for entry-level IT certifications like CompTIA Network Plus, A+, the Cisco CCNA, maybe Juniper, Palo Alto Networks, even cloud services like Google Cloud Platform and Amazon Web Services. And last but not least, once you complete this course, you'll be better empowered to decide if you want to pursue or transition into a career in information technology. I'm very excited to get started on this journey, but first, let's see what we're going to cover in the first module. Welcome to Module 1, TCP/IP Overview and History. We're going to look at networking fundamentals right off the bat. Then we'll dig into the OSI reference model from the organization ISO. And then we'll finish up in the third lesson looking at the TCP/IP protocol suite and architecture. Welcome to Lesson 1, Networking Fundamentals. In this lesson, we'll first get a little bit of history, then we'll introduce network types and attributes. We'll review network performance concepts, we'll examine networking standards and organizations, and then we'll wrap up understanding applied binary and hexadecimal mathematics. Well, this first lesson's called A Little Bite of History, you know, B-Y-T-E, get it, bite. But I will tell you this, we're not going to spend a lot of time in this particular course looking backwards, okay? We're not going to look at a lot of legacy technology. We're not going to look at things that are outdated or obsolete. It's all about really TCP/IP now and into the future. However, I do want to kind of pay homage to some of the people that are responsible for giving us what we have today on the internet and the World Wide Web. We need to kind of, do a tip of the hat to them. Before we do that though, let's just make sure we understand what we're talking about here. We're talking about packet switching technology, and the packet switching technology is represented by what we call protocol suites. Now, I'm a big fan of music and I'm a big fan of suites, and they've been around a long time. Vivaldi did suites, Gershwin did suites. We see them in classical music and jazz music. We also see suites in classic rock. Remember Band on the Run by Paul McCartney and Wings, or Bohemian Rhapsody by Queen? Those were suites. They were songs that have various layers, 3 or 4 layers, and then there was transitions from one layer into the other. And that's very similar to what we're looking at here with the TCP/IP protocol suite and the associated reference models. TCP/IP, which is Transmission Control Protocol / Internet Protocol, finds its origins in the ARPANET reference model. And we'll kind of look at that ARPANET history as we look at some of the people that were involved in the early days of the internet, or what we know to be the internet. The architecture evolved from studies in methods for connecting multiple packet-switched networks. And it does kind of go back to the military-industrial complex, the Department of Defense, and really trying to put together a network that could survive in case there was some catastrophic event, right? So let me just talk about protocols for a second as we look at this air bill from FedEx. What we're talking about is we're talking about taking data and we place it into an envelope. So imagine you've got a FedEx envelope, and inside of that envelope is, 4 or 5 pages of data, right? So you put that data in the envelope, and what you're going to attach to the outside is basically metadata. Metadata is basically, if you look at the Greek word, it's data that goes alongside with data. It's data that is about data. So if you look at this, you can see obviously on this air bill, we have, dates, we have who's it from, who's the sender, who's the receiver, and that's the type of information we would need, for example, if we were sending something over the internet. Over on the right-hand side, there's little check boxes, and those we could call flags, okay, or those could be various attributes or variables. And we have the same thing with the protocol headers that we use. We have certain standard information that we have to fill in, right? Where's it from, where's it going to, and then some other variables that are little things we check off. In a protocol header, often it's basically just flipping a 0 to a 1, okay, or turning it on with a binary 1. And so this type of information is placed on the FedEx envelope and then sent out, right? Now, some of the protocols, they'll have a header, but they'll also have a trailer, and we'll look at that as well, which is something that goes on the back end, right? And that happens to our frames, and we'll see that more often. But this is a great way to kind of understand protocols, okay? It's certain information about data that we need to transport or send that over a network or over internetworks, right? Well, let's look at some of the pioneers of packet switching. The first guy we're going to talk about is named Leonard Kleinrock, and he was an American computer scientist. He was a professor at UCLA, and actually UCLA was one of those first participants in the original kind of ARPANET project. It was really a few universities. UCLA was one of them. The U.S. Air Force established a wide area network in the SAGE radar defense system so that it could survive a nuclear attack. And that's, if you look back kind of to the beginning of TCP/IP, that was one of the main reasons, to have a network where we could kind of switch packets as necessary if one of the nodes was detrimentally, catastrophically brought down by some type of attack. Kleinrock conducted early research in queuing theory, and he published a book in the related field of digital message switching. Now, that was message switching, but not using packets, okay? We're doing packet switching here. But he was still early on in the process in 1961 of sending messages digitally or sending zeros and ones over a network. Another person, Paul Baran, is considered one of the 2 original inventors of packet switching. Baran developed a concept of distributed adaptive message block switching to present a fault-tolerant, efficient routing method. And those words there, fault-tolerant, okay, able to survive a failure, and efficient routing of the packets is at the core of what we're dealing with here in this course. He was part of a research program at the RAND Corporation. It was funded by the U.S. Department of Defense. So we have Kleinrock, we have Baran, we also have Donald Davis. Donald Davis was a Welsh computer scientist who was employed at the UK National Physical Laboratory, or the UK NPL. In 1965, he developed the concept of packet switching. His work was independent from Baran in the US, who had a similar idea in the early 1960s. And this kind of concept of people working on something kind of at the same time, yet not really knowing the other person's work, is not that unusual. Especially when we get into things like cryptography, there were people that were working on some of these things at the same time and not really knowing that others were, doing the same type of thing. We have Louis Pouzin, who invented the datagram and designed an early packet communication network called Cyclades. So we've got the US, we have a guy from the UK, and we got a French individual, Louis Pouzin. His work influenced Robert Kahn and a guy named Vinton Cerf, who actually, Vinton Cerf has just come into the news lately. This is October of 2018 when I'm doing this training, and there was just a story that came out from Vinton Cerf, and we'll talk about him in a second. And there were other people that developed the TCP/IP protocols that are used in the internet. Here's the guy I was talking about, Vint Cerf, often referred to as the father of the internet. Okay, he began his work at the US DoD on the DARPA project, and he served from 2000 to 2007 as the chairman of the board for ICANN. And we'll talk about ICANN a little bit later on in an upcoming lesson when we look at some of the different organizations that we're dealing with. He also served as the founding president of the Internet Society from 1992 to 1995, and then he went on to work with Google, who you might have heard of, okay? Now, lately, he's working on a project called INRUPT, I-N-R-U-P-T, which is pretty cool. He has the goal of kind of decentralizing the web and really trying to kind of reverse the control that some of these big companies like Google and Facebook and Amazon actually have on the internet now. So he's trying to kind of decentralize the World Wide Web, and he's working closely with a lot of people to make that happen. So it's almost an alternative World Wide Web that he's working on that's going to be more open source and more decentralized and kind of taking it out of the hands of just a few big companies, which is really kind of cool because that's actually the philosophy that was early on in the World Wide Web. It wasn't until probably within the last 10 years that the control of the internet started to consolidate. And he now heads this group, this organization called INRUPT, I-N-R-U-P-T. Now, what's at the heart, and we're going to look at this a little bit later, of this TCP/IP protocol suite are things called requests for comments. These are published documents that go through different phases, and this is actually RFC 871. And by the way, I'm going to mention a lot of RFCs in this training. You should probably write them down. You should document them. If you're going to be taking this information that I'm giving you and going forward to be an IT professional or a network technician or get into security or communications or anything, you're going to build on this knowledge and extend your career. Maybe you're a high school student. Maybe you're a college student. Maybe you're somebody that's my age that's changing careers. Well, you want to make sure that you kind of start to build this library of knowledge. And the RFC is kind of where it begins. And this is 871, a perspective on the ARPANET reference model. And this is really the document that is the fundamental document for much of the things that we're going to look at in this particular series. Let's look at the timeline real quick of TCP/IP, specifically what we call version 4 or IPv4, which is what most of us are used to using when we use our browsers. The early internet and TCP/IP were developed together as part of the US DARPA ARPANET project. In 1973, there was a complete interworking system for the ARPANET. It officially began then. In December of 1974, we had an RFC number 675 for the early TCP. In March of 1977, we had TCP version 2. And by the way, back then, in 73 and 74, there was only one core protocol. It was called the Transmission Control Program, TCP. And then it was revised in RFC 675 in December of 74. After March of 1977, we had a guy named John Postel. I'll show him in a second too. In 1978 through 1980, we had TCP/IP version 3. And then in the early 80s, a bunch of machines, mostly Unix machines and networks, started using TCP/IP version 4 on the ARPANET. And that's, of course, when I started to get on the internet with my first computer. Here's Jean Postel. He was late in the sense that he recently passed away, but he was great. He was called the God of the internet, and he published critical comments in 77 warning that the early TCP was trying to do too much and was actually violating the core principle of layering. So TCP, they took his advice, and TCP, or the Transmission Control Program, soon became TCP/IP, the Transmission Control Protocol / Internet Protocol, and that's where we are today. Okay, the first thing we're going to look at in network types and attributes is the concept of circuit switching versus packet switching. Now, really, in TCP/IP, it's all about packet switching, but let's kind of get this circuit switching thing out of the way. Traditionally, network types have been categorized based on the path taken between the participants. So with circuit switching, a circuit or a full path is first determined and set up before the data is transmitted between two devices. So let's say, for example, we have host A and we have host B. A full path would be set up, or a circuit between both devices before we start sending and receiving data, okay? Now, this is actually a better method for dedicated communications like a phone call. You know, when you use your landline, or even when you do cell phone as they pass through cell towers, the circuit is set up first. Now, in a packet switching topology, there is no fixed pre-established path between the communicating devices, okay? So the data gets broken down into discrete packets first. So that's where our packets come in, right? Our discrete packets. And then what we're going to do is we could theoretically take different paths based on congestion, okay, based on an outage. And if we remember back to the beginning of why TCP/IP was created and the original ARPANET, it was to have a packet switching network that said, you know what, if some catastrophic event happens, you know, like somebody, you know, some enemy fires off a nuke, you know, and this goes up in smoke and this is no longer available, well, then we can switch our paths. Maybe originally we were going this way, right, to get to our destination, but something happens here and we can immediately switch from this site down to this site and change the path, okay? So it's kind of like the letter you send through the postal service, or maybe considering, you know, let's say you're driving in a large metropolitan area like Houston or Chicago, and you're going to determine your route in real time based on maybe some app on your iPhone that's showing you, hey, we've got traffic congestion in this location, or we're doing road repairs in this location, so you can decide to take this different boulevard or take this different pathway to get to that ultimate destination. So that's a fundamental difference between circuit switching and packet switching, and that's what we're talking about in this course, packet switching. Next, let's talk about message transmission methods. And there's really 4 types. And this should be self-explanatory, the first one. But let's say we have client A, and then they're going through some type of intermediate device, maybe a router, okay, going to 3 different servers. We have server 1, server 2, and server 3. So this is a client-server kind of relationship here. The first type is unicast. So unicast is basically sending information to one recipient, okay, kind of a point-to-point unicast transmission. So the datagram is going from client A to server 3. That is unicast traffic. Another type of traffic is broadcast traffic. And that would be saying that client A is going to broadcast their frames or their packets or their datagrams to all the participants, okay? So that would be broadcasting to all servers, S1, S2, and S3. That's a broadcast. The third type is multicast. And a multicast would be saying, okay, we want to send traffic not just to one node and not to all the nodes, but to a group. So let's say server 2 and server 3, they join a multicast group. And so we would send that to, let's say, their multicast group at something like 224 dot something, an IP address. That's a multicast type address. So that's what multicast is. The fourth kind is anycast. And anycast is only available in IP version 6. Anycast basically says send the datagram to the nearest node. So if you look at a wide variety of factors and you determine that server 1 is the nearest server or router, then Anycast would send the packet to that server. Now, one other thing about IP version 6, IP version 6 does not do broadcast, okay? What it does is it gives you the same concept of broadcast by using multicast groups. So it will broadcast to a group, and that is how it accomplishes its broadcasting. So IPv6 only does Anycast, not IP version 4, and IP version 6 does not do broadcast, only IP version 4. Okay, finally, I want to define some other communication and network terms, starting with these three terms up here. There's three kind of main categories of communication. The first one is simplex. Simplex communication is kind of like if I grabbed a bullhorn and went outside and started, yelling at everybody, or a public address system, okay, kind of one-way communication. That's simplex communication. Half-duplex communication is two-way communication, but only one party can communicate at a time. When you were a kid, maybe you got for your birthday some walkie-talkies. Okay, a walkie-talkie is half-duplex. Okay, you say, "Hey, Pete, can you hear me?" Over, and then Pete gets his walkie-talkie and he talks back to me, and we go back and forth. Okay, Citizens Band Radio is kind of like that. Only one person can talk at a time, but it is two-way communication. We call that half-duplex. And some networks still kind of operate in a half-duplex way. So for example, we'll talk about wireless networks. They still operate half-duplex. A Ethernet hub technically operates in a half-duplex fashion. Full duplex, or just duplex, is two-way communication where both parties are talking at the same time. So if Pete and I are on our cell phones and we're talking to each other, that's full duplex communication. Okay, we could both be talking at the same time, and that happens a lot, but it's two-way communication. So that's one way to differentiate some communication types. We also can talk about types of nets, okay? An internet or internets are networks of networks, okay? So you have different networks which are basically administrative domains or their own autonomous systems. And when you connect these together, okay, these networks, that's what we call an internetwork. And basically the internet is the largest of the internetworks that we deal with out there. But there's all kinds of internets that companies have, organizations have, that the military has, that are outside of the, quote, internet, capital I. We also have intranets, okay? So these are networks within a network. So if you think about at your company, you may have your internal web servers, your internal HR department and their servers. That's what we call an intranet because they're networks within networks. Extranet is a special type of network where you connect your network to some large vendor or some strategic partner or some large customer. So it's an extra net that goes beyond the internet or your intranet that's kind of a special use network, okay, that you can set up. You could also say, this is a research firm, a company, and I have a connection to a research hospital or a certain university, or maybe with a military contract, part of that as an extranet. So that's another kind of differentiation. Another way to look at networks are these terms right here. So if we start with the kind of the smallest network, that's a personal area network. So I could do that using Bluetooth. Okay, that's a really short distance. So I could use infrared to my PC or Bluetooth, some short range communication. That's a personal area network. Then the most common really is the local area network. That's what you have, within your home. All of your devices behind your router that you have, that your provider gave you. This is what companies have. Everybody in the call center, or all of the different endpoints on a certain floor. That's a local area network. And this is typically separated by routers or multi-layer switches. If you go from an Ethernet, which is 802.3 to a wireless network, then that's a wireless LAN. So it's a local area network, but you're using the RF band, the spectrum, as opposed to something like Ethernet. A CAN is a campus area network. So if you go up to, let's say, Oregon, and you go to Hewlett-Packard, they have a huge campus, and it's a contained large network. That would be a campus area network, okay? A MAN is a metropolitan area network. And this is often kind of a fiber type network that's for a municipality or local government or the police department and the first responders, maybe the city government, or maybe even it could be a county seat. That's what we call a metropolitan area network. And then finally, we have the wide area network. And that could be some organization like in Arizona and Phoenix. Maybe you've got a Motorola, for example, or one of those big companies, and they have a headquarters, okay, but they have several branch offices and several sites that are geographically dispersed, either across metropolitan Phoenix or maybe across multiple states. We refer to that as a wide area network. So these are some terms that are important that you know moving forward in your TCP/IP adventure. In this lesson, we're going to talk about performance metrics, and it's important to understand the different terms used to provide performance of a network. Now, to be honest with you, this was a bigger deal kind of back in the day when I first started getting into using the internet and the World Wide Web. We were using dial-up modems, and memory was really expensive, and we didn't have, big pipes that went to our service provider. Today, you can use your cable company or you can use your phone company, and you're getting such high speeds that it may not be that big of an issue. However, if you're going to launch from here into an IT career, then you really should understand some of these, what we call metrics or indicators. So performance has several aspects. We want to classify that here kind of early on in our knowledge. The way data is sent is often more important than the actual raw speed capability. So for example, I might have much faster speeds with my wired network than I do with my wireless network. So the way the data is sent, it could be asynchronous in the sense that you get really fast downloads, but you get really slow uploads. So there's these different factors that tie in here we want to be aware of. Now, I titled this slide, Speed is the New Black, because as far as networks go, speed is cool. But speed is a generic term that often relates to the nominal or the rated speed of the network infrastructure. So a lot of local area networks are what we call fast Ethernet, or 100 megabits per second, or maybe 1 gigabit networks, okay? That's the rated speed, but that doesn't mean that's what we're getting, okay? We're probably getting something less than that. Fast Ethernet, which is very common, has a rated speed of 100 megabits per second, or 100 million bits per second. That's what we're talking about here, by the way, folks. That's what's moving either across those wires, that Ethernet cable, or moving across that fiber cable, or moving across the airwaves if you're using an RF or using wireless. It's all zeros and ones. And so this is the theoretical throughput of the network infrastructure. But again, like I said, that doesn't mean that you're actually getting that throughput. Here's an example of running something called a speed test, and you can do this on your own computer at home. You might want to do it, for example, this is me doing a speed test on a workstation at my home office that's using the wired Ethernet. So I've got a Ethernet cable coming from my PC going to my router. As you can see here, I'm getting really fast download speeds, okay? Almost 800 megabits per second. and my upload speed is almost 50 megabits per second. And this is what we call asynchronous, okay? In other words, I have a different upload than a different download. And this is very common, by the way. If you want to get higher speeds of upload, for example, maybe you have to upload big files like I do to my company or my contractor. Well, then I need those big upload speeds. I might have to pay extra for that, right? And then here's an example of my same network, but now I'm using my laptop and I'm using my wireless connection. Well, notice on my laptop using wireless, I'm getting 8 megabits per second upload and about 17 megabits per second download. That's not nearly as good as my wired network. And so that's why I was mentioning earlier, it depends upon kind of the network type that you're using as to the speeds you're getting or bandwidth. Now that term bandwidth is also used to determine radio frequency bandwidth for wireless technologies like this one. This particular laptop is using a technology known as IEEE 802.11n, which offers up to 432 megabits per second. I'm not getting anywhere near that, but this is a wireless computer. Let's talk about the term latency. Latency is a term used to designate any type of delay that occurs in the data communication over a network. Network connections in where there's small delays are often called low latency networks. So example, if you use Amazon Web Services or you use Google Cloud Platform or IBM Cloud or something, you use some cloud provider. Those are low latency networks, okay? There's going to be very few delays on those networks because they just simply have a very well protected and very beefy infrastructure. Network connections that suffer from long delays are called high latency networks, and that's indicative of some type of bottleneck in the network communication. It could be, part of the network is under an attack. Maybe somebody inside the company has launched a denial of service attack. Maybe there's some misconfiguration. Maybe it's just time to replace one of those devices or upgrade the software. Here are some other common causes of latency. It might be problems with the transmission medium. With a wireless network, if you make some change, let's say you move all the furniture around, or you put in a wall, or you just reorganize everything, that's going to affect your wireless network, right? You might have configuration errors on the switches that your workstations connect to, or the routers that those switches connect to. It may be you've introduced some new encryption, and that's going to cause overhead. That's going to cause some delay. Maybe you've got some antivirus programs running. That can slow traffic down, okay? The time to propagate, because your network just wasn't designed very well, okay? So you need to redesign your network, whether it's wired or wireless. There may be some storage delays, okay, in the storage systems that you use for your data, or the database services. The delay may be there. That's where your latency is. Maybe it's just a malfunction of the software or the hardware, or like I said, it could be a certain type of attack. Okay, in this demonstration, we're going to begin our journey through building a portfolio of important websites and organizations and standards that can help you to pursue your deeper knowledge of TCP/IP and the Internet. And we're going to start with the IETF, which is the Internet Engineering Task Force. So if you go up to www.ietf.org, and I highly recommend that in your favorite browser, you create a folder and you add all of these different websites that I'm going to take you through in this demonstration, starting with ietf.org. The first thing you're going to see here on the main website is how to read an RFC, a request for comment. And by the way, it tells you that this is how many of the protocols are specified or designated on the internet. And there's different, layers of RFCs. For example, later on we'll look at the EIGRP protocol from Cisco, which has an RFC, but it's not a fully published standard. And if you notice down here, there's some helpful tips from an RFC author on how to read these. And by the way, this is an excellent exercise in learning more about these different protocols and services, because they're almost all backed up by one or more RFCs. Now, to find out more about the IETF, for example, its mission and principles and who we are, you can click on the About link. And it tells you that it's a large open international community of network designers, operators, vendors, and researchers that are concerned with the evolution of the internet architecture and keeping the smooth operation of the internet, okay? And you can see that it's done in working groups. They also have mailing lists, and they also have 3 meetings annually. And this is the group responsible for those requests for comments and other internet standards. If we click on that link, it'll take you to the RFCs, to some of the things that are in progress, like the drafts. And by the way, if you want to kind of learn about what's coming in the future, what's coming down the pipe, well, go to the drafts, because you'll see a lot of really cool stuff and a lot of really cool technology about what's coming on the internet in the future. Let me take a moment to show you probably one of the most famous requests for comments that's out there, and we'll be looking at this later on in this training, but it's RFC 1918, and we actually refer to certain IP addresses as RFC 1918 addresses, and this is the address allocation for private internet. So let me give you an example. Let's say you're at home and you went out and you bought some wireless router or some wireless access point. Maybe your service provider, your cable provider, or your DSL provider gave you one. Or you go out and you buy a Linksys wireless router or Netgear or something like that, okay? Well, that particular device, it's going to allocate to all of the hosts or all of the things that you use in your home, like your workstation, your PC, your laptop, and it could be things that are on a wire with a cable, a wired Ethernet going to this device, or it could be wireless. It could be your gaming system, it could be your smart TV, your iPad, your phone. You get the idea. But that particular device is going to allocate to your wired and wireless home devices an IP address. And it's going to be allocated from this private internet. So basically, the devices in your home behind that router are using a private type of address, IP version 4, that is not routable or legal on the internet. So some translation has to be done on that particular device to translate to an IP address that's public on the internet and routable and legal. And it's one that your service provider, your broadband provider, your cable company, your DSL company, your satellite provider, whoever, they're going to give you an IP address that's valid on the internet. Or they may actually do some translation on your behalf at their site. The bottom line is, you can see this RFC is going to kind of give us the different blocks of what are called IANA reserved IP addresses, okay? And you can see that they're right here. And we're going to talk about these later on in this course, but I just wanted you to see, kind of the structure of these requests for comments. You can see that they come in different formats. They go through different versions, okay? So, before 1918, there was 2 other versions that have been made obsolete, okay? 1597 and 1627, right? And so this is an example of an RFC. Now, it tells us that the IETF working groups are grouped up into areas, and they have several other members, okay? So here's one you want to know about. First, the IESG. So the IESG is responsible for technical management of the IETF activities and the process of generating internet standards. So they administer this process according to their rules that have been ratified by the Internet Society. That's another group, okay, the ISOG, that you want to be aware of. and it tells you that it administers the process according to the rules and procedures ratified by the Internet Society. So here's the official site of the Internet Society, the ISOC, and you can see up here it's got a link that says the Internet, okay? And by the way, if you want to get deeper and go well beyond what I tell you about the history of the Internet and who makes the Internet work, for example, this is a great site to come to, okay? Our Internet ecosystem, which is an interesting set of information. And by the way, you can download over here a particular document, and we'll take a look at that, and you can see, who's involved with policy, who's involved with the oversight, who's involved with the implementation. So we've talked about the IETF. There's also a group called the IAB, and if you go down here, you can find out more about the IAB, the Internet Architecture Board. Let me make this a little bit bigger for you. So we've already looked at the IETF. We've also got the IAB, which is chartered as a committee of the IETF, and it's an advisory body of the ISOC that we're talking about, the Internet Society. What is it responsible for? Architectural oversight of the IETF activities, the Internet Standards Process oversight and any appeals, and it also appoints the RFC editor. It's also responsible for managing the IETF protocol parameter registries. Okay, what else? Well, there's the RIRs, and these are the regional internet registries, and these oversee the allocation and registration of the internet number resources and things like addressing. Okay, and that's also where ICANN comes in. ICANN is a non-for-profit benefit corporation coordinating the system of unique names and numbers to keep the internet secure, stable, and interoperable. The ICANN community encompasses domain name registries and registrars, ISPs, including cloud service providers, intellectual property advocates, commercial and business interests, as well as non-commercial and non-profit interests. Okay, we also have the IANA, which is the Internet Assigned Numbers Authority, responsible for the global coordination of DNS route, Internet Protocol addressing, IP version 4 and IP version 6 that we'll learn about, and other Internet Protocol resources. And you can see here's a link to all these organizations, and you need to go ahead and add these, including the Number Resource Organization, that coordinating body for the 5 regional Internet registries, RIRs. So you want to add these, the IAB.org, all to your folder, and then use that as kind of an ongoing way to learn more about the internet and keep up with the internet. Okay, so this particular diagram here, which we see at the Internet Society, the ISOC, talks about who's responsible for the policy aspects, okay, protocols, numbers, and names, who does the oversight, the IAB, the NRO, the ICANN, and who is responsible for implementation, which is pretty much the IANA. Okay, so this is a great resource, and these are organizations you need to know about. Now, there's a couple of more that we want to talk about. We're going to take a look at the W3C, which is the World Wide Web Consortium. We're also going to look at ANSI, ANSI, and then the third one is ISO, but I'm going to save the International Organization of Standardization, or ISO, with its OSI for a dedicated demonstration in the next lesson. So let's go take a look at the World Wide Web Consortium. Here at the World Wide Web Consortium, which is an international community that develops open standards to ensure the long-term growth of the web. Now remember that the World Wide Web is really only part of the internet, okay? So specifically, when we hear the World Wide Web, we want to think about that part of the internet that uses protocols like the hypertext markup language and protocols like HTTP, because there are other protocols and services and applications that can run on the global internet that are not necessarily the World Wide Web, okay? And that'll become clearer as we go through this training. But notice that over here on the left-hand side, they're going to show you how the web integrates with different industries like automotive, publishing, web payments, telecommunications, the Web of Things, okay? So there's the IoT, maybe you've heard of that, the Internet of Things. There's also the Web of Things. So the Web of Things is a smaller subset of the IoT Internet things, because the Internet things may not use the same protocols and services that the World Wide Web uses, okay? And you can, of course, click on this and find out more about the W3C, their mission, some facts, and other information. So that's an organization. You want to add that to your knowledge base as well. The final one I want to look at in this demonstration is ANSI, which is the American National Standards Institute. So as you can see, this one is more focused on, America, North America specifically, but also its integration and cooperation with other organizations and other entities like the EU, for example. But if you go and you take a look at the frequently asked questions, you can get an overview of ANSI, and you should. Okay, what is it? Well, it's a coordinator of the U.S. private sector. It's a voluntary standardization system. It's been around for more than 90 years. Okay, what do? They voluntarily work on consensus for standards systems, a neutral forum for developing policies and standards, kind of serving as a watchdog for the development of standards and conformity to assessment programs and processes. That sounds, kind of general, but you can get much more deeper into ANSI. For example, how do they interact with, consumers and other organizations? And you can also click on About ANSI and find out their mission. You can see they've been around for a long time, since 1918, and they're a 501c3 non-for-profit organization. And you can see that they've got several other websites here and other affiliations that they're with. Some of the affiliations you might also want to check into, okay? I didn't add these to my list, but there's obviously, we mentioned we're going to look at the ISO, the International Organization for Standardization, in an upcoming lesson and demonstration. There's also the International Electrotechnical Commission, the IEC. We also have the International Accreditation Forum, the IAF, and then others, okay? Because they are also members of other international organizations across the globe. I hope you enjoyed this first demonstration where we went in and looked at different types of standards and organizations: IETF, ISOC, IESG, the IAB, the W3C, IANA, and ANSI. And again, we left out the ISO. And by the way, what's interesting is notice that this is the International Organization for Standardization, but it's called ISO. Why is that? Well, technically, this is a French organization. So if you were to look at the French title of this organization, it actually is ISO. So that's why the acronym ISO doesn't match the actual name of the organization, because this is the English rendering of the French official name of the organization. Okay, so just in case you were noticing that off the bat. And we'll look at the ISO, specifically their OSI model, in greater detail in upcoming lessons. All right. Okay, in this video, we're going to look at some math. And maybe you might have heard, hey, there's no math in this. Well, that's not true. Okay, there's going to be some math. But let me just say this. One thing you're going to see is just some basic kinds of math that we need for networking. If you already understand like binary and hexadecimal numbers, you could actually skip this video. Also, one thing you're not going to see is my big head in this training lesson, because I want you to focus on what's on the slides for this particular lesson. So let's start out with base 10. Okay, base 10 is actually one of the most common types of math systems. It's used in most modern civilizations. It was one of the most common used in ancient civilizations, and really, if you think about it, because we have 10 fingers, it kind of makes sense that we're going to base this on tens, okay? It's also called the decimal system because a digit's value in a number is determined by where it lies in relation to the decimal point, okay? Now in a base 10 system, there are 10 possible numbers, 0 through 9, and their true values based on their position in the system. So this is obviously something that we're all very familiar with, okay? If you go all the way over here to the right-hand side, notice that we have in this little table, to the far right-hand side, we have the ones column, and then we have the tens column, and then we have the hundreds column. And you can see that, you know, the ones goes from 10 because it's 10 times that, and then hundreds is 10 times 10, thousands is 10 times 100, and so on. So it's based on tens, right? So we have the number 457 because we have the number 7 in the ones slot. We have the number 5 in the 10 slot, that's 50. And we have the number 4 in the hundreds slot, that's 457, something you're very familiar with. Well, that was easy. But what about binary math? Well, binary is extremely important to computers because at their very base nature, computers work as binary operations, zeros and ones. So think of a 0 and 1 as a 0 is off, 1 is on, or 0 is no, 1 is yes. So these kind of binary decisions are very powerful for computers. So in the base 10 system, you know, we were based on tens, but in the base 2 system, we've only got 2 possible numbers, 0 and 1. So if we look, now we have these columns, and we can see the first column here is the 1 column, which can only be 0 or 1. And then as we move up, we're kind of taking that number and we're doubling it. Okay, we have the 2 column, we have the 4 column, we have the 8 column, 16, 32, and so on, okay, all the way up to the 512 column. So you can see how we're doubling the value of the column as we move. So what we're doing here is notice, and what we have here on the far left is the 512 column, which is 2 to the 9th power, okay, and we have turned off that bit. So we're not going to even use the number 512. But if we move over to the next column, the 256 column, or 2 to the 8th power, we're turning that one on. So we've got 256. We'll go to the next column, the 128 column, which is 2 to the 7th power. We're turning that one on. And we're going to turn on the 64 column as well, or 2 to the 6th power. Turning off the 32-bit, turning off the 16-bit. We're going to turn on the 8-bit, turn off the 4-bit, turn off the 2-bit, and turn on the 1-bit. So if we add up all the bits that are turned on, 256 plus 128 plus 64 plus 8 plus 1, we get 457. Okay? Now what if we went to the 2 column and we turned on that bit? Well, we'd have 459, wouldn't we? Because we're adding 2 to that. Let's say we didn't turn that one on, but we went to the 4 column and we turned on that bit, or 2 to the 2nd power. Well, that would turn on the 4-bit, so now we would have a number of 461, wouldn't we? So this binary math is very important. Now, computers work with binary numbers, but often what we do is we convert the binary numbers back into decimal numbers because that's what we understand better. So later on, when we look at an IP address, we're actually looking at some binary numbers, or what are called octets, group of 8s, that are converted into decimals so that we can better understand those, right? So that's binary math. And here's some examples, okay? So you can see, let's go to the second one. If I have a binary of 101, well, I'm turning on the 1-bit, I'm turning off the 2-bit, but I'm turning on the 4-bit. So that gives me 5, doesn't it? Let's go down here to the one that's 12. If I turn on the 8-bit, 1, turn on the 4-bit, 1, and then leave the 2 and 1-bit 0, well, that's going to give me 8 plus 4 is 12. So here's ways that we represent these in binary. Now the good news is, remember, I'm all about modern TCP IP and moving forward. You know, back in the old days, we would do this by hand, but there is absolutely no reason today you should be doing this by hand. We've got plenty of calculators, and we'll be talking about subnet calculators later on. So unless you're taking some exam and they force you to do this, you know, by memory, then you may need to come up with some techniques for taking, you know, an exam and answering a couple of questions. But there's plenty of training, there's plenty of live lessons that can help you do that. We're not going to focus on that in this course. We just want to understand the underlying math behind this. So here you can see in a calculator, for example, I say I'm going to type in 819. So this is the scientific calculator, and I've got decimal chosen, right? So I put in 819, and then I go over to my calculator and I convert that and put in the binary. And so we can see there's the binary representation. One thing you'll notice, if the last bit is turned on, if it's a 1, it's going to be an odd number, right? Because it's adding 1 to everything. So if the last bit's turned on, it's going to be an odd number, right? So, you know, this is something that we're going to use very often, a scientific calculator or a subnet calculator, okay? So what does this mean to a computer, this decimal and binary? Well, the computer interprets combinations of binary numbers ultimately as instructions or words, okay? They're groups of binary numbers. For example, each lowercase and uppercase letter in the alphabet is actually assigned a different binary code. And then each of those is assigned a decimal representation. We call that ASCII, A-S-C-I-I. And when I get to my whiteboard presentation, I'll talk more about that, okay? So, for example, if you had ASCII code, 97, okay? Well, that would be the lowercase a, okay? So these zeros and ones to the computer eventually get translated into something much more meaningful. Now here's hexadecimal math. Hexadecimal is what we call base 16 math. So it's based on 16s, right? So you have values of 0 through F. So you have, the first 10 decimals of the base 10, but then we have to add 6 more, don't we? So we use the letter A, B, C, D, E, and F, and that's hexadecimal. Now, where does hexadecimal math matter to us going forward? It really matters in 2 places. One, on the network interface in your computer or your laptop or on an access switch at your company or even in your mobile device. The network interface actually is identified using a hexadecimal identifier, okay? So that's one place, we call it a MAC address. That's one place where hex is important. The other places it's important is in the newer version of Internet Protocol. Now I mentioned already IP version 4. Well, in the newer version, IP version 6, that's such a huge address, okay? It's a 128-bit address that we represent that as a hexadecimal number. So these are important because there's a couple of places where we use hex identifiers, okay? So just realize that there's 16 possibilities, 0 up through the letter F, okay? And so here's the values of each of these. For example, the number 10 in decimal is expressed as the letter A in hexadecimal. So here's an example, right? In the first column, okay, we have what we call 16 to the 0 power. So in this first column, the values are going to be anywhere between 0 and F. So if we have the number 7, 7 times 16 to the 0 power gives us 7, right? Now I mentioned earlier, if it were 10, then it would be the letter A, right? But here, the number 7 looks the same because when you go up to this little table here, notice that 7 in decimal is also still 7 in hexadecimal. And that's true all the way from 0 to 9. But after that, it starts to change. Notice in the second column, this is 16 to the first power. So these are going to be combinations of 16, okay? So 15 times 16 to the first power, in other words, 15 times 16 is 240, okay? When we get to the third column, which is 16 to the second power, these values are all combinations of 16 times 16. Okay, so if I have the number 2 in that column, it's basically 2 times 16 to the second power, okay, which, by the way, is 512. In the fourth column, I've got the value A, and this is 16 to the third power, so everything in this column is going to be a multiple of 16 times 16 times 16, right? 16 to the third power. And this is no different, by the way, than decimal or binary. You know, we have these values in the first, second, third, and fourth column is whatever the base is. If it's base 10, it's 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. If it's binary, right, it's 1 to the 0, or 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, same thing. But this is base 16. So if we have the letter A, we know that A has a value of 10, doesn't it? So 10 times 16 to the third power is 40,690. So 40,690 plus 512 plus 240 plus 7 gives us 41719. So A2F7 equals 41,719. One of the advantages of hexadecimal math, and it's why we use it to identify an address on a network interface card, and why we use it in IP version 6, is it's a more efficient way to express really large decimal numbers and really large binary numbers, okay? So it comes in really handy, okay? Hexadecimal math. And of course, notice that if I go to my calculator and I set it on decimal and I type in 41719, and then I go over to the left-hand side and I click in the hex radio button, it converts it for me, and there it is, A2F7, okay? So understanding decimal math, understanding binary math, and understanding hexadecimal math is important as you move forward in your TCP/IP and your networking career. But remember, let's be smart, and let's go ahead and use tools like calculators and subnet calculators. Don't get hung up on having to do this in your head or write this out on paper, okay? All right. In Lesson 2, we explore the ISO OSI reference model. We'll introduce the International Organization for Standardization, we'll explore general concepts of the OSI model, and then we'll examine the 7 layers of the OSI model. Okay, I'm going to start out this lesson with a demonstration, and we're going to look at the ISO, the International Organization for Standardization, which is extremely important. And as you pursue your information technology future, as you work with the internet and internet protocols and possibly get into things like, risk management and security and all these great things, governance, compliance, you'll need to be interacting with the ISO, the ISO. So let's go to All About ISO. Okay, and take a look here, and we're going to find out it's an independent, non-governmental international organization with a membership of 162 national standards bodies. Now, I mentioned earlier that it's actually, if you look up here in the URL, okay, it's actually Organisation Internationale de Standardization, okay? So it's really in French, and you can see that their headquarters is in Geneva, Switzerland. So it does tell us, however, what are standards, okay? International standards make things work. And you can see they give us an example here of an ISO standard 13216 for car seats for babies, okay? So it obviously goes beyond just the internet, right? They've got standards for pretty much every industry, from technology to food safety to agriculture to healthcare. So they're a huge and very important organization, okay? And if you go to standards, you can see there's many standards that they deal with, okay? They develop and they publish international standards. Now, one thing they don't do is actually certify you. They don't provide accreditation. So for your company, let's say you're trying to adhere to some ISO standard. For example, I think on the main page, they mentioned their top 3, the most common, and you can see here's the ISO IEC 27001 Information Security Management. That's a huge, very important standard. So as a security practitioner myself, who has a wide array of certifications like CompTIA Security Plus and CISSP and Cisco CCNA Security and others, a lot of those certifications, you have to learn about these ISO IEC 27001 security management standards. So, you know, that's a biggie that they deal with. And we'll just take a look at that one while we're here, okay? Keeping your information assets secure, okay? Providing ISMS, a systematic approach, okay? Using information security management systems to basically protect people, processes, IT systems, and applying risk management processes. And it tells us it's a family of, you know, several standards. There's more than a dozen standards in the 27,000 family from the ISO organization. Now, one of the main reasons we're looking right now at the ISO organization is because ISO many years ago, decades ago, came up with their OSI model, okay? And so we're going to be looking in this particular lesson at the OSI model from ISO and how that OSI model can be used for a wide variety of purposes. And it can be very helpful in allowing us to kind of deconstruct and to understand in a modular fashion the different applications and services and protocols that work on the internet using TCP IP. So I wanted to make sure we started out this lesson talking about this organization, and then if you'll go up here and spend some time on your own and going through here, you'll start to develop a foundation for this, and you can even go here and look at the history. And as we go through and we take a look at the OSI model and the TCP IP model, which is a derivative of that 7-layer model. So we're going to be looking at a 7-layer OSI model and a 4-layer TCP IP model in the upcoming lessons. All right. The ISO OSI model is an important tool for explaining how networks function and for guiding software and hardware development that supports the internet. Now, even though we rarely perform programming or development strictly using this 7-layer model these days, we still do refer to devices, protocols, and services as things like layer 2, layer 3, layer 4, upper layer, layer 5 through 7, and so on. So obviously the term layers is key here. And these are at the center of the model, as each layer is responsible for certain tasks. So a developer like Susan could basically focus on layer 3, the network layer, while only needing to interface with the layer above that in her development and the layer below that in her development. Now, some folks may just focus on the lower level functions, okay, physical, data, network, and transport, layers 1 through 4, while others may focus on the upper layer functions, layer 5 through 7, session, presentation, application. And for decades, this was the most common and popular demarcation point, okay? The lower was kind of the hardware and the device drivers, where the upper was the software and applications and services. Today, however, if you're working with something like Google Cloud Platform as a cloud provider or Amazon Web Services, all you really have to be concerned with is pretty much layer 3 through 7. Okay, they'll completely handle layer 1 physical and layer 2 data link in their infrastructure. As a matter of fact, if you're paying them, Google or Amazon Web Services, for some managed service, they may even take care of everything from layer 1 all the way up to something like layer 6. Okay, so we call that software as a service. So if you're using Workday, and I'm here in San Francisco, which is the headquarters of Salesforce, they have the biggest building downtown, or maybe using Google Drive or Dropbox, well, then they'll take care of everything from layer 1 through layer 6. Now, when we talk about different types of technology, for example, we talk about an access switch, which is the thing that all of your devices connect to, or maybe your wireless access point, okay? That would be a layer 2 device, and we call it a layer 2 device, a layer 2 switch. A router or a multi-layer switch is typically a layer 3 device, okay? And it can even be a multi-layer switch, an MLS, and a multi-layer switch is going to operate at layers 2, 3, and 4. We often talk about providing security. Maybe we have a next generation firewall and we say we're going to provide layer 5 through 7 inspection or content security. Well, that's what we call the layer 5-7 firewall because it provides security at the session, presentation, application layer. And we often use that term for what we call deep packet inspection. So even though we don't strictly program or develop to the OSI model, these layers are still very important in your networking and IT career going forward. And so you might want to memorize these. If you're going to get any type of certification, you'll have to memorize these eventually. So there's mnemonics out there. So you could say, you know, we can start at the bottom or we can start at the top, whatever is easier for you to do 1 through 7. But you could say all people seem to need data processing. That's a very common one, okay? So whatever mnemonic, you can go search the web, and they have mnemonics for the OSI model to help you memorize that. You should memorize it from layer 1 physical all the way up to layer 7 application. Let's continue and look at those lower layers, which you want to be well aware of in TCP/IP, because basically that's where TCP/IP do all their work. Another term to be aware of is what's called the PDU, the Protocol Data Unit. Each of these layers has their own protocol data unit, and these are the messages for communicating information between the different layers, between the different protocols. And remember, each one of these layers is especially responsible and is especially well equipped to interface with the layer above it and below it. So let's say that you're sending an email message, and that email message is using the SNMP protocol. So it's coming down from the upper layer, the application layer down, and it finally gets to layer 4, the transport layer. At the transport layer, it's going to use most likely connection-oriented TCP or connection-less UDP. Well, this is an email message, so it's going to use TCP. So the upper layer data, which we know is an email message, I'll just put a little email in there, that is our upper layer data. So it comes down to layer 4, and then layer 4 is going to put a header. And that header is just basically metadata that TCP uses to do all the things that TCP has to do. And we'll, of course, talk about all of that. So this PDU at layer 4 is called a segment, okay? Now this segment of layer 4 then gets sent down to layer 3. And this segment becomes the upper layer data that layer 3 is working with. Well, layer 3, and most often we're using the IP protocol, is going to take the layer 4 header and then put its own header in front of that, a layer 3 header, okay? And that's the Internet Protocol IP metadata. So for example, what would be in there? Well, the source IP address, and the destination IP address. That would be in there, very important information. That PDU, which is referred to as a datagram or a packet, gets then passed down to layer 2. Now, at layer 4, most often it's TCP or UDP. On the internet, at layer 3, it's Internet Protocol IP. Layer 2, that can be a whole bunch of data link protocols. There's a bunch of them. But let's say we're going to use the most common that we're familiar with, and that's Ethernet, what you're using in your home, okay? So all of this information, this datagram comes down, and that becomes basically the upper layer data. It's the original email message plus the layer 4 header plus the layer 3 header. This information is going to be encapsulated. It's going to be framed, and that's why we call it a frame, because there's going to be something on the back, okay, and there'll be something on the front, okay. So this frames the entire datagram or packet. So we have a footer, a layer 2 footer, and the footer usually has like a checksum in it. So if this frame gets corrupted on the wire or in the wireless, it can just tell it to resend it, okay? So it has a checksum in there. And then we have the layer 2 header, which for most of us is the Ethernet header. And as we'll learn, this has stuff in there like the source and destination MAC address, or the address of the network interface card or the network interface. Well, that frame then goes down to layer 1, the physical layer, which, by the way, could be, a lot of different things, okay? It could be sent across some fiber connection. And this is where all this information then gets changed and encoded into zeros and ones, because that's where, so down here, our protocol data unit, our PDU, is actually binary, okay? Zeros and ones sent across the wire or sent across the wireless RF using some type of physical medium. Okay, let's look at the 7 layers of the ISO OSI model. And we're going to start at the top with the application layer. So layer 7 is application. Layer 6 is presentation. Layer 5 is the session layer. Layer 4 is the transport layer. Layer 3 is the network, or it's also called the internetwork layer. And then layer 2 is the link or the data link layer. And then down here at layer 1, we have the physical layer. Now let's go ahead and then kind of describe what these are. Layer 7 is application, and that is to accomplish a networked user task. Now remember, these are applications that are internet enabled or web enabled. So if you're running, let's say, your Microsoft operating system, and you're running, let's say, WordPad, that's not a layer 7 application, okay? Has to be web enabled or internet enabled. Layer 6 is the presentation, and that is expressing and translating data formats, okay? You also might see some encryption and decryption happen there, but that's where we kind of, take stuff and put it into ASCII format or Unicode format. Layer 5 is the session layer, and this accommodates multiple session connections. Something else that also operates at layer 5 is the security protocol HTTPS or SSL TLS. Here's layer 4. That's the transport layer, which connects multiple programs on the same system. So if you're running several web browsers, going to several websites, that's the transport layer, TCP and UDP. Network layer 3, that facilitates multi-hop communications across potentially different link networks. So this is going forwarding datagrams across routers. That's layer 2, the link layer or the data link layer. Communication across a single link, including media access control. So that's where that MAC address resides. Up here we have that IP address. Down here we have the MAC address. And then the physical layer, which is layer 1, specifies connectors, data rates, and encoding bits. So turning zeros into ones. Here's some example of our layers again, and I'm going to give you some mnemonics here in a second that's going to help you memorize these layers from top down and from the bottom up. But let's kind of look at some of the common protocols that operate here. So at layer 7, things like HTTP, like your web browser, file transfer protocol, SMTP for email, DNS for name resolution, and Telnet for terminal emulation. Presentation layer, this would be ASCII, also graphics files like PNG, video files like MPEG and AVI. And I have a little history in the music business, and so we would use MIDI to interface with different systems. So MIDI works at layer 6. Layer 5 is the session layer. As I mentioned, SSL TLS operates there. SQL, okay, structured query language for your database. Microsoft's RPC, remote procedure calls, and certain file systems like NFS. Down here at layer 4, the transport layer, TCP and UDP are the most common, but Novell's SPX from days gone by operated there, and AppleTalk also technically operates at layer 4, kind of a layer 4, layer 3 protocol. Here's layer 3, the network or internetwork layer, IP, Novell's IPX, the ICMP protocol, ICMP version 4 and version 6, ARP operates here if you're in IP version 4, and of course our layer 3 devices, routers, multi-layer switches, load balancers, IPS prevention, IPS sensors, anything that's going to forward datagrams through the device. Here's layer 2, the link or data link, bridges operate there, switches operate there, protocols like SLIP and PPP, and we'll be talking a lot about PPP in this course. That's also where Ethernet's happening, okay, which is very common for us. Our wireless 802.11, maybe G11N, that also operates on layer 2. And then of course at layer 1, the physical layer, binary transmission, encoding, bit rates, and voltages. So like a positive voltage would represent a 1, okay, a 1 bit. A negative voltage would represent a 0 bit, okay, so that's one way we get those zeros and ones across the wire. Well, how do we remember some of these things? It's always good to have some mnemonics, so here's a couple that might help you. If we're going to go from the top down, okay, starting with application and then presentation, you could do this one. All people seem to need data processing. That's a very common one to help remember this. All proper suitors tell no devious phrases. That's one you might want to look into. Now we go from the bottom up, okay, starting at the physical, then the data link, and then the network. We could do please do not throw sausage pizza away. I know that Peter and I would hate to see that happen. Please do not tell secret passwords anytime. That's one you might want to use. Or this one, physical data networks transport session presentation applications. Okay, so some mnemonics to help you remember the OSI 7-layer model from the top down and the bottom up. Welcome to Lesson 3, TCP/IP Protocol Suite and Architecture. We're going to get familiar with the network interface layer, then we'll look at the internet layer, and then we'll look at the transport layer, and we'll finish up looking at the application layer of the TCP/IP model. Let's go ahead and compare some reference models here. Okay, I want to compare the OSI model to the TCP/IP model. The OSI model, if we notice that we've got our number of layers here, layer 1, 2, 3, 4, 5, 6, 7. You can see here's our 7 OSI layers. Notice that TCP/IP really only has 4 layers. This hardware down here, or the physical, it's not part of the TCP/IP model. Now this 4-layer TCP/IP model And this is arguable, but it was actually developed before the OSI model. And it's actually more indicative of what our modern networks use. And it was inspired by that original ARPANET, that Department of Defense project, also referred to as ARM, ARM. And this model actually gained popularity with the emergence and the dominance of the Microsoft operating system. Now, as I mentioned, this model doesn't officially deal down with the hardware, okay? Also notice that we've got this network interface, or layer 2, that's similar to the link layer, okay, or the data link layer of OSI. Also notice that up here at the application layer of TCP/IP encompasses layer 5, 6, and 7 of the OSI. So there's no official presentation layer or session layer. And actually, most modern programs and apps typically perform the functions of layer 5 through 7, and even sometimes the functions of the transport layer. Okay, and we'll actually see this later on. Sometimes if you're using, let's say, some fully managed service from a cloud provider like Amazon Web Services or Google Cloud Platform, they'll do everything all the way down pretty much to, the link, or from the physical up to the network or the link. So lots of different variations out there of how this is used. But in this lesson, I wanted to first show you the differences between the 7-layer OSI model and how it maps to this more modern TCP/IP model, although we're still going to use both of these. Now, I want to really talk about the main aspects of this network interface layer. Okay, so in the OSI model, it's called the network or the internet layer, or the internetwork layer. In the TCP/IP model, it's called the internet or the internetwork layer. And so I want to focus on that here in this lesson. So let's look at the network interface or the link layer, which is the equivalent of the OSI link layer, with the goal of sending and receiving IP datagrams or packets on behalf of the layer above it, the network or the internetwork layer. It's also referred to as the network access layer. And this is where the TCP/IP upper layer protocols and services are going to actually interface with the local network. So often when we think about the network or the link layer on an operating system, it's made up of what we call device drivers or code. So a lot of us will never really actually probably install a device driver, but you might. Let's say you get your own PC, your own personal computer, and you open it up and you put in another extra network interface card. In that PC on the motherboard, there'll be some slots in there, and you shove that card in there and it's got a little Ethernet, or maybe even it's a wireless kind of card. Either way, when you put that into your computer, you'll have to install, most often, some device drivers or something you download from the vendor or the manufacturer. Now, the operating system may actually have its own native device drivers because of plug and play. Like in a Microsoft system, it might recognize that card and go, oh, I know what that is. I'm a Microsoft operating system and I have a relationship with that vendor, okay? That Hewlett-Packard card. And so I've got an adapter, I've got some software code I can use, or you could go ahead and use something from that vendor. And often it's better to go ahead and use the vendor's device driver or program that goes along with that card, because it'll be updated and it'll actually have additional functionality. So that's where the term device drivers come from. It's really just a program, a software program. Now, this link layer or the network interface layer is arguably considered part of the stack architecture, even though strictly there are no core TCP/IP services that run here, okay? So to be honest, the TCP/IP services technically are running at the layer 3, the network or the internet layer, and then above that, okay? But the interface or the link layer does a whole lot of stuff on behalf of that network layer and above. And again, that's where those device drivers and other programs come in. Now on some networks, there's no TCP/IP protocols or services running at this layer. And I mentioned this earlier. If you're using Amazon Web Services or Google Cloud Platform, this layer is actually kind of unnecessary for you to be concerned with because their virtual machines that they use, like VMware or Xen, those virtual machines and virtual appliances that they use, they're taking care of all this stuff at the link layer. You really don't need to worry about this, most likely on your own home computer. If you're going to be adding or upgrading or updating some network interface on one of your own systems, or if you get a job in the future at a company where you have to go and deal with the laptops and the PCs that are being installed or deployed in some local area network at a computer, at an enterprise. Also, TCP/IP over Ethernet, or OE, is going to also handle their own layer 1 and layer 2 functionality. TCP/IP supports many different link layer or network interface services, including Ethernet LANs. They can support metropolitan area networks like FDDI. They can support underlying technologies like DOCSIS, which is what you would use if you were using your cable provider, and DSL. They can also support wireless voice networks like voice over IP, wireless LANs, cellular, and satellite. So all of the different technologies that will operate at the layer 2 or the link layer, TCP/IP can run on top of all these different types of layer 2 and layer 1 medium. And they also use a wide variety of encapsulation techniques. And when I say encapsulation, I mean we're not just going to put a protocol header on stuff like we do at the IP layer. Remember early on I showed you that FedEx package and we had that FedEx air bill? Okay, that's the header. But with layer 2 or link layer protocols and services, we have a header and a trailer. And so we call that encapsulation. Right? We have metadata on the front and metadata on the back. They also support different message transportation or message transmission units. Different networks allow for different default sizes of packets and frames, okay? So one network might support a larger type of frame than another network, okay? Well, the good news is we can accommodate that at layer 2 and different ways that we frame or encapsulate that data that we get from the upper layers, layer 3 through 7. Okay, let's get familiar or more familiar with the OSI layer 3. We call it the network layer or the internet layer. And remember that this is layer 3 and it interfaces above it with layer 4, the transport layer, which we have TCP and UDP primarily. And of course, layer 3 is going to function down here with the network interface or the data link layer, which is layer 2. And so there's a couple of protocols right off the bat that kind of reside kind of in between layer 3 and layer 2, and that's ARP, Address Resolution Protocol, and Reverse ARP, which we don't really use much anymore. But ARP protocol we use, and we use ARP with TCP/IP or IP version 4, okay, only. So here's our kind of internet protocols that we have at layer 3. So we have IP version 4, okay. Remember, there is no version 5. We went right to version 6, which solved a bunch of problems, for example, giving us a much larger address space, 128-bit addresses as opposed to 32-bit addresses. Some other things that function here with IP is IP network address translation. So sometimes inside of our company, we're using what's called an RFC 1918 private address, and we have to translate that at our edge device or our edge router. We call it the customer premises equipment. We have to translate that into a publicly globally routable IP address. So IP network address translation functions here. Also security, IPsec, IP security functions here. Okay, and we also have relatively new but mobile IP, which is going to help us with our mobile devices as they roam around and still use Internet Protocol. So that's what's kind of going on here with IP version 4 and version 6. Then we have some IP support protocols. We have ICMP version 4 and we have ICMP version 6. And these have notification messages, they have error messages, and they're kind of going to help us with some diagnostics on behalf of IP. We also have what's called neighbor discovery, and neighbor discovery is basically used with ICMP version 6 or IP version 6, and this neighbor discovery or these ICMP v6 discovery protocols actually take the place of address resolution protocol, which is only used in IP version 4. ARP is no longer used in IC or IP version 6. Instead, we rely upon ICMP version 6 to take care of that functionality. And then we have this category of IP routing protocols, okay? So we have routed protocols, protocols that can be routed, and really IP is the main routed protocol, but we had others in the past. Let me put a little line here. We had protocols like AppleTalk was a routed protocol, okay? You had a protocol called IPX SPX, which was also a routed protocol. We also have a protocol that's still used called ISIS or ISIS. So there are other routed protocols, but we're talking about TCP IP here, so all we really care about is the Internet Protocol, routed protocol. Now there are routing protocols, and these are the ones that forward those IP datagrams or IP packets from one device to another in the packet switched network topology. Historically, some older ones were RIP, Routing Information Protocol, RIP version 1 and RIP version 2, and you still see RIP version 2 used primarily in small networks or Microsoft networks. Okay, there's also the Hello protocol, which is used between layer 3 devices like routers. We have EIGRP, there was a proprietary Cisco protocol called IGRP, and they enhanced it and came up with EIGRP, and it actually has now, it was proprietary, but they've also written some requests for comments, some RFCs, so it's actually a published standard, okay, EIGRP. Another very popular protocol is the Open Shortest Path First protocol, or OSPF, and then on the internet, the points of presence, the service providers, the cloud service providers, most of those internet providers are going to use the Border Gateway protocol as their routing protocol. And realize that these routing protocols, they all have a version for IP version 4, and then they also have a next generation version, okay, for IP version 6. So all of these I listed here have a next generation version, and some of them were totally rewritten, okay, and completely redone to support IP version 6. So there's kind of our layer 3 internet protocol support protocols and routing forwarding services in a nutshell. Okay, in this lesson, we're going to look at the transport layer, but I first want to compare the 7-layer OSI model to the 4-layer TCP IP model. And actually, this model is more indicative of what we use nowadays. Microsoft really popularized this 4-layer model. So with the 4-layer model, you have an application layer which basically encompasses layer 7, layer 6, and layer 5 of the OSI model. So the application layer, the presentation layer, and the session layer are all kind of enveloped into this application layer. So that's our top layer. Then we have the transport, and that's the same thing as the OSI model. So we have the transport. It's often also referred to as the host-to-host layer because you're using your port numbers to identify those hosts and those sockets, the applications they're using. So we have layer 4 is transport. Layer 3 in the TCP/IP model is called the internet or the internetwork layer, and then layer 2 and 1 are combined. And technically speaking, in the TCP/IP model, we don't include the hardware, okay? So the lowest layer of the 4-layer TCP/IP model is this, what we call the network interface or the link, okay? So let's talk more about this transport layer as we realize that it's the same. It's layer 4 either in the OSI model or the 4-layer TCP/IP model. So the transport or host-to-host layer allows end-to-end communications logically over networks or internetworks. It creates a logical connections or ports that are made between the host either in a reliable, connection-oriented manner with TCP or an unreliable, connectionless manner with UDP. TCP/IP identifies the source and destination process or service. Transmission Control Protocol TCP will ensure the reliable and flow-controlled delivery of data, typically using IP, and of course this happens at layer 4. If you use the User Datagram Protocol, UDP, this is a more efficient, streamlined version of TCP that actually sends data between hosts without that reliability flow management that we use in TCP. We often use UDP for like streaming audio, streaming video, conferencing, things like that. The TCP/IP transport layer includes specific functionality of the OSI session layer 5 as well. Okay, I'm here on my PC, which is actually an HP PC, and you can see that if I go to the properties here and go to properties, you can see that it's not a real new operating system. It's actually Windows 7 Professional with Service Pack 1. Okay, so it is a 64-bit operating system, but it's not a super new operating system. So this is representative of a lot of the things you'll see, pretty much across the globe. Windows 7 still very popular as an operating system. But my main goal in this demonstration, as we kind of observe the application layer, the thing I want to really get across to you is that the application layer of the OSI model or the TCP/IP model is not necessarily applications. Okay, let me give you an example. On my Windows operating system, here's an application called Paint. And here's an old picture of me from the 90s when I was in my rock band. And you can see that Paint is an application. It's a program that runs on my operating system. However, this program does not use TCP/IP. It doesn't connect to the internet. It doesn't use the World Wide Web. It has no capability within this application to actually connect to my network interface card and send frames and packets out onto the internet. Now, here's the same thing with something like Calculator. It's a program, it's an application, it runs on my operating system, but it, like Paint or WordPad, is not a layer 7 application, okay? And by the way, we're going to be using this calculator. It's a very excellent one to use. Use the programmer calculator and add the unit conversion, because as an IT professional, you may need to come in here and say, okay, I've got decimal 10. What is that in hexadecimal? Oh, it's A, okay? What is hexadecimal A or decimal 10 in binary? 1010. Excellent. So we can use this calculator to help us, for example, when it comes to looking at hexadecimal and binary and decimal. We can also use this to say, I want to convert from feet, let's say 100 feet, to meters. So 100 feet is 30 meters. That also comes in handy with networking. For example, if you're running cable in an environment, or if you're setting up a wireless network and you want to know how far away your endpoints are from your wireless access point or the antenna. And so you may need to convert from feet to meters and so on. So the point is, this is a very valuable application. It's a valuable program, but it's not part of the TCP/IP or the OSI application layer because it doesn't use the internet. It's not connected to the internet. Now, some applications, for example, I'm recording this. You can see me recording in Camtasia. This is actually a program or an application that runs on my system. However, when I bring up Camtasia for the first time, it does ask me if I want to check for updates. Okay, so we have programs like that that run primarily locally on our operating system, but they do have a program or code or an application within the application that can connect to the internet and say, let me get some updates, let me get some upgrades, let me download some things like that. So some applications that seem to be local can also be connected to the internet. So for example, when I run a program like Malwarebytes, okay, well, this is a program that obviously is going to look for things on my system. It's going to scan for malware and exploits and ransomware on my system, but it does connect to the internet. It uses application layer 7, specifically the HTTP protocol, to go up and connect to a server and bring down updates. Say it says my updates are current or other code that Malwarebytes needs to run. So that's a very common application layer program, but remember, the program is using the application layer service HTTP. So for example, I like to use as my search engine DuckDuckGo, which is actually a very secure search engine, and I prefer it over some of the big ones that are out there, okay? But this is actually a program that uses the application layer 7 of the OSI model because it uses HTTP. Here's another program, okay? This is Mozilla Thunderbird. So this is a program that is actually using several protocols of the OSI or TCP/IP model. Specifically, when it goes to send email, it's using the SNMP protocol, which we'll talk about later, the simple message transport protocol. When I pull down email messages from my mailbox, I'm using the Post Office Protocol version 3 or POP3, and I can use unsecure or secure versions of those. So this is an email client. It uses several protocols at the application layer of the OSI model or the TCP/IP model. Here's another program that uses several services or protocols of the TCP/IP application layer. So for example, this is FileZilla. Now the first thing that happens when I open up FileZilla is it wants to go check for updates. So to check for updates or install the newest version, I'm going to be using the HTTP or the secure HTTPS protocol, which will use SSL TLS, secure sockets layering, or transport layer security, okay? So those are also upper layer protocols that can be used by internet applications. But also, this is a program that uses the file transfer protocol, FTP. So notice that when I open up the site manager in FileZilla, I can use the FTP file transfer protocol, which is an application layer protocol, okay, layer 7 of the OSI model, or layer 4 of the TCP/IP model. We can even choose the type of encryption behavior, right? Or we can use SFTP, which is the Secure Shell File Transfer Protocol. And in this training, you're going to learn about different ports and the combination of ports and IP addresses, which are called sockets. And so if we're using FTP, we're going to use port 20 for data and port 21 for the actual connectivity and exchanging commands. And if we use SFTP, the Secure Shell FTP, we're going to be using port 22. Okay, so as you can see, I want to make sure that you understand the difference between running applications on your operating system, but then running applications and programs that use the application layer of the OSI or TCP IP model. Excellent. Module 2 is entitled Lower Layer Core Protocols and Services. In this module, we'll look at point-to-point protocol, PPP, as well as EAP, Extensible Authentication Protocol. Then we'll look at TCP/IP address resolution protocols like ARP, reverse ARP, and gratuitous ARP. This is Lesson 4, Point-to-Point Protocol, PPP. We're going to ponder the purpose of point-to-point protocol. Then we'll examine the core protocols of PPP. We'll introduce feature protocols and the very important Extensible Authentication Protocol, EAP. We'll explore the PPP frame formats, and then I'll finish up demonstrating the behavior of point-to-point protocol and EAP. Okay, in this lesson we're going to ponder the purpose of point-to-point protocol. How's that for a lot of P's? Okay, but before we look at PPP, or the point-to-point protocol, let's look at the ancestor of this protocol, which was called SLIP, Serial Line Internet Protocol. Now, I don't like to do too much with obsolete protocols, but I want to talk about this because for me, this is where I began, okay? This SLIP, by the way, was first designed to offer layer 2 connectivity for TCP/IP over a physical link where there was no layer 2 technology. In my first internet account, it was called a SLIP account. And I had, a really old PC, and it was running a really early version of Microsoft. And I had a SLIP account with my service provider, and I had to install this software program, and I had a modem. Remember those things that I had one of those, right? Those dial-up modems, 56 kilobits per second, or kilobytes, but not very fast. And as a matter of fact, my service provider, and this is true, I wanted to go actually visit my service provider. So I called them and asked them where they were located. I wanted to come by and ask them some questions. Well, lo and behold, my service provider was actually this guy who had this out of his house. He had dug up his front yard, and AT&T had put in what was called a T1 line. So they ran this cable and they buried it in his front yard, and he had his business in the garage. So when I went to visit him, he brought me through the side door into the garage, and he had all these racks of modems, and it was super loud, all these modems. He had 50 or 60 modems in there, and that was my service provider. And I would use my SLIP account, my SLIP protocol, to connect to one of those modems that he had up on the shelf to get access through AT&T to the internet. So that was my first foray into using the internet, even before the World Wide Web really started to happen. And so SLIP really filled the gap between the physical layer and the IP layer 3, okay? And it provided basic framing, and it was the predecessor of the PPP protocol that we're going to look at here in this lesson. The point-to-point protocol is really the biggie, okay? It's the ubiquitous protocol that is all different types of versions and all different types of extensions and variants of this protocol used all over the world. And so this was what we had before we started using PPP. And I actually remember transitioning from a SLIP account to a PPP account while I had that service provider, the guy working out of his garage. Now, what's interesting is SLIP was defined in an RFC. And this just goes to show you that some things can actually be defined, or there can be information about the protocol, but it can never get to the point of where it actually becomes a standard. So just because something has an RFC, a request for comment, and a number, doesn't mean it kind of gets to the full-blown standardized publication, right? SLIP never got there. Let's talk about some weaknesses of SLIP, because this will tell us why we had to have point-to-point protocol, or PPP. SLIP was simple, but it had limitations. It only supported a certain size of a maximum transmission unit, and 1006 bytes is not very big, so that wasn't very efficient. It had no error correction, it had no error detection. There were no extra control messages. It was really basic. It didn't have any header metadata, so you couldn't define information about the data that was being carried from the layer 3, the IP layer. It couldn't learn other IP addresses. You couldn't compress, and that was a problem with SLIP because it didn't support compression. Back in the day, when you had those 56K modems, that wasn't very fast. And so we would use techniques to compress the data so we could actually, send a picture or an animated GIF, or we could download that animated GIF eventually and have it show up in our browser. And there was no security. There was no way to authenticate the links, okay? And there was no way to encrypt the data. So SLIP had a lot of weaknesses, which led to why they had to develop the point-to-point protocol, PPP, which, by the way, we still use PPP and its variants all over the world today. This is one of the most important protocols that you're going to learn about in this TCP/IP series. The irony is, it's actually not a TCP/IP protocol. It really kind of functions at layer 2, or the link layer of the TCP/IP model. There's several RFCs that define point-to-point protocol. It's a popular technique for carrying IP packets or datagrams over what we call serial line connections. Now, when you hear the phrase serial line, what a serial line means is that it sends all the information in a string or a series of zeros and ones, okay? And certain things like serial connections still send things in a series of zeros and ones, right? Still used by a service provider that offers DSL, for example, over your phone line. The links of PPP are established using a protocol known as Link Control Protocol, LCP. Very important, and we'll learn more about LCP as we proceed through these lessons. And also with PPP is a family of network control protocols, and it's a family because it has to support different layer 3 protocols, okay? There's other protocols out there at layer 3 besides Internet Protocol, okay? Historically, there's been protocols known as IPX, SPX. Apple Talk had its own protocol called Apple Talk or Apple. So PPP needed to be able to support those different types of networked protocols, or what we would call routed protocols. So this family of NCPs establishes network layer links after the Link Control Protocol, LCP, has established a basic connection, okay? And so that's fundamental to how PPP works, and obviously we're going to learn way more about that as we move forward. Okay, in this lesson, we're going to examine the point-to-point protocol, PPP core protocols. But before I put that elaborate diagram up here, I just want to show you simply where PPP resides in the OSI model. So we have OSI layer 1, which is the physical layer, and then we have, of course, OSI layer 2, which is the data link layer. So between layer 1 and layer 2, this is where our network interface resides. And this is, that Ethernet port that's on your laptop, for example, or the Ethernet ports on a layer 2 switch, okay, the network interface card that's on the system board or the motherboard, that's the network interface. And it functions basically at both layer 2 and layer 1 because ultimately that network interface and the device drivers or the driver program that is associated with it eventually has to convert those frames into zeros and ones, either to send a stream of them in a serial fashion or a wide band of zeros and ones over a wireless RF, okay? So that's the network interface. Here's where point-to-point protocol comes in. Technically, it's at layer 2. And as we're going to find out, PPP is at data link layer 2, but it's kind of got a halfway point. So there's an upper layer of PPP we'll talk about, and there's a lower layer of PPP that we'll talk about. Obviously, the upper layer of PPP is going to be an expert at talking to the layer 3 of the OSI model, and the lower layer of PPP is going to be better and excellent at talking to layer 1 or the physical link, which can be a serial connection. It could be Ethernet, it could be ISDN, it could be fiber. There's all different types of physical links that we're dealing with. So that's kind of where PPP resides in the OSI model. Let's take a look now at kind of the PPP suite and all the different core protocols and kind of where they sit within the infrastructure of layer 1 and layer 2. Well, in the previous diagram, I kind of showed you how PPP, which is at the data link layer or layer 2, has an upper layer protocol and a lower layer protocol. The upper layer technically is NCP, or Network Control Protocol. That's the one that specializes in communicating with layer 3 of the OSI model. Then the lower protocol, which is the one that specializes in communicating with layer 2, is technically LCP, Link Control Protocol, which of course you can see is going to communicate with this layer 2 framing, right? So we have NCP and then LCP. That's kind of the basics of the PPP protocol. But we have other core protocols within that. So for example, if you're going to do compression, and I'm going to break these down for you a little bit later in greater detail. But if you're going to compress because it's a slow link, maybe you're in a certain country or a certain area that's using a 56K modem or maybe ISDN, you may have to compress it with the CCP protocol. If you're going to combine a couple of modems together or combine a couple of ICND channels, then that's going to give you what's called multi-link. And if you're going to do multi-link and you're going to combine channels or combine modems, you're going to use protocols like BCP to control the bandwidth. You're also going to use BAP and BACP, okay? If you're going to use any type of encryption between those 2 points in the point-to-point protocol connection, then you have the option to use a kind of older ECP, which is an encryption protocol. Technically, we don't use that anymore, but we can still use this for both sides to determine, hey, am I going to use some type of security? If they are, then we're most likely going to use an authentication protocol. The original one was called PAP, okay, which we don't really use much anymore, even though we could still use it. We could still use PAP along with extensible authentication protocol. But PAP, CHAP, which is a challenge handshake protocol, and then more likely than not nowadays, we're using the EAP, extensible authentication protocol, which has over 40 different variants out there. So it's very, very flexible. There's a similar functionality in PPP like we have in IP at layer 3. Remember, IP at layer 3 has the ICMP version 4 and ICMP version 6 protocols. We have something similar in the point-to-point protocol, and that's link quality management, okay? And then to report that information, basically all the information aggregated together, link quality reporting. So these are all core protocols of the PPP suite. I want to use this diagram to help explain some of the PPP behavior here and realize that over here we have our client, our PPP client, which we also call the initiator. And over here is our PPP server, which we'll call the responder. So this could be, your workstation at home, and then, or your small business and going through a modem, and this is the service provider, okay, the responder. And notice up here we have IP datagrams being sent, but realize that point-to-point protocol is basically protocol agnostic. So it can transport pretty much any layer 3 protocol, and through the years, down through the decades, there's been other layer 3 protocols besides Internet Protocol, and I've mentioned those. So PPP could really send any of those, not just IP, but that's what we're talking about here. So we are doing IP. So next we have the Network Control Protocol. And so this is going to be logically communicating NCP between the initiator and the responder. So this is going to be stuff like, the server is going to assign, the IP address, okay? And it uses an NCP protocol called IPCP to do that. So it doesn't use DHCP necessarily. It could, but it can also use IPCP to give out an IP address. It could also say, hey, here's the location of your DNS servers. Okay, that would be good information to know. Okay, so that exchange happens as it comes from the responder. Next, we might want to authenticate the user. Okay, so we can say, let's do some basic authentication. Let's use PAP, or let's get a little bit more advanced and use that handshake protocol. But if we really want to get happening, we can use extensible authentication protocol, which could use things like X509v3 certificates, okay? It could use other mechanisms to get more advanced authentication. So that's what happens there. After that, and by the way, the server is going to say, hey, who are you? And the client or initiator is going to say, hey, here's who I am and here's my credentials, okay? And they can be a wide variety of choices. As I mentioned earlier, there's over 40 variants of the extensible authentication protocol. Next we have the LCP, okay? And this is going to actually create that link, okay? So that's going to establish the layer 2 link, and there's also some optional negotiation that goes on here. Remember earlier I showed you some of those core protocols? So some of those optional things can happen here. So for example, this is a multi-link connection using 2 or more modems or multiple ISDN channels. I could, do some multi-link activities here at the LCP. And then of course we get down to, the layer 2 framing. So here's our layer 2 framing, and we've got a layer 2, header, and then other information, and then a trailer, okay? And so that's what's going on there. And there's a wide variety of options that happen down there. There's the HDLC serial protocol, Ethernet, which you're familiar with. We could also do frame relay, which used to be really, really popular, ISDN. If you're using fiber optics, you could use SONET. So that's all going down here. And then of course the physical layer is where the encoding mechanisms that are going to transfer the information in the frames, okay, which has everything above it all the way up to layer 7 in that frame, and it gets converted into zeros and ones and sent across the physical medium. So that's point-to-point protocol. Okay, the first feature protocols we're going to look at for PPP is what's called LQM and LQR. Realize that point-to-point protocol and TCP both have basic methods for detecting errors and finding corruption. PPP link quality monitoring, LQM, lets devices analyze the link quality very quickly. Link quality reporting, or LQR, will request that the other device on the link tracks link statistics and reports periodically. Now realize LQR, it actually aggregates, or it collects all the statistics for all the higher layer protocols. It doesn't separate those. So it's really an aggregate of statistics that it reports on a periodic basis. So for example, one of the things that it can report on is the number of frames that are sent and received. That's an example. It could also say how many octets or bytes, 8 bits, right? How many octets are sent and received in all the frames, maybe the number of errors that it detects, or the number of discarded frames. So those are all really important statistics, and PPP can do that. And if you imagine, you've got that workstation connecting to the service provider using a PPP program as you're trying to, download web pages or go and do other activities on the internet or the World Wide Web. These are very important features and activities. So an analogy is like asking a teacher to post a progress report to a web portal, or maybe send out an email message for a specific time period, like every 2 weeks or every 4 or 6 weeks, a progress report. We also have the CCP, the PPP Compression Control Protocol. This provides an optional way to compress data on PPP links to enhance the performance. Now let me just say this. Back in the day, when we used dial-up modems, or we had certain connections, for example, through your telephone company, that maybe gave you, 64 bytes or 128, those weren't really big bandwidths or pipes. So it was really important back then to be able to compress information so we could get more information over those slow connections. Like I said, in first world countries, this is not that big of a problem anymore, but there's lots of countries out there across the planet that are still have very slow connections to the internet, and so this is still something that's viable, okay? CCP defines the methods for two hosts to negotiate the compression scheme. Both sides have to support CCP to be able to configure it and have that kind of compression control. There's separate algorithms that perform compression and decompression. For example, there was a protocol called Microsoft point-to-point compression that was popular back in the day. PPP also has a protocol called ECP, which is Encryption Control Protocol. Typically, we're going to use IPsec or IP security or SSL/TLS for our encryption prior to transmission. However, ECP is an option. It's seldom used, but it's a data privacy feature that's still available as part of the PPP protocol family. You can use PPP-DES encryption protocol, DES, or you could use PPP-3-DES or triple DES. Now, triple DES is not 3 times faster than DES. What 3-DES means is that we do the DES encryption process 3 times. We go through 3 iterations. So that's what 3-DES means. Not 3 times stronger, but 3 passes of that particular algorithm. These algorithms, by the way, for ECP are published in their own RFCs. There's also multi-link protocol. Again, going back to the days of yore, to get extra bandwidth, you might combine modems, or you might combine channels with your service provider to get larger bandwidths. So a company, for example, could say, I want to combine 1 or 2 or more modems, or I might want to combine 1 or 2 or more channels, like ISDN channels, with my service provider to get higher bandwidth, okay? And that was called multi-link. So sometimes we needed two layer 1 connections or more between devices. So the multi-link protocol, MP, was optional, and it actually inserted another sublayer into PPP. And it looked something like this, where you would have 2 physical links, and then you would have 2 PPP layers, PPP1 sublayer and sublayer PPP2, and that was handled by the multi-protocol or the MP PPP protocol, okay? More important, back in the day, but again, can still be used in certain countries that are still using dial-up modems and other types of connectivity. Remember, not all countries have digital fiber running everywhere, or have high-speed internet through cable companies or their telephone companies. So these protocols are still used in many different parts of the world. There was also a couple of protocols called BAP and BACP. BAP was the bandwidth allocation protocol, and BACP is the bandwidth allocation control protocol. These protocols offer dynamic management of the multi-link protocol functionality and behavior. So BACP has a similar role as the link control protocol, the NCPs, the CCP compression, and the ECP. In other words, it has control mechanisms. So if we think of LCP, the NCPs, CCP for compression, ECP for encryption, it was all different ways to control the PPP connection. Well, BACP, or Bandwidth Allocation Control Protocol, provided that type of control in a multi-link environment where you had a couple of modems or where you had multiple ISDN channels. BAP, on the other hand, handles the requests between the communication devices. Now we have extensible authentication protocol. The word extensible is a very important word, and I want to talk about it for a second. We learned about extensibility early on when we were kids, okay? For example, when you got that first set of Legos and you realized that I had one Lego block and I could take multiple Lego blocks and I could connect them together and I could increase the functionality and I could turn those multiple Legos into a building or a helicopter or into, a truck or something. So you can add pieces as they became available, right? If I got a new set of Lego blocks, I could extend the functionality. When I was a kid, I had Hot Wheels, with those little Hot Wheels cars. And if my birthday came around or if it was the holidays and I wanted a present, I wanted more track. I wanted more Hot Wheels track. I wanted a way to do a 360 so I could send my Hot Wheels through the 360 or go around curves. I wanted to extend my basic Hot Wheels that simply just went down a hill and extend that to do loops and turns. So extensibility is a very important concept because we have all these frameworks and all these architectures that we use on the internet and in the World Wide Web, and as new technologies come around, right? New apps, okay, on your phone, new programs, new applications, ways to make things faster for your mobile device. The Internet of Things, the IoT, right? As we can take, our toaster and put it on the internet, right? Or you can take your pet feeder and you can actually put your pet feeder on the internet so that if you're out of town and you're not going to be able to come back, you can, reset the pet feeder. That type of extensible capability is extremely important. Well, this concept of being extensible happened pretty early on with the point-to-point protocol, with another protocol called EAP, Extensible Authentication Protocol. And we use this all the time, okay? As a matter of fact, there's about 40 different methods to extend the functionality through EAP. It's very, very flexible. And we use this on wireless networks and we use it on wired networks. One of the main reasons to extend the capability of PPP was to go beyond some of their simple authentication protocols like PAP and CHAP, okay? Those are kind of older, not very secure, not very flexible ways to authenticate the 2 points on the connection. It's point to point, right? You have 2 points. Well, we would use the PAP protocol and the CHAP protocol to authenticate those 2 points. Hey, are you who you say you are? Well, prove it by giving me a username and a password, okay? That makes sense. Well, EAP extends that functionality and makes it more secure, more flexible, and also gives us other ways to authenticate those points, okay? So with EAP, there'll be an initial what's called EAPOL negotiation. I'm going to show you that here in a second in a diagram. And then once you go through that initial process, we have a wide variety of choices we can use to how we're going to extend the authentication of those peers, okay? We can use a lot of different devices and mechanisms. For example, we have the EAP transport layer security. So we can say we're going to use EAP with the SSL TLS protocol, which you use on the internet all the time. If you go up to, your online banking site, or you go up to your online broker, or you're going to do maybe a gaming site or PayPal or whatever, you're using SSL TLS all the time. We might use EAP POTP with one-time passwords that are really strong, okay? We can use ICE version 2 on our IP security connection, our VPN, let's say, to our company. We can even use some methods that are kind of proprietary, like Cisco has one called EAP Fast, okay? So, like I said, there's over 40 different variants of EAP. This is the diagram I was going to talk about. So let's say you're going to use extensible authentication protocols in your enterprise, okay? Now this can be in your enterprise, and it could be over a wired network, or it could be a wireless network. So for example, let me get my little laser pointer. Notice this little authenticator here. That could be, in a wired network, a switch, okay? It was just a rack-mounted switch, like 24 ports or 48 ports that you're connecting your PC to in your company, okay? It's going to some wiring closet somewhere or a data center, or if it's a wireless network, that could be what's called a wireless access point, okay? This, by the way, could even be your wireless router in your home. You could use EAP on your home network. But what happens is, if this authenticator is compliant, okay, this particular laptop or handheld device or PC is called a supplicant. And it will most likely send an EAPOL start frame, okay, either on the wire or wireless, to this authenticator, okay? And it'll send that start frame and say, hey, you know what? I want to start the authentication process. Now, if the authenticator notices that there's something connected to it and it doesn't get an EAPOL start frame, it will go ahead and say, after a certain period of time, I'm going to request your ID. It'll say, well, I haven't heard from you, so I'm going to send a request ID frame to you so you can send me your credentials. And then maybe that one will send a response and identity frame. So ultimately, that goes to the authenticator. And then the authenticator connects to some authentication service, like the Radius service, and at that point, right there, is where those other different types of EAPs can kick in, and I can add different types of extensible authentication using certificates, using SSL TLS, using something like a protected access credential. You could even use something like a biometric or a smart card or something like that, okay? So EAP is an especially important protocol right now and going forward in the future. Okay, what I want to do here is demonstrate the general frame format of the point-to-point protocol. And by looking at this, it's going to be a really good indicator of some of the things you can look at in other protocols. And PPP being, ubiquitous all over the world, it's a good one to look at. This will also come in handy later on when you start using a tool like Wireshark to start looking at some of these different protocol datagrams and frames. So let's take a look first off here with this flag, okay? Now, the PPP flag field designates the start of the PPP frame, and it always has a decimal value of 126, or if it was hexadecimal, it would be 7E. Next, we have the address frame. This is the destination address, and remember that this is a direct point-to-point link between two hosts. So actually this field is kind of meaningless for all practical purposes. So basically all the bits are turned on. So we get, binary of 8 ones or 255, which means all stations or a broadcast, okay? The next field is control, and this field is always set to decimal 3, or as you can see, if you have 8 binary bits, the last 2 bits are turned on. Then we have 2 protocol fields, okay? And this identifies the protocol using 2 bytes, okay? So we have 2 different fields of 8 bits each. Now for data frames, this is typically the network protocol that generated the datagram. If it's either the CCP, which is compression, or ECP, which is encryption, and that's pretty unlikely in a first world country, but this field would specify if the data is being compressed with CCP or encrypted with ECP. So if the first protocol field is 00 and the second field is 21, then the protocol is IP version 4. If the first field, which is going to be even, is 00, and the second one, which is going to be odd, 57, that's going to be IP version 6. Next we have the information area, and let's go ahead and take a look at that a little bit closer. The information field is 0 or more bytes of data or control payload. If it's a normal PPP data frame, for example, this would be the network layer datagram, okay, layer 3. If it's control frames like we see here, then the control information fields will be inserted as shown. Now, as you've learned, there's a bunch of PPP control protocols that could be represented here. They could be LCPs, they could be NCPs, for example, the IPCP protocol, which is going to assign an IP address. It could be CCP for compression, ECP to set up encryption. It could be authentication with PAP or CHAP. And these protocols and associated options are specified in the code, type, and identifier frames. And we'll take a look at an example here in a second, but let's go down and finish up with padding. Padding is basically just additional dummy bytes to get you to the correct size of the PPP frame. And then we have an FCS, which is a frame check sequence. This is a checksum that gives us basic error protection during transmission. It's a lot like the FCS that you would find on an Ethernet frame. And it defaults to 16 bits as seen here, but it could also be 32 bits in size. And then we have the flag. Remember the flag at the beginning? Well, here's the flag at the end that designates the end of the PPP frame, and it always has a decimal value of 126. So here's an example if our PPP was in the information area using CHAP, okay, as a CHAP challenge and response frame. So it's still widely used. Typically it's the Microsoft variant, MS CHAP, but if you see here in the code type field, you have 4 options. It could be 1, a challenge, the number 2 would be a response, the number 3 would represent a success, and number 4 would represent a failure. And then the value is the actual challenge and response text that's used by the CHAP protocol. And then the name, finally the name field down there, is 1 or more bytes of text that identifies the device that sent the frame, kind of like a response from a Radius server, for example. One last thing, realize that the PPP protocol suite is based on the ISO or ISO High-Level Data Link Control HDLC protocol, so the PPP frame is pretty much the same. And remember, all messages sent by PPP are either control messages or data messages. What I want to demonstrate in this particular lesson is some of the most common usages of the point-to-point protocol. And the one we're going to look at here first is called PPPoE, or PPP over Ethernet. Now, using just raw PPP, typically you're not going to do that anymore. Historically, you would go and you would download some point-to-point protocol client and install it onto your operating system, or you could use some native client that came on the operating system, and then you'd be using some modem, some dial-up modem or some ISDN modem, but those are really kind of legacy solutions. PPP over Ethernet is actually one of the more common usages of this protocol because a lot of people out there go through their phone company to get the internet and the World Wide Web. So if you already have an existing landline in your home through, let's say, AT&T, which is extremely common, and I've done this in the past, you can go to AT&T or whatever your telephone company is, and you can use their service for internet. Now, when you're using that, what you're most often using is what's called asynchronous DSL or ADSL. Now, what does asynchronous mean? Well, if you look over here on the left at this end user with the PPP client software, or more specific, PPP over E client software, which, could come with Microsoft, for example. Asynchronous means that the download speed, so if they load up their browser, let's say like Mozilla Firefox or Internet Explorer, into their PC or their workstation or their laptop, downloading is going to be considerably faster than uploading. Okay, so that's why it's asynchronous. So it's faster downloads, slower uploads. And by the way, if you were to go through your cable provider, you wouldn't be using PPPoE. You'd be using something called DOCSIS, DOCSIS, and it would still most likely be asynchronous in the sense that you would get something like, I don't know, a gigabyte or whatever downloads, but you would get much slower uploads. Okay, so that's what asynchronous means. So if you look at this diagram here, your provider, most likely your phone company, is going to give you a little box, and it's a DSL modem. And then that DSL modem is going to connect through the phone line to what they call a DSLAM. And you would see a DSLAM, not the box itself, but you would see where it's located. If you drove around your town, you might see little buildings, little small buildings that are owned by phone companies like AT&T, and that's where these DSLAMs, which are just, a rack-mounted box, is inside this small little building, okay? And if you were to drive around right now, most likely you would see these little buildings typically off of a main road or a highway. And then those little buildings are connecting what we call in the back end over the AT&T network, which is using a layer 2 technology, a framing technology called ATM. And ATM is a OSI layer 2 technology. It's not packet based. It uses what's called cells, a fixed length cell. So it's not a packet switching protocol like we're learning in TCP/IP. It's kind of its own dedicated cell switching network, but it eventually gets to your ISP, your service provider like AT&T or Verizon or whoever. Okay, so that's what's going on with PPPoE from a topology standpoint. Now notice that we're using some layer 3-4 TCP/IP protocols with the client, like we might be using DHCP, and we might be using network address translation, because remember that PC over there probably has a private IP address like 192.168.0.11, and it has to be translated into something that's routable and acceptable over the global internet. And then the PPPoE behavior is going to be between your DSL modem or your ADSL modem and the service provider. And that there's actually several layers of activity going on with that PPPoE connection, and I'll show you that here in a second. And then of course at layer 2, you're connecting to your DSL modem, typically using Ethernet, but it could be a wireless, so you could be using 802.11, maybe a .11n for example, or it could be a wired Ethernet, which is called 802.3, okay? But that being said, the Ethernet aspect or the .11 wireless aspect stops at the modem, and from that point, at layer 2, the ATM, asynchronous transfer mode, takes over, okay? And it connects to what's called a DSLAM, a DSL-AM, inside that little building on the side of the highway, okay? And then that connects encrypt to the cloud of the provider's network, which is an ATM network. And at layer 1, okay, we're most likely using, Ethernet, 100 base T, we call it, or 1 gigabyte Ethernet, or maybe even 10 gigabyte Ethernet. Or again, it could be wireless. But then at the DSL modem, it's going to be using what's called ADSL at layer 1. So that's what's going on from a topology standpoint. And by the way, this is an extremely popular usage of the point-to-point protocol. It's PPPoE. Now we're going to look at this tool at the end of this training in much greater detail, but I'm looking at a tool called Wireshark. And I've actually loaded up into Wireshark what's called a PCAP file. So it's just a capture, okay? It's actually capturing a communication between, if you go back to the diagram, this DSL modem and the DSLAM, okay, that's owned by some company. So what we're seeing here is the communication between really this DSL modem and the DSLAM. And so we've got a capture of this. And what we're going to see first, if we go to step number 1 up here, and these are numbered, is you can see that the PPPoE modem is doing a broadcast, okay? It's actually sending out a frame where it's all Fs. So if you look down here, it's all hexadecimal Fs, okay? And that's what a broadcast is at layer 2, at the Ethernet layer. It's using a protocol called PPPoE discovery. So it's the PPPoE discovery protocol, kind of like the DHCP protocol that's used. And you can see the different offers, offer, the request, and then confirmation. And then now we go up to the what's called the PPP LCP layer. So you can see if we look at the kind of stack, we go from the lower layers to the upper layers. So we start at Ethernet, we go to the PPP over E session, and that goes up to the point-to-point protocol, and then that gives us our PPP link control protocol, or the LCP. And we can see all the different LCP activities here, the configuration request, the configuration acknowledgement, echo request. We've also got some basic authentication with PAP or PAP, the password authentication protocol, and we can still use that today, but typically once you go through that initial password authentication, your provider is going to provide extra security or additional authentication of your machine or your user. And if we go down here, we can see here's, for example, IPCP, and here's how that DSL modem is going to get its IP address that's public on the internet, okay? The DSL modem is going to go ahead and use DHCP, and it's going to give you an IP address from that private RFC 1918 address range. But the DSL modem on its outside interface here, it has to get an IP address that's kind of public out there on the internet, that's routable. So that's where this IPCP configuration request comes in. And you can see this is, we've got IPCP and maybe possibly IP version 6 CP, because you may be using IPv6 and IP version 4. And you can see LCP kicks in again with its final activities. So we're going to dig deeper into this Wireshark tool, but I just wanted to show you kind of the power that you have available to you. This is a free tool, by the way. You can download Wireshark, just go search for it. And you can also get a bunch of these PCAP files that are just examples or samples of different protocols that we're learning about here. You can get a PCAP file for the TCP handshake. You can get a PCAP file for Telnet and other protocols as well that are very popular. And I recommend that you do that. Now, the other thing I want to mention is that you may be using extensible authentication protocols, okay? For example, most likely in your organization, at your business, okay? You may be using EAP, extensible AP, on your wireless network, and that's very, very common to add a higher level of security. So at your company, your PC will have what's called a supplicant on it. It's the software, and that supplicant allows it to use different variants like EAP Fast, which is a Cisco proprietary type that uses PAC files or protected access credentials, Or maybe your workstation at your organization is using what's called EAP TLS or EAP Transport Layer Security. That's very popular in an enterprise organization. Let me show you that. I'm in this certificate location on this Windows 7 system. And let's say this Windows 7 system is at a company and they're using more recent and more extensible, powerful versions, extensions of PPP called extensible authentication protocols. And let's say that they're using EAP TLS in the enterprise. If that's the case, then you're going to have to put on the system a enterprise certificate, root certificate. Okay, so whatever your certificate authority is at your company, let's say it's a Windows server or it's a Linux, for example, you have to install the certificate on the system. Now I've got a bunch of other certificates, so if I want to go surf the internet, okay, so all of these certificates are here for me if I want to use my web browser and I want to use transport layer security to go up to all these different various websites, okay. And so I've got, you can see, things you've heard about on the internet like GoDaddy, okay. So I've got GoDaddy, I've got Microsoft, I've got some of the ones that are really popular like Thought and VeriSign. So I can pretty much go any SSL TLS server on the internet, okay, because I've got all of these root certificates in here. However, if I'm going to use extensible authentication protocol in my enterprise, then some administrator is going to have to go and install a certificate into this area, into the enterprise trust, okay? And so EAP TLS is one of the best options because it uses these very secure X509 v3 certificates and transport layer security, usually 1.1 or 1.2, that you use on the internet with secure servers. And there's other versions of EAP though. I mentioned EAP Fast from Cisco, which would involve installing a text file called a pack on your system instead of a certificate. But you could also use older protocols. Microsoft has one called PPTP, which is point-to-point tunneling protocol. Another one that's also popular with Microsoft is called PEEP, Protected EAP. And so those are most likely the ones that you're going to use. So I just want to kind of show you in this demonstration some of the more modern usages of the extensible and very popular and ubiquitous point-to-point protocol. Welcome to Lesson 5, which is entitled TCP/IP Address Resolution Protocols. We're going to learn about the need for address resolution. Then we'll examine the MAC address, media access control. We'll examine the TCP/IP ARP protocol. We'll look at reverse ARP, and then we'll finish up with a demonstration of MAC addressing and ARP. In this lesson, we're going to understand the need for address resolution and for different types of translation. Now, address resolution refers to the method of locating an address of a host in a network. Now, the address is resolved using a protocol in which a chunk of information is sent by a client process running on the local host to a server process running on a remote server host. Now, the information received by the server allows the sender to uniquely identify the network system for which the address was required and therefore can provide the needed address. So the address resolution procedure is completed when the client receives a response from the server, for example, the ARP server, with the necessary address information. Now, what I want to talk about real quick is why we use different types of numbers or indicators for different types of systems and for different resolution. So I want to talk about why we have kind of stopped using binary, which computers use, and sometimes even move from decimal to hexadecimal. And I want to use this example from the movie The Martian. Maybe you've seen it with Matt Damon. If you haven't, it's easy to explain. Matt Damon plays an astronaut named Mark Watney, and they're on Mars, him and his crew. And some storm rolls in, and Mark Watney, an antenna blows through the wind, it cuts into his suit, and he gets left behind. So the rest of the crew has to take the ship and blast off and get up there and connect with their other ship that's in orbit around Mars. So here's Mark Watney all by himself. So what he has to do, he has to figure out a way to communicate back with Earth. So he remembers that there's this Pathfinder probe that's several miles away that was sent to Mars years before. So he gets in his little rover and he rows on out and he digs up this Pathfinder probe, and then he brings it back to his base, and now he can communicate. Once he gets the antenna going and the batteries going, he can communicate back with NASA and JPL, or the Jet Propulsion Laboratory. But here's the problem. It has a camera on it, so he can face the camera at himself. But all he can really do is put up some signs that say yes or no. Okay? In other words, his communication that he can do back with NASA is binary. Okay? So, for example, he can hold up a sign and says something like, "Does the crew know I'm here?" Okay? Well, they can point the camera at the sign that says why, and they can say yes. Or if he asks a question and the answer is no, they point the camera at the sign that says no. But that's all they can communicate, is that binary information. And we need to be able to communicate more advanced, more complex information than just binary. Yes, no, on, off, left, right, 0, 1. You get the point, right? So what did Mark Watney think of? He came up with a brilliant idea. Let me show you. So the problem was, how could Mark Watney get more complex information sent to him or communicated to him besides just a binary yes or no? Well, he thought of ASCII. ASCII text is a code. And so what ASCII does is it assigns, first off, a decimal to all the letters of the alphabet and other control characters. Well, the problem with decimal is that's still a whole heck of a lot of numbers and letters. So he realized that there's also hexadecimal identifiers for ASCII characters. So this way they could transmit information to him, and the bottom line was they had to translate or send information to be able to actually issue commands into the computer to be able to get the computer back up so they could actually communicate, using a console, not this method anymore. But what they could do is they could simply point the camera, and so he got 16 of these on little signs, starting with 0 through F, right? The hexadecimal characters. So he had a sign for each one of those. So when they pointed the camera first at 0, and then they pointed the camera at 2, he knew that's 0, 2. 0, 2 is the start of text, okay? So we knew that we're starting the text now. Then if they pointed to the 4, and then the camera to the 1, 4, 1 is the letter A, right? So they could express characters of the alphabet and words and commands. For example, 5A, so pointing to 5, and then pointing to A is a Z. Right? And they could say, well, we could put a space in there. 2, 0, that's a space. Okay? So they were able to communicate enough to him so they could take the information and then have some commands to type into the computer. Now, why do I say this? Okay? Because we have to find ways to communicate more efficiently. This is an example of Mark Watney coming up with a great solution using the ASCII table to allow them to communicate more efficiently. But as human beings, we don't like binary. We don't really like decimal numbers. We don't even like hexadecimal. So we need to take that information that identifies certain components in the OSI stack and translate or convert those into something more user-friendly. So converting a decimal IP version 4 address into some friendly name, using the domain name service, for example. And so this name resolution is a very important function and it builds on these kind of complex systems. It's a very important function to help us as human beings be able to identify these types of components on our TCP/IP systems. Let's take a look at the MAC address, and MAC stands for Media Access Control. This is an IEEE 802 48-bit address, okay? So 48 bits is what makes up this address. Actually comes from the original Xerox Ethernet addressing scheme. That's right, Xerox early on actually had their own networking protocol, okay? It's not just a copier machine. And it's represented in hexadecimal, and it's most commonly referred to as the EUI-48 identifier. The reason why that phrase EUI-48 is important is because it's going to come back again when we look at the IP version 6 address. So IP version 6 actually can use this EUI-48 identifier to actually make up its version 6 local address. So this will come back to be important to us. A MAC or Media Access Control address is typically tied to a core connection device in your computer called a network interface card or a NIC. Now for most of us, the network interface card is going to be something that's part of the system board or the motherboard, or it's part of the laptop, okay? But we can always, if we have the capability, we can add those in. But also realize that we have these NICs on switches. So if you have a switch that has 24 ports on it or a big 48 port switch, each one of those switch ports is going to have its own MAC address assigned to it. A network interface card actually converts data into an electrical signal that can be transmitted over the network. And by the way, it's going to work along with some software known as a device driver. Every commercially viable NIC has a hardware address that's known as a MAC. Now, whereas IP addresses are linked with TCP/IP networking software stacks, a MAC address is linked to the hardware of logical or physical network adapters. Manufacturers all place a special number sequence called an organizationally unique identifier, or OUI, that identifies them as the manufacturer. The OUI is usually at the front of the address. So for example, consider the MAC address 001422012345. Well, the OUI is going to be the first half of that, 001422. Now, something that's interesting in this MAC address is that, remember, that's a hexadecimal address. There are no A's through F's in there, are there? I don't see an A, B, C, D, E, or F. And I did this on purpose, okay? There's no letters in that MAC address. However, that's still a hexadecimal address, okay? So keep that in mind. Here's an example of some of the bigger companies that were involved early on, but you can see Dell's OUI is 001422, for example. If I go to my Windows PC and I issue the command ipconfig, and we'll see this in a demonstration, by the way, so don't worry about it. I'll demonstrate this for you. But if I do an ipconfig/all, what I'm looking at is my wireless adapter. And notice that even a wireless adapter has a MAC address, okay? Very important. You can see this one has a physical address of AC, B5, 7D, and so on. And the AC, B5, 7D is actually the OUI, probably going to be Qualcomm. So down here, the Ethernet adapter, this has a physical address, and you can see that's 3065 EC 6984 AF, okay? So that's the actual network interface card on my laptop, my Acer laptop. So the one above is the wireless, for the wireless adapter on this Acer laptop, and the one below is the Ethernet adapter, which is part of this Acer laptop. Now I mentioned that a MAC address can be physical or it could be logical. So here I'm up at Amazon Web Services, and I'm going in and creating on Amazon Web Services a virtual adapter. It has a virtual IP address, and notice I've got a virtual MAC address. So this is actually part of the kind of virtual machine, the Zen XCN virtual machines that are used at Amazon Web Services. So there, they virtualize everything. And so, like I said, it can either be a physical MAC address for an Ethernet port or a switch port. It could be a MAC address for a wireless adapter in a laptop or on a cell phone. Here, it's a logical MAC address at a cloud service provider. Okay, let's look at the Address Resolution Protocol, or ARP. ARP is a protocol used by the Internet Protocol, but IP version 4 only, and it maps IP network addresses to the hardware address, or the Media Access Control MAC address used by the link or the data link protocol. ARP functions below the network layer as an interface between that layer and the link layer. An Ethernet network uses two hardware addresses to identify the source and destination of each frame sent on the Ethernet. A host sends all frames which it generates with its own hardware source link address, and then it receives all frames which match the same hardware address in the destination field of, let's say, for example, the Ethernet header, or one or more pre-selected broadcast or multicast addresses. There are 4 types of messages that can be sent by the ARP protocol. These are identified by 4 values in the operation field of the ARP message header. So these are the ARP request, the ARP reply, and rarely, but it's still officially part of the protocol, the reverse ARP request and the reverse ARP reply. We don't really use reverse ARP that much anymore. So the 2 biggies are the ARP request and the ARP reply. To reduce the number of requests, a client will typically cache resolved addresses, or the mappings of the MAC address to the IP address, for a short period of time, like 5 minutes or 10 minutes, or it can be longer. The ARP cache is a finite size, and it can fill up. For example, if there's a denial of service attack or a flood attack against a switch, for example, or a workstation or a server. So periodically, the system will flush out all of the entries in that ARP cache. And this deletes unused entries, and it frees up space in the cache, which is basically in RAM memory, and it stops the unsuccessful attempts to contact hosts, which are typically not running. Therefore, their MAC address doesn't need to be in the cache. Let's take a look at ARP in action, and let's say that we're going to be using the ICMP ping program, okay? So here's host A, and host A is going to use the ping, which is an echo request, and it's going to send an echo request to host B, and host B's back over here, okay? Both of these, of course, are running the ARP service. So host A is going to send this ping to host B at its IP address of b.b.b.b. By the way, it could be 192.168.1.100. How's that? Well, here's the problem. Host A doesn't have a IP to MAC address mapping for that IP address. So the ICMP packet is going to be stored in memory. It's going to be queued, okay? It's going to be waiting there lined up until the hardware address is resolved. And that's where step 3 comes in. ARP, the ARP protocol, the ARP service, will request the destination hardware MAC address of host B. Host B, of course, is going to send an ARP service reply back to host A, and then it can do its echo request, and now host B can respond with an ICMP echo reply. Now, this is kind of a common scenario, but let me tell you what's actually more common. Let's say that host A here is coming onto the network for the very first time, okay? Maybe it's a brand new system, or you're bringing in a laptop to some organization. Most likely, this host is going to get its configuration information using the DHCP protocol, okay? The Dynamic Host Configuration Protocol. So DHCP is going to eventually give host A a bunch of options, okay? These options might be, this is your default gateway, okay? This is the IP address of the router to get out of your network. Okay, well, let's say that's exactly one of the settings or one of the options that DHCP gives it. If this host wants to send let's maybe do a TCP IP three-way handshake with some web server out on the internet, it has to know how to get to the default gateway, okay? Well, it has the IP address of the default gateway or its router, okay? DHCP told it that. Maybe it said it's 192.168.1.1. Well, it has the IP address, but it doesn't have the MAC address of the default gateway, okay? So what is host A going to do? Host A is going to use the ARP protocol. It's going to send an ARP request to that router or that default gateway and say, hey, I know your IP address, 192.168.1.1, but I don't know your MAC address, so send me back that MAC address. And it will, and it'll be stored in host B, or host A that is, it'll be stored in its MAC or its ARP cache for a certain period of time, okay? So, a couple of examples of ARP in action. In this lesson, we're going to look at two ARP protocols or two ARP variants. First, we're going to look at reverse ARP, which actually isn't used that much. It's kind of obsolete. However, reverse ARP leads us to gratuitous ARP or GARP, which we still do use today. So let's talk about reverse ARP first. Realize that ARP and reverse ARP are entirely different operations, okay? The address resolution protocol ARP assumes that every host knows the mapping between its own hardware address, its own MAC address, and its protocol address or addresses. Remember, you can have more than one IP address associated with a single MAC address. Information collected about other hosts is then stored in a small cache known as the ARP cache, which is in your RAM memory of your system. All the hosts are equal in status, as there's no distinction between an ARP client and an ARP server. Reverse ARP, or RARP, if you can say that, on the other hand, also called inverse ARP, needs one or more server hosts to actually keep a database of mappings from hardware addresses to protocol addresses, and then it can respond to requests from clients. ARP, or reverse ARP, is now an obsolete networking protocol, and it's actually, there's other protocols that can perform these kinds of duties for us now, so we don't really use reverse ARP anymore. Gratuitous ARP, however, which kind of comes from reverse ARP, we still do this. Now, gratuitous means that an ARP request or reply that's not typically needed according to the ARP specification is used, but it can be used in some other situations. So it's not always used. GARP isn't always used, but in some scenarios, we can still use GARP. A GARP means that both a gratuitous ARP request or a gratuitous ARP reply are used. And the reason why I say not all systems use it is sometimes on the switch that your device connects to, they won't allow a gratuitous ARP on your port. So some switches and firewalls actually will block this kind of behavior. But let's find out what it is. A gratuitous ARP request is an ARP request packet where the source and destination IP address are both set to the IP address of the machine issuing the packet, and it uses a destination MAC address that is a broadcast. So a broadcast MAC address is FF. Well, you can see it's 6 sets of FF, right? That's a broadcast. Just like an IP broadcast is all the bits turned on, so it's 255.255.255.255. An IP broadcast, the MAC address broadcast is pretty much all Fs. So a gratuitous ARP reply is a reply to which no request has been made. So I'm replying without there being a request. Now, if you think about that, that could be used in some nefarious activities. For example, as an attack. Okay, so if I'm replying to something that was never requested, could I send a bunch of replies as a gratuitous ARP to a system as kind of a flood or a denial of service? You betcha, I certainly could. And that's why I said some switches and firewalls won't allow this. But here's some use cases for GARP if you're going to allow it in your network. Gratuitous ARPs are useful for detecting IP address conflicts. You can use them to update the other hosts' ARP cache, their memory tables of the ARP mappings. You can inform access switches of the MAC address of machines on specific ports if the switch allows it. It can also be an indicator of bad Ethernet cabling or a hardware problem when you see multiple gratuitous ARPs. Okay, in this demonstration, we're going to talk about MAC addresses and the ARP protocol. And let's go ahead and on this machine, which we know is Windows 7, let's do a command in the, you can run cmd.exe, and it'll bring up this command console. I'm going to run a command called ipconfig, that's one word, space, and then I'm going to do a /all. I want to see everything for the TCP IP configuration on this system. And when I go up here, I can see that the host name, of course, we can see that we've got an Ethernet adapter. Okay, so this is a standalone workstation, and it's only got one Ethernet adapter. Now these adapters, by the way, they have a MAC address assigned to them. And so you can see that this one says the physical address is 1C/CE-54-58-55. Now let's just talk about that for a second, okay? Obviously it's in hexadecimal, but it's much easier to express that. It's more user-friendly to express it in hexadecimal. Now, here's the interesting thing. This particular system that I'm working on, it has this Ethernet adapter. It's actually on the motherboard. Okay, it's actually integrated onto the system board. Now, what if I wanted to add an additional Ethernet adapter? Could I do that? Sure, I could go to the store, I could go on eBay, I could go to Amazon or whatever and buy a card, open up my box, and I've got several slots in there where I can add additional Ethernet adapters. And if I did that, whatever the vendor is, I can tell you that the first half of this MAC address is going to represent whatever particular vendor that is. Now this says the description is Broadcom Nextstream Gigabit Ethernet. However, if I were to go take 1C, C1, and DE and go do a search, and let me do that real quick. And I did a search just, on Bing, and you can see here's 1C, CE, DE, and it says this is produced by the Hewlett-Packard Company. And you know what? Lo and behold, this is an HP machine. So this first half represent the actual vendor. And by the way, if I went and bought one of these from, Best Buy or Amazon.com, and I took the first half of the hexadecimal address and stuck it in here and searched for it, it would tell me that vendor. I mean, this actually shows me a satellite of Hewlett-Packard located in Houston, Texas on Compact Center Drive. It also shows me, if I scroll down, there are more registered Ethernet addresses of this manufacturer. So if it's any of these as well, it's also going to be Hewlett-Packard. And most of the large vendors obviously have a bunch of these. And you can see show other MAC addresses of this vendor. And this is just one website among many. Now going back here, if we look at this, the second half of this, okay, which is 54F855, this is what we call the BIA, the burned in address. So theoretically, if you have an organization and you buy a bunch of HP machines, or you buy a bunch of network interface cards and you put them in the machines, this second half should be unique, okay? These are unique identifiers, or the burned in address of this network interface card. Now, can I spoof that? Okay, could I actually, learn this information and represent myself on the network as this burned in address, or this entire physical address, or MAC address, which stands for Media Access Control? Yeah, I could. I could go get an exploit kit, I could get Kali Linux, and I could load it up and run a tool called Yersinia, 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 that actually has tools that will allow me to go and spoof or masquerade as this MAC address. And if somebody gets, into your physical local area network, they can do this kind of thing if they run those tools. Now, something else I can do, if I scroll down here, and by the way, I also see other information as well, but if I scroll down here and do an ARP command, and remember, ARP is a hybrid layer 3, layer 2 protocol, but ARP is also a program, okay? So if I do ARP-A, it's going to show me what's called my ARP cache. This is a buffer in memory that actually has mappings of IP addresses to physical addresses. Now, I'm not going to see my own system's address here, okay, because that's going to show up in this IP config up here. ARP is what I collect. It's what I gather as I send frames specifically to other switches or other routers or whatever, okay? So what I can see here is I learned one of these dynamically, and this is actually what I would call my upstream gateway, or this is in my case, the wireless router that this workstation is connected to. So this is the IP address 192.168.0.1 of my what's called a default gateway, or my next hop router. It's what I go to get from this machine out of my home network and out onto the internet. And this is the physical address of that particular box, 3C 7A 8A. Okay, so I went back up to the same website and I searched for that, and I can see when I put in 3C 7A 8A that this is actually a device, which in my case is a wireless router that came from my provider, my cable company, which happens to be Suddenlink here in Texas. And you can say that you can see this device is from the Eris group in San Diego. And then of course there's the satellite picture of the Eris group, which by the way is right next to Google San Diego. Wow. And then you can see here's some other MAC addresses of Eris, which happens to be my router that I use in my home for all of my devices to get out to the internet, okay? So that's in my ARP cache, but I also have some other static entries as well. For example, this broadcast address, which is for my local network, that's going to be in there, and then other special types of addresses as well. If I go up and I look at this again, I can see that here's that default gateway I'm talking about, right? 0.1. Now, this machine, the IP address of the network adapter on this HP machine, as you come down here, happens to be 192.168.0.100 with a 0/24 CIDR subnet mask, or 255.255.255.0. So the IP address of this machine is 0.100, and of course my default gateway, or that ARIS router, is on the same network, 192.168.0, but .1. And I have other systems that are on this network, and they're using other IP addresses, but they're all on the 192.168.0/24 network. So a couple of protocols and a couple of commands you can use, and just some information so you can kind of get an idea of the IP to MAC address and ARP on your local machine. Now, remember, other devices like access switches that you might have at your company are going to have lots of ports on them. They're going to have lots of Ethernet adapters, lots of switch ports. They could be 24, they could be 48. Let's take a look at that, for example. So here's what we would call a layer 2 switch, and you can see we issued the command show, or sh, MAC-address-table. Now this is also on like a Cisco switch. If you've heard of Cisco, this is actually also called a CAM table because it's called content addressable memory. So this information is stored in RAM volatile memory on the switch, okay? Now, because it says it's dynamic, right? So if I shut this switch down, I'd have to relearn all of these. But you can see that all of these different MAC addresses have been learned dynamically, and they are mapped to fast Ethernet interfaces on this switch, okay? Number 1, number 10, number 16, number 15, and they were learned dynamically. So as hosts, connect to this switch and send frames to the switch, often using the ARP protocol. They get stored in this MAC address table. So the next time that the hosts that connect to this switch want to communicate and find that host, it's already in the table, and the switch can basically bridge this from one port to another very, very quickly, okay? And like I said, this could be a 48 port switch, and I could have tons of different entries in here. Now I'm noticing the MAC address on this one. The first half of this MAC address, if we notice it, and it's a different representation, okay? So on my Windows machine, it would have been 00:60:2F:, you get the idea? Notice how this Cisco switch represents it differently, okay? 0060.2FCC.9102. But the first half of this MAC address, which is the vendor portion, is 00:60:2F. The BIA, the burned-in address, which should be unique, is CC9102. If I go back to my website and I put in 00:60:2F, the vendor address, lo and behold, I wasn't lying to you, it's a Cisco switch, and it says Cisco Systems. And by the way, Cisco has a ton of their own registered Ethernet or MAC addresses, okay? And a lot of them begin with 00. Why did they get 00? Well, Cisco Systems was one of the first companies to actually purchase and introduce the access layer switch, the layer 2 switch, to the public. And of course, down here you can see a satellite of the Cisco Systems building right there on Guadalupe River Trail in San Jose, California. All right. Module 3 is all about the Internet Protocol. So first off, we'll look at several lessons on IP version 4, and then we'll look at several lessons covering IP version 6, or IP Next Generation. In Lesson 6, we're going to look exclusively at Internet Protocol IP version 4. We'll review some IP concepts and versions. We'll understand the IP version 4 addressing concepts. We'll work with classful addressing. We'll explore IP subnetting. We'll look at the importance of CIDR, classless interdomain routing. We'll examine practical addressing at Amazon Web Services, and then we'll finish up examining the characteristics of the IP datagram. The Internet Protocol, or IP, is the core protocol of the TCP/IP suite, and it's also the key protocol of the network or internetwork layer, which would be layer 3. IP's main purpose is to provide internetwork datagram delivery. Remember, the protocol data unit at layer 3 is officially called the datagram or the packet. Okay? At layer 4, we call it the segment. At layer 2, we call it the frame. But the datagram delivery is basically on behalf of layer 4 protocols like TCP and UDP. IP often uses layer 3 devices like routers more often, but they can also use multi-layer switches, and multi-layer switches are switches that operate at layer 2, layer 3, and often layer 4. That's why we call them multi-layer, again, having to do with the OSI model. But also other devices like load balancers and firewall appliances, as well as even intrusion prevention system sensors. All of those devices can forward IP datagrams or packets. Some of the key characteristics of IP is that it provides universal addressing, okay? So it defines an addressing mechanism. The IP version 4 uses a 32-bit address. IP version 6 uses a 128-bit address. IP version 4 represents those 32 bits in decimal numbers. IP version 6 represents those 128 bits in hexadecimal numbers. It's also protocol independent, so IP works with both Ethernet, wired Ethernet, and the 802.11 wireless family. It also provides connectionless delivery. So for example, TCP at layer 4 is a connection-oriented protocol that sets up ports or sockets. However, with IP, there is no handshake setup before you transmit to the remote host. It's also an unreliable delivery, so there's no tracking of the datagrams. We rely on other mechanisms to do that for us. So some of the main protocol functions is, of course, providing the IPv4 and IPv6 addressing scheme, performing data encapsulation, and that is really in the form of the IP header, right? It provides formatting. It provides packaging of the upper layer information from layer 4 through layer 7. It provides fragmentation and fragment reassembly. And what does that mean? Well, sometimes when you go from one network to another, the maximum transmission unit of one network may be larger than the other network. If that's the case, if you're going from a network with a larger MTU, then you have to fragment or break up those packets or those datagrams into smaller datagrams for the other network. So one of the services at layer 3, or IP, is to provide for that fragmentation and reassembly on those layer 3 devices. It also does routing and internet delivery. So we get some help from the ICMP protocol. We get some control messages. We have some query messages. We also have dynamic routing protocols like RIP, OSPF, and BGP, to name a few. The main functions of IP were planned and designed well before the protocol suite was defined. The original transmission control program was actually divided into Transmission Control Protocol, TCP, and Internet Protocol, IP. And it was because of that man, John Postel, the late John Postel, is where they actually did that. There were 3 previous versions of the original transmission control program, by the way. So when they split it up, IP was actually called version 4. So there was never an IP version 1, 2, or 3. Interesting. Now there was an IP version 5, but it doesn't really exist anymore. It was intentionally skipped basically to avoid confusion. Version 5 related to an experimental TCP/IP protocol called the Internet Stream Protocol version 2, which was originally defined in RFC 1190. So basically, the protocol never progressed, so we just bypassed it and skipped from IP version 4 to IP version 6. IP version 6 was intended to replace the widely used IP version 4 that's considered the backbone of the modern internet. IPv6 is often referred to as the next generation internet because of its expanded capabilities and its growth through recent large-scale deployments. IPv6 will be covered in greater detail in a later lesson in this course. Let's look at IP version 4 addressing concepts. When representing hosts on an internetwork, it's very important that coordinated, non-duplicate addresses are being used. Every device on the internet will have at least one IP address. As a matter of fact, when you're using IP version 6, the next generation, it's very likely that your system or your network interface will have multiple IP version 6 addresses. For most end users, the addressing is actually shielded or facilitated by the domain naming system. So the friendly names or the fully qualified domain name is what you're referencing in practice. Groups of assigned or allocated IP addresses are given to users and organizations, and various service providers like Internet Service Providers, ISPs. There's also ISP telephony providers like ITSPs. There's cloud service providers like CSPs, maybe like Amazon Web Services. They typically provide the addresses and routing services on the internet. The most common is the dotted quad or the dotted decimal IP version 4 address. Let's take a look at an example here. Well, first off, here's an example of a dotted quad representation, okay? You've got 4 octets or 4 groups of 8 bits. So let's say here's 1.2.3.4. How is that represented in binary? Well, you can see here's our first octet, right? Well, the 1 bit is turned on there, okay? So all these other bits are turned off. The 1 bit is turned on. There's our 1. Over here, the 2 bit is turned on. All the other bits are turned off. There's our 2, so 1.2. Over here, we're turning on the 1 bit and the 2 bit, and that gives us .3, right? And then finally, back here, we're turning off the 1 bit, we're turning off the 2 bit, and we're turning on the 4 bit, and that is our 4, okay? So if we take a look at this other example of 10.0.0.255, well, let's take a look at that. Over here, we're turning on the 2 bit, and we're turning on the 8 bit. That gives us 10. No bits are turned on in this octet or this quad, so that's 0. No bits are turned on there. That's 0. Check this out. In the 4th octet, all the bits are turned on, okay? Turn on all the bits. If you added all these up, 128 plus 64 and so on, you'll get 255, okay? Now here's an interesting thing about this particular address. Let's say that this would be, we're going to call it 10.0.0.255/24. That's a CIDR representation. What that means is the first 24 bits or the first 3 octets represent the network. Now we can also use a subnet mask to say 255.255.255 masks out the first 3 octets. And then the last octet is for the host. So notice that if we did that, where the first 3 octets were the network, 10.0.0 network, this 255 is actually called a directed broadcast. That means let's send this IP datagram to every host, every single host on the 10.0.0 network, okay? Now that's interesting. What's more interesting is this kind of directed broadcast on most routers, like a Juniper router or a Cisco router or a 3Com or whatever you're using. Most routers won't allow that type of address because it's part of an exploit. Now what it will allow as a broadcast is this bottom one down here, okay? So all the bits turned on gives us 255.255.255.255. That is an IP version 4 broadcast. Goes everywhere. That one is allowed, okay? And there are lots of examples of when IP applications need to send out a broadcast, okay, to all of the hosts in a particular broadcast domain, or we also call it a VLAN, a virtual LAN. So there's some examples of IP version 4 addresses. IP version 4 has a possible 4,294,967,296 possible addresses in its space, okay? Most of the space is for unicast addressing. I'm sending it to one host with an IP address. There are some that are reserved for multicasting, and that's to send it to a group of hosts in a particular domain. We also have public addresses that are routable out on the internet that are legal, and we also have private addresses that you use internally. Those are defined in RFC number 1918. When originally defined, okay, early on, every address had a network portion and it had a host portion. And it was grouped into one of 5 classes. So we had, Class A, Class B, Class C, and then we had the multicast were in D, and then experimental were in E. In this lesson, I want to talk about the classful addressing that we had historically. Now, the good news is we've kind of moved away from this system, but I do want to teach it to you just so you know, because it still may come up in some environments. Now, remember that our IP address is 32 bits, so it's made up of 4 groups of 8 or 4 octets. So you can see we have the first octet, the second, third, and fourth octet. So when they designed this IP version 4 addressing scheme, remember early on, they actually weren't thinking about this being on the internet and the World Wide Web and YouTube videos of your cat playing the piano. That was not in their mind thought at all. This was a network for universities, for research, for companies, and for government organizations. They did not imagine, some of the viral videos, right? So they actually came up with a classful scheme. And that classful scheme started to break down as soon as the World Wide Web and the Netscape Navigator hit, okay? But our Class A address basically assigned the first octet, the first 8 bits, for the network portion, and then the next 3 octets were for the host portion. Okay, that was Class A. Class B took the first 2 octets and said, this represents the network, and these last 16, those are the hosts. So 2 to the 16th power networks, 2 to the 16th power host. The Class C said the first 1, 2, 3 octets are for the network, and the 4th are for the hosts, okay? So what did that give us? Well, that said in the first octet, the decimal number could be either between 0 and 127. In the second octet, or the Class B, the first octet would be a number of 128 through 191. So the ones that got Class A were some of those early organizations and big companies. Like I think 3M, the company 3M, they actually got a Class A. Microsoft came along later, they got Class Bs, okay? Class Cs are what the average people got. So the Class C, if it started with a 192 through a 223, that was basically a Class C network. Now, they stopped at 223 And we know that 2 to the 8th power actually equals 256. So there's something missing between 223 and 256, and that is true. There was also a class D and a class E. I'm not really going to get into that. The class D address, which starts at 224, these are very important, okay? And these are what we call multicast address, okay? That was the multicast address range. And then E was experimental, okay? But really, for the public, all we really cared about is that. So if you got a class A address, you had 128 networks, and each network had a possible 16,777,214 hosts per class A network. If you got a class B address, that gave you up to 16,384 networks, and there's a reason why it's not 65,000. Don't worry about it. But you got 16,000 plus networks, and each network could have 65,534 hosts per network. If you got class C, well, there were a bunch. There were over 2 million class C networks, and each class C network, again, you only had 1 octet for the hosts, so that 1 octet, 2 to the 8th power, meant you only have 254 hosts. Now, let's talk about the 254 just for a second. How come if I have a class C, let's say I have a class C of 192.168.1, that's my network, okay? So that's the first 3 octets. If I have 192.168.1, which is class C, how come I only have 254 hosts? Here's why. The 0, that's the actual network you're on. So I can't give that to a host, right? 255, because remember it's 0 through 255. 0 through 255 gives us the 256, right? I can't use 255 because that's what we call a directed broadcast. So if you send out this in an IP packet, it's going to go to every host or every node on the 192.168.1 network. So we can't use 0, which is the network itself, and we can't use 255, that's the broadcast address, so all we can use is 1 through 254. So that's why we only have 254. And by the way, that kind of principle, it applies regardless. But this class C, remember in the 90s, they already started realizing, you know, because of the World Wide Web, they started realizing, yeesh, this is not going to work in the long run. And that's why IP version 6 started to come along. And we ran out of the class Bs. They started going to these companies like Microsoft and saying, hey, you're not even using anywhere near your class B space. Can you give them back? So they started going to these early companies going, hey, can you give back some of your class A addresses? Can you give back some of your class Bs? And then by the time 2014 came around, they had pretty much used up all of the public usable IP version 4 addresses. Now, there is a set of addresses that's part of RFC 1918. And those are the private IP addresses, and we still use those. Okay, we use those internally, and then we use network address translation to translate to some public address. Let me show you the private address ranges that are used today. Early on, they decided to reserve some of those addresses from the Class A and Class B and Class C space for private addressing. They could be used internally behind a edge or a customer edge router. They wouldn't be legal on the internet, but you could use them internally. You could use them in your local area network or whatever, but they would be blocked by a service provider, or even your own edge router may block some of these. But we still use these today. If you're using IP version 4, internally and you're using network address translation or port address translation, even at your own home, behind your wireless router or whatever, you're most likely using something from this 192.168 space. So they reserved in RFC 1918 a set of addresses from the Class A a set from the class B, and a set from the class C. So you could use 10.0.0.0 through 10.255.255.255. You could use that, and that gave you 8 subnet bits, 24 host bits, and the mask was /8, otherwise known as 255.0.0.0. Okay. Then we had Class B. And Class B, and let me just say this, a lot of organizations use the 10 network. They'll use 10.10/16. It's a very common thing to do. B, 172.16 through 172.31.255.255. Gave them 12 subnet bits, or 12 networks, and then 20 host bits per network. And the mask there is a /20, and that's basically 255.240.0.0. Okay, so A, B. And then the Class C space, this is the one you see a lot on home routers like your Netgear or your Linksys, those kind of routers you buy at online or at Best Buy or whatever. They're going to give you something between 192.168.0.1, usually .0 or .1, through 192.168.255.255, okay? And that is going to be 16 subnet bits, 16 host bits, and the mask by default is /16, or 255.255.0.0. But often with this, we'll use a 32-bit, we'll use a 24-bit mask. So it'll be 255.255.255.0 or /24 is very common. And again, because of CIDR, which we're going to learn about, we don't really worry too much about this whole classful system anymore. And we can also use CIDR representation, classless internet domain CIDR. We can use that with any of these private IP version 4 addresses inside our home, our small business, or our enterprise. Okay, in this demonstration, we're going to explore IP version 4 subnetting. At first, we'll kind of do it manually, and then we'll look at a subnet calculator, which is actually the way that you would do it in the real world, okay? Now, the early challenge we had involved the inconvenience of needing to allocate a new network number for each new network segment on the internet. And this also included creating new networks for a growing organization or in a merger or acquisition. The explosion of local area networks in the 1980s exacerbated the problems. So a method was needed to locally subdivide networks without affecting the Internet Core routing tables. A technique was needed for modifying the line between the network part of the address, which is the first bits, the first order bits, and the host portion, but only for site local purposes. By using subnet addressing, a company was assigned, let's say, a Class A, a Class B, or Class C network number where the remaining host bits can be subdivided into subnetworks for different departments, business units, organizational units, floors of a building, or buildings in a campus, etc., according to their design. So let's go ahead and subnet a Class B address, a classic address. Notice that of the 32 bits in a Class B address, the first bit is going to be 1, it's going to be turned on, and the second bit's going to be 0. This is always the case in a Class B address. And so with the first bit turned on in the first octet, it means our Class B address is always going to begin with 128. So if you have an octet, or 8 bits, and you turn on the first high order bit, and the remaining 7 bits are left at 0, that's going to give you 128. So a way that we would classically subnet a Class B address is to take the first 16 bits, which represents the network number. Notice that it tells us that 14 of the bits are free, because as I said, the first bit has to be 1, and the second bit has to be 0. So we could say our Class B address is 128.16. That's our network. Then what we could do, and what's classically done, is to take the next octet, or the third 8 bits, and use those 8 bits for our subnet ID. And then the final 8 bits we would reserve for our hosts. So for example, in this address, our network is 128.16, our subnet is .1, and it's host 15 on the .1 subnet. So notice we have our customer edge router, and that's our default gateway. So we have our host at the bottom on the 128.16.1 network, and it's host number 15. And over on the right-hand side, we have our second subnetwork, which is 128.16.2. And of course, we have up to 255 subnetworks. And that's host 23 on the .2 network. And then typically what would happen is on the .1 network on the left, our default gateway would be the first available address in that subnetwork. So our customer edge router or default gateway would have the address on this network of 128.16.1.1, and over there on the other interface for the .2 network, the default gateway would be 128.16.2.1. Now the subnet mask is a bit assignment that's used by hosts and routers to partition the network portion of the address from the host portion of the address. It's where the network ends and the host begins. And they're the same length as the corresponding address. So the subnet mask for the IP version 4 address is 32 bits, and the subnet mask for the IPv6 address is 128 bits. The subnet mask can be assigned manually, or more often it's assigned dynamically as an option in the DHCP protocol header. The subnet mask is formatted by starting from the left with some numbers of 1 bits turned on, followed by the rest of available bits as zeros. Today, a subnet mask is typically represented as a shorthand prefix length using a /, as in CIDR representation. The subnet mask uses the bitwise AND operation. Let's see how the subnet mask works with this address of 128.16.1.15, and the /24 is a CIDR representation that basically says the first 3 octets represent the network and the last octet represents the host. So for this, our mask, and this is the actual mask of a class C, is 255.255.255.0, which means the first 3 octets are going to have the bits turned on and the last bits are turned off. So when we do the ANDing process, notice that 1 and 1 gives us 1. But any other combination, 0 and 1 or 1 and 0, will give us 0. So when we apply these first 8 bits to the first octet, we're only going to turn on this bit, so that's 128. In the second octet, here's our ANDing process. We can see this bit and this bit is 1, so this is going to be the 16 bit, so there's our .16. In this third octet, we've got all of these turned on, and with the ANDing process, this 1 and this 1 gives us 1, and that's the 1 bit. The subnet mask is not masking out any of the final 8 bits, right? So that's going to go ahead and give us these 4 bits turned on, which gives us 15. So that's how the computer knows that this is the 15th host on the 128.16.1 network. And of course, as we saw earlier, that subnet mask still allows us to, take this third octet and make subnetworks out of it. Here's some subnet mask examples. Here's a dotted decimal of 255.0.0.0, and that prefix is /8, and we're masking all these first 8 bits. Here's a very common one down here. A mask of 255.255.254.0 gives us a prefix of /23, so you can see that the first 16 plus 7, the first 23 bits are turned on. This is a pretty common mask, especially when you're using CIDR, because this /23, as we're going to see in a moment, actually gives us 510 hosts. So for enterprise networks, they often use this mask on their internal LAN machines. Now you can download an IP subnet calculator, or you can just go to subnet-calculator.com, which is what I'm going to do. And notice I'm going to choose B here. I could put in an IP address, but what I want to do first, whenever you're approaching this, you need to determine how many hosts do you want to have per subnet, okay? Like I said, with an enterprise, 510, around 500 per local area network, like for a call center, would be good. If you don't want that many hosts per subnet, maybe you only want 254, well, of course, you can see that our mask is going to be 255.255.255.0. 254 per subnet. Let's say we need less. It's a small business. We only want 126. Okay? Well, that's going to shift it over, and we're going to borrow 1 bit from the 4th octet. So the mask is 255.255.255. Then the first bit of this 4th octet is turned on. That gets us 128. So you can say we've got 9 subnet bits. 8 from this 3rd octet, and then 1 bit from the 4th octet. So 512 subnetworks, 126 per subnet. Wildcard masks are an inverse mask. These are used by routers to create their access control lists. That's kind of beyond the scope of this course. So the bottom line is whatever kind of network class you get, you want to choose it and then determine how many hosts you want per subnet. Say I want to do 126. And then it'll tell you what the range is. So I can assign .1 through .126. This is a great tool to use. You can download these. You can also do CIDR representation, okay, by saying, you know, how many addresses do I want? 510, okay? And I can put in my IP address 192.168.1.0, and I can see 23 mask bits, 512 subnets, 510 maximum addresses, and it shows you the range. Okay, so these are tools that you're going to use in the real world. Either go up to this website, or you can go and download a subnet calculator. In this lesson, we're going to talk about classless interdomain routing, CIDR, and often when we say something has no class, it usually is not a compliment. But in this case, being classless is for sure a very good thing. Okay? In 1994, realize that over half of all of the Class B addresses, for example, the class of addresses that companies like Microsoft got from the IANA, they had been allocated. And the number of entries in the global routing table, which was basically one for each network, was already well beyond 65,000 entries by the mid-90s. The 32-bit IP address space was deemed inadequate to meet the future needs of the World Wide Web and increasing expansion into new territories on the planet as countries like India and China and others started getting on the internet. We quickly ran out of the IP version 4 address, and as a matter of fact, I think it was 2014 when we officially ran out of the IP version 4 address. In 1992, the IETF ROAD group, and ROAD was basically RI for routing and AD for addressing, they started tackling problems 1 and 2. So remember, problem 1 was that half of the Class B addresses were used up, and problem 2 was that the 32-bit IP address was inadequate for the growth of the World Wide Web. So they started working on that way back in 1992. They figured they could extrapolate into the future, and really once the World Wide Web became popular, and remember that's a different service on the internet, okay? It's just one of the services on the internet. But once that started to explode, specifically with the Netscape Navigator browser, then they realized they needed some new solutions. And eventually, IP version 6 would solve problem 3, which was that 32-bit address space, by expanding it to 128 bits. And by the way, 2 to the 128th power is a really huge number. So we've got plenty of IP addresses with IPv6. With RFC 4632, CIDR alleviated some of our problems, especially with the availability of Class B addresses. And it uses what's called a CIDR mask or a CIDR prefix. CIDR prefixes, which are widely used, by the way, for example, if you go and you use Amazon Web Services, networking services, you'll be using CIDR representation. It eliminates the predefined partitioning of the network part of the address and the host part of the address. So the number of network bits, or N, okay, it can be arbitrarily placed anywhere in the address without regard to those legacy classes, class A, B, C, and then D and E. For instance, the traditional class C address, which looks like 192.168.3.15, we can actually express that now as traditionally /24, right, with a subnet mask of 255.255.255.0. That's the traditional class C mask. We can use that CIDR prefix. We could do /24, or we could say 192.168.3.15/16, or we can even do /23. As a matter of fact, that subnet mask of /23 would be a subnet mask of 255.255.240.0. And that's actually a pretty common one to use in a large enterprise because it gives us it gives us a lot more hosts, 510 possible host assignments. And so with a /23 CIDR, a broadcast domain or a network of 510 hosts is really very practical for a large organization. The other thing about CIDR is we can do aggregation. So eliminating the legacy classful scheme makes it easier for us to allocate blocks of addresses, blocks of contiguous addresses to enterprises. It also makes it easier for service providers to give out contiguous blocks to their customers. Remember, the size of the internet routing table began to reduce dramatically once we brought in CIDR and CIDR aggregation. It also reduced the opportunity for configuration errors and other local area network issues that adversely affected the upstream routers in our topologies. Here's an example of some of the special use IP version 4 addresses represented in CIDR as opposed to with a subnet mask. So here we can see, private networks, so the RFC 1918, private network space of 10.0.0.0, that can be represented with 10.0.0.0/8, okay? If you have a Microsoft machine, all right, and suddenly that Microsoft machine can no longer get access to its enterprise network or Active Directory, for example, it may be given a temporary address from the APIPA or a PIPA address space. It may look like 169.254.something/16, okay? So that's a way to represent with the CIDR/16 the APIPA network. We can also see how our RFC 1918 networks represented with our /12 and /16. IP version 4 multicast, which used to be class D, that's from the 224.0.0.0/4 CIDR representation. One thing about multicast addresses I want to mention to you right off the bat is that a multicast address will never be the source address of a IP datagram or an IP packet. As a matter of fact, if it were, the routers of the internet or your company's edge routers would block those IP packets. Remember, an IP multicast is going to a group of hosts. So it's always going to be in the destination field of the IP version 4 header, okay? And then finally we see, the network broadcast address. Okay, before we head up to Amazon Web Services to start looking at some IP version 4 addressing, I want to show you another site that could be very powerful for you going forward. This is Cisco's Virtual Internet Routing Lab, where you can come in here and build a simple to complex network using the iOS router, virtual router. You've also got some virtual switches and virtual firewalls here, including the adaptive security appliance. So if you can afford $199 a year and you want to kind of launch your networking career or get deeper into networking and security, then I would highly recommend Cisco's Virtual Internet Routing Lab for $199. That being said, I'm up at Amazon Web Services, and I'm going to go up here and I'm going to create a VPC. Now I'm going to get to the VPC area, Virtual Private Cloud. And a virtual private cloud is exactly what it says, okay? It's your own virtual private network. And you can create private subnets where everything in there is isolated completely from the internet, or you can have a public subnet, and then with that public subnet, you would attach what's called an elastic IP address, and that would be a public address that people could access your public subnet, okay? So I've logged in here to Amazon, and by the way, you can come up here and create your own account. You get 1 year of free tier access, and what that means is, for example, if I go to launch EC2 instances, free tier means you've got some of these instances, like here's Amazon Linux AMI or AMI, which is a Amazon machine image. So you've got some Linux, Red Hat. These are eligible for the free tier. Now what that means is, as long as you kind of spin these up and keep them private and don't run any other applications on them, or don't get into the marketplace, because they've got a big marketplace up here. You know, if you don't get into the marketplace stuff, it will be free, or it only costs you a little bit a month. But when you create an account, you're going to have to go and give them a credit card. So you have to use a email address that nobody else has used before on Amazon Web Services, and then you'll provide some credentials and you'll provide a credit card, because they have to have a way to bill you if you do generate any kind of costs up here, okay? So what I like to do is come up here, create your own virtual private cloud, your own VPC, and then just kind of delete it, okay? So I'm going to click on this Launch VPC. It gives you several options, but let's look at this VPC with a single public subnet. That's probably the best place for you to start, okay? Because it's going to tell you that your instances, your Linux instances, your Windows instances, are going to run in a private, isolated section of the AWS cloud, but they have direct access to the internet, okay? So you can actually get an IP address, and then you could, from your own home computer, for example, you could use Secure Shell to connect to that Linux instance, or you could use the RDP protocol in your Windows system to connect to a Windows instance, okay? And then there's some security features you have to set up, but by default, it'll be kind of an open network. Now, this is what I wanted to point out to you. This is what it's going to create, okay? It's going to create a /16 network, okay? So a /16 is a CIDR representation, which means you've got a /16 network, but you've got a /24 subnetwork. So basically, you're going to have 255 subnetworks, and each subnetwork will have up to 254 hosts, okay? You know, /16 is over 65,000 networks. You have a /24 subnet, so it's going to be, you know, most likely 192.168.0.0 for your /16, and then it'll be for the subnetwork, it'll be .1 network, .2 network, 168.3, 168.4, and so on. Each subnetwork has up to 254 hosts in it, because obviously the first address is the subnetwork, and the final address, .255, is the broadcast. You're creating your own virtual private cloud. Inside of that, you're creating your own public subnet. Now, these instances, okay, that you spin up, they'll be inside your public subnet. Okay, the Linux and Windows instances, you can go to the marketplace and get virtual routers and virtual firewalls and all those cool things. But there are other services, like the internet, of course, but there's also services from Amazon Web Services that are what we call kind of managed services. Like S3 is a storage, DynamoDB is a type of database service, simple notification service, simple queuing services. So these all run outside of your Amazon virtual private cloud, and you have various ways to connect your public subnet to those other services. that are outside of your VPC but still part of the Amazon Web Services network. So here's where we're saying, okay, here's our IP version 4 CIDR block. So I'm going to go ahead and do my own. I'm going to do 192.168.0.0/16. And this is going to tell me I have a total of 65,531 IP addresses. Now, this is not all the ones that are available in a /16, but in Amazon Web Services, they're going to keep some of these IP addresses for themselves, okay? So they don't actually give me 2 to the 16th power minus 2 addresses. They take a couple of them back. Now notice that I can also have a IPv6 CIDR block, okay, if I want to go ahead and do IP version 6 here, or I can say, hey, I want to have Amazon Web Services give me one. And of course, if I do that, I need to change this down here. I'll say, look, I don't want an IPv6 CIDR block. I'm going to name my VPC my first virtual private cloud VPC, and then these public subnets IP version 4, 192.168.0.0/24. And notice here, this is /24. So normally I would have 2 to the 8th power minus 2, right? So the 192.168.0.0 is the network, 0.255 is the broadcast. So normally I would have 254 addresses available, but again, Amazon Web Services keeps some of them back. And then I can say, where do I want to put these, okay? These availability zones are ways to provide high availability. I can say no preference, or I can say I want to put them in the US East. Here you can have your subnet name, and it tells you that, after you do this, you can create more subnets. You can create public subnets, you can create private subnets. And then remember earlier when I showed you that diagram, and there were those services that were outside of your virtual private cloud, like S3 and DynamoDB and those kind of cool things, the queuing service, notification service. Well, you would connect to those by clicking on this and adding an endpoint, okay? We can also say, do we want to enable DNS host names? And we'll say, yes, we do. And we'll just create the VPC. So my VPC has been created successfully, and I can now launch instances into the subnets of my VPC. And if I go down here and look at your VPCs, there's my first VPC, okay? And there's the CIDR. Notice, by the way, there's a default VPC. I created my own here, but when you create your account at Amazon.com or Amazon Web Services, you get a default VPC. And notice that they're going to give you the IP version 4 CIDR of 172.31.0.0/16. Okay, if I choose my first VPC, I can go down here and kind of get a summary of it. Okay, here's my IP version 4 CIDR. Okay, here's the CIDR blocks, right? And then we can go in now if we want to. We have the ability to attach an elastic IP, and I'm not going to do that because it's going to cost me money. But an elastic IP is when Amazon Web Services gives me a publicly routable IP address, and then that publicly routable IP address, I can access that from somewhere on the internet, or I can access it from some other place, okay? So that's the elastic IPs. And so when you come in here, you just basically come in and allocate a new address, and that's going to cost you money. But this is giving you a publicly routable, non-RFC 1918 address that you can use to expose the instances in your subnetwork.
Let's take some time now to examine the characteristics of the IP version 4 datagram. So what we see is that IP version 4 header. Remember way back when I showed you that FedEx sticker that you put on the outside of your FedEx envelope? Okay, this is the same type of thing. It's that metadata. It's that data about data. We're going to look first off here. Let me grab my pointer. I want to look at the version field, the IHL field, all the way down to the identification field. So let's focus on those 4 or 5 fields. And notice they have different lengths, okay? So service type is 8 bits, total length is 16 bits, identification is 16 bits, right? Well, let's kind of talk about those and break them down. The version field basically tells us the version of IP being used. So, it's IP version 4, the number in that 4-bit field is going to be 4. Obviously, there's a version field in IP version 6, so it would be 6 there. The next field is IHL, Internet Header Length, and that designates the length of the IP header in 32-bit words. That'll include things like options fields, which are kind of obsolete, but they're still there, and sometimes padding that has to be added. The next field is the TOS, or type of service. That was designed to carry information to give us what we call quality of service, like prioritizing the delivery of the datagram, for example. We never really use that one. Today we use something called DS, or differentiated services. TL is the total length field, and that specifies the total length of the IP datagram in bytes. Notice that the maximum length of the IP datagram is 65,535 bytes, although most of those are going to be smaller. Then we have the identification field, which is a 16-bit value that's common to whenever there's fragmentation that goes on. Fragmentation is not as common as it used to be, but it still may happen. Next, I want to look at these 3 fields, the flags and the fragment or the fragment offset and the TTL. Let's go back a couple of slides and show you that again. So we're going to look at flags, fragment offset, and then TTL, or time to live. The flags are used for fragmentation, okay? So you can either don't fragment, so if it's set to 1, that says the datagram should not be fragmented. In other words, you're going between 2 networks that have the same MTU, or maximum transmission unit. The MF is more fragments. If that's set to 0, that means the last fragment in the message, okay, or it means that it is the last fragment in the message and it's been fragmented. If you look at the next field, the fragment offset, when fragmentation does occur, this field is going to designate the offset, or the position in the overall message where the data in this fragment resides. The next field, TTL, is very important, okay? Time to live. This specifies how long the datagram is allowed to live on the network in terms of hops, or the number of routers, or basically the number of layer 3 devices that this datagram goes through. The TTL field is actually there to prevent loops, or these endless loops happening. So by decrementing that by 1, eventually it's going to get all the way down to 0, and at that point, whatever router decrements from 1 to 0, that's where the datagram or the packet's going to discard, okay? So that's kind of a loop prevention mechanism. Next, we have the protocol field, and basically this says what type of protocol from the upper layer am I carrying, okay? So for example, if the number 1 is in the protocol field, well, you're carrying ICMP information, okay? If the number 6 is in there, very common, you're carrying TCP information. If the number is 17, it's 1 1 in hexadecimal, but if it's 17, that's going to be UDP. So those are the 3 most common. 2 others that are very important is if the value is 50, that means this is an IPsec datagram, and it's being encapsulated using ESP. If it's 51, it means it's using IPsec authentication header. So the protocol field is also very important. Firewalls, for an example, can actually filter out and deny traffic based on these protocol numbers. Next, we see some other values, some other fields in here. For example, the header checksum. The checksum basically is just a mathematical process to look for corruption, okay? It's not a complex type of checksum. Next, we have the source address, okay? So it's 4 bytes or 32 bits, and that's the source IP version 4 address. Then we have next the destination address. That's the 4 byte or 32-bit IP address. So it's 4 bytes or 4 datagrams. Then we have options. By the way, the options were there to kind of add some extra functionality, but in today's modern networks, typically we don't use the IP version 4 options because they represent a way for hackers to actually do exploits on our network. So typically those are going to be disallowed. And then we also have padding, and you may have to pad it out to get to multiples of 32 or multiples of 4 bytes. Add some extra padding in there. Then of course the data, okay? That's the data that's going to be transmitted in the datagram, either an entire higher layer message, or if there's fragmentation, it could be just a fragment of the upper layer message. Welcome to Lesson 7, IP version 6. First off, we're going to understand why we needed a new IP version. Then we'll compare IP version 4 to IP version 6. We'll examine IP version 6 addressing. We'll look at IPv6 distinctives, and we'll finish up demonstrating IPv6 up at Amazon Web Services. In this short lesson, we're going to understand why we need a new version of the Internet Protocol, or IP. This version, IP version 6, was originally called IPNG, or Next Generation, kind of like Star Trek NG, Next Generation. The IPv6 address was designed to solve the problem of global IP address exhaustion. So that was really, and this was thought up way back in the 90s, that's the main reason for having a new version of IP, solving the exhaustion problem, going from a 32-bit address to a 128-bit address. And so 2 to the 128th power is a huge number. So every device on the planet could have many, many, many IPv6 addresses. It's enough to accommodate for decades and decades to come. Also, it allowed us to replace a lot of these kind of interim solutions or transition solutions that we use, like network address translation and port address translation, CIDR representation. We can even do away with even using DHCP altogether because we can use auto configuration. Now there is a DHCP version 6, but it's actually not used all that much. So we can get rid of those interim solutions altogether. Also, IPv6 had native support for IP security, or IPsec. Now what that means is for you to have a legitimate IPv6 stack or program on your system, it has to support specifically what's called authentication header and encapsulating security payload. It has to support those two protocols of IPsec, but it doesn't mean that you have to use it, okay? It just has to be in the stack and able to be initiated if necessary. Also, the IPv6 metadata, okay, the IPv6 header was simplified. There's fewer fields, and all of the fields kind of line up on a 16-byte demarcation. So that's much more efficient and much more effective for routers, for example. So the simplified header was a good thing. Also, they introduced extension headers, and that was really a replacement for the IP version 4 options, which a lot of routers and firewalls won't even allow because that's a security vector or an exploit vulnerability. So extension headers added extensibility into IP version 6. So if they come up with some new functionality, some new method or technique that they want to do on the global internet, they can just create an extension header for it, okay? And so that's a cool feature. It allowed us to use IPv6 to kind of repair some of the complex hierarchical addressing that we had to use in IP version 4 networks, okay? So it really simplified that. IPv6 has support and enhanced support for mobile IP, and that's very important because of all the different mobile devices and handheld devices and personal devices that are out there. It enhances auto configuration, and I mentioned that that's one of the things that we can use instead of using DHCP version 6. We just basically take that MAC address of that particular device and add some information to it, and that's our auto-configured address. And this really comes in handy with the Internet of Things, or you might hear it referred to as WOT, the Web of Things, okay? Everything is going to be having its own IPv6 address. So it makes this kind of plug-and-play auto-configuration of these devices as they connect to the internet, to the cloud, so they could rapidly get their IPv6 address. And it basically makes it easier for us in organizations to make changes to our IP addressing scheme or to have to renumber. In the past, if you had a very mature, elaborate IP version 4 complex hierarchical addressing for your large enterprise or your large organization, if you had to modify that or make a change to it, it really caused a lot of headaches, okay? So for example, if I had a company over here, company A, and we're using IP version 4, and we go and we buy this company, right? Or we merge, we buy company B. What if we're both using IP version 4, 10.10.0.0 as our internal addressing structure, okay? They're both using 10.10. Well, in the meantime, in a short interim period, we can use what's called bidirectional network address translation to translate between these two networks, right? So, in other words, we could say this company is going to translate to, this to 10.11, and they'll translate to 10.12, and we'll let a router translate between them. Well, eventually, this company over here that we bought or remerged, they're going to have to change their IP addressing, and that can be a huge headache. Remember, IP addresses can be stored in registry files on a Windows computer. They can be in configuration files. They can be stored in applications up at the higher layers of the OSI model. So if you change your IP addressing scheme, right, it could take a lot of time and cause a lot of problems for end users and productivity applications. So by using IP version 6, we can really simplify and take away all of those challenges when we have changes in any renumbering scheme. So IPv6, that's the future, and the more you can do on your own to learn about IPv6, the better off you're going to be moving forward. In this lesson, we're going to break down and compare IP version 4 to IP version 6. And we're going to start with IP version 4, okay? IP version 4 has a 32-bit address space, so 2 to the 32-bit power, so over 4 billion, okay? It's in dotted decimal format, like 192.168. It uses primarily DHCP for its dynamic addressing. The IP version 4 header has 20 bytes. It's a 20-byte header, and it has 13 fields. It also has a variable header length. It does have the options field, but the header options are obsolete. We don't really use them anymore because they're a security vulnerability. They're an exploit vector. And there's also a header checksum, just as kind of as a quality control mechanism. Version 4, the packet size is 576 bytes required, okay? Now it can be larger. If it is, fragmentation is optional. So that means if you go from a network with a larger maximum transmission unit to a smaller network, it can fragment and break them up, and it has a way to keep track of those fragments. And so fragmentation is done on both routers and sending hosts. Remember, IP version 4 was never designed to be secure, so we typically will add IP security to IP version 4, okay? Right there at layer 3 of the model. So IPsec is optional in IP version 4. And it has a non-equal geographical distribution. In other words, over 50% of the allocated IP version 4 addresses are in the United States. Let's go back now and talk about IP version 6, which has an address space of 2 to the 128th bit, massive, okay? We're not going to be able to represent that in a decimal. It's just too big, so we use hexadecimal. Also, to get our addresses, we can do it manually, but most often we're going to do an auto configuration called SLAC, okay? Or sometimes you can actually use DHCP version 6. Realize, however, that SLAC, or auto configuration, is the most common way to be assigned a version 6 address, especially with the Internet of Things, the IoT, with all these little devices getting on the internet. The header is a 40-byte header, and it has fewer fields than IP version 4, only has 8 fields. It's not a variable, okay? So the basic IPv6 header is fixed in length. To increase that functionality, we have what are called header extensions. So those are extensions that go beyond the fixed length IP version 6 header, so that's much more efficient, much more effective on internet routers. And there is no header checksum at all to look for some kind of errors, okay? Also, the packet size, you have to have at least 1280 bytes required for IPv6 without fragmentation. As far as fragmentation goes, it only happens on the sending hosts, okay? So this won't happen on IPv6 routers, okay, or servers. It does have native encryption and authentication built in, so IPsec is mandatory, right? Now that doesn't mean that your IPv6 implementation is going to use IPsec by default, but it has to be part of the stack, okay, to be legal, and it is available. And by the way, with version 6, there are no geographic limitations. So this is much better for the global allocation of addresses country to country all across the planet. So there you go, comparing IP version 4 to IP version 6. Okay, in the previous lesson, we compared IP version 4 to IP version 6, and we established the fact that the IPv6 address was 128 bits, okay? Well, the format of this 128-bit address is actually going to be 8 of these X's, or 8 segments. So each X is a 16-bit hexadecimal field. The leading zeros in each field are actually optional. So let's say this final field here, X, let's say the value is hexadecimal 010F. If that's the case, you can leave off the 0 and it would just be :10F. We can do that. Also, if a field contains all zeros, so let's say this field right here, the second to last segment is 0000, well, that can be written as just simply 10, okay? So as you can see, we've got some techniques here to make this address more compact, okay, and easier for humans to deal with. Successive fields of zeros, if that happens, and let's say that all 3 of these fields are 4 zeros, 4 zeros, and 4 zeros. If you have successive fields of zeros, those can be represented by a double colon, okay? Now, you can do that only one time, okay? And that makes sense, okay? The IPv6 stack knows that there's 8 segments, and so if you put a double colon in there, right, it can just say, all right, I understand that this is going to be all zeros. But if you had 2 of those, it would have no way of really understanding that address. So we can only do that once per IPv6 address for successive zeros. Remember, the use of the double colon can actually make your IPv6 address very small. Here's an example.
If I've got FF02 and then a long string of zeros, and then notice that the last one here, that's actually 0002, but we know we can leave the zeros out, right? And so if we do that, that can be expressed as FF02 double colon 2, okay? So it makes it much more user-friendly for us humans. The unspecified address, and there is an IPv6 unspecified address, in other words, I don't know, that's written as a double colon, okay? So it's basically all zeros, right? So if there's 8 segments of hexadecimal, then it's just basically going to be double colon, okay? That means all zeros, unspecified. We have different types of messaging with IPv6. We can do unicast, and this is the most common, okay? Unicast addresses are used in a one-to-one scenario, okay? Host to host. We also have multicast addresses, and this identifies a group of interfaces. So traffic is sent to multiple destinations at the same time, a multicast group. So for example, dynamic routing protocols, like the next generation of RIP and the next generation of EIGRP, the next generation of OSPF, they use multicast addresses to send updates or hello packets or advertisements to groups of other routers in their domain, okay? So an interface can belong to more than one multicast group. We also have anycast, and this is unique to IP version 6, the anycast address. We don't use these early on, we didn't use these very often, but we do use these in some things, for example, like a group encrypted transport VPN. Okay, you can look that up, get VPN. But an IPv6 anycast address is assigned to an interface on more than one node, and it's routed to the nearest interface that has that address. So anycast means send this to the nearest router or the nearest server. There is no broadcast support. So with IP version 6 uses multicasting to get the broadcast functionality, okay? We have scopes and prefixes in IP version 6. The IPv6 address scope designates the region of the network in which the address is valid. So for instance, the loopback address, which basically means my address of my host, has a scope called link local. And that means it should only be used on a directly attached network link only, okay, or a directly attached broadcast domain. And there's 3 different scopes or regions that we're concerned with, okay? There's the link scope, okay, which is basically my VLAN, if you want to think of it that way. There's a site network scope, which is typically organization by organization, business by business, okay? And then there's the global network scope, and that's, to send unicast messages, for example, globally to host on the internet. So to look at it this way, if we, drill down, here's our link local unicast address, and then we have the site, which is a unique local unique address. And by the way, this is one that would be assigned by an organization to your company or your business. And then we have the global unicast address. So an IPv6 unicast address normally uses 64 bits for the network ID. So remember, it's 128 bits expressed in hex. So normally the first 64 bits is the network ID, and then the last 64 bits is the host ID, typically, okay? The network ID, this first 16 bits, or I'm sorry, this first 64 bits, is administratively assigned, and the host ID then can be assigned manually, or it could be auto-configured with that aforementioned Slack auto-configuration, or you could use DHCP version 6. The global unicast address is the one that's routable and reachable across the internet. So as those IoT or those web of things, those WOT devices out there, those mobile devices, all with their IPv6 addresses, they can communicate with each other across the global internet. And these are designed for pervasive, generic usage. Okay, that's the official phrase of IPv6. A global unicast address is structured hierarchically to allow for address aggregation. So one of the advantages of IPv6 is it makes complex aggregation or combination of network prefixes much easier for the internet and for organizations. So this is an improvement over IP version 4. And that global unicast address is going to be identified by the fact that the 3 high-level bits are set to 001. So the way that would look would be 2000. Okay, so 2000:/3 says this is a global unicast address. So here's an example of just kind of the formatting of it, right? So if we take a look at this, this right here kind of is the demarcation point for the host, okay? That's 64 bits or 4 of those segments, right? 4 hexadecimal segments. So it's half of the address of 128 bits. And then we also can take these 16 bits, that little section right there, and that can be our subnet identifier. So an organization who's assigned this information, right, from some assigning organization out there, they get assigned this, your company, let's say Trainology.com, a domain that I own. Let's say Trainology is assigned this. Well, we can take these 16 bits here and we can create our own structure of subnetworks, okay, on department by department basis, or floor by floor, or building by building, okay? That's where that subnet ID can come in. And that's kind of the structure of the global unicast address so that hosts can find each other at different companies. And so here's an example of a unique local unicast address. And again, still got the 64 bits. And by the way, when you use auto configuration or SLAAC, S-L-A-A-C, this auto configuration, this 64 bits is actually built from the MAC address. It's the 48-bit MAC address on that system or that network interface, and then it combines a few more bits to that to make it 64 bits. And again, here's our subnet, because the subnet is also locally significant as well. So the local unicast address is a ISP independent, globally unique prefix. It has a well-known prefix to allow for easy filtering at site boundaries or your business or your organization, and it allows combining or privately interconnecting sites without creating any address conflicts. And again, this is a huge advantage over IP version 4. In this lesson, let's look at some distinctives of IP version 6, starting with the way that IPv6 allocates its addresses. And there's really 3 main ways. You can do this manually. So for example, if you continue on in your path of IT or networking or whatever you decide to do, this may be your responsibility, and you could manually assign an address to a host, like a workstation, or even, let's say, a router or some type of device like that. You can also use what's called stateful auto configuration. If you're going to use that option, you're going to use the next generation of Dynamic Host Configuration Protocol, or DHCP version 6. The most common method, however, is stateless auto configuration, or SLAAC. Okay, let's talk about SLAAC. SLAAC uses what's called neighbor discovery, and by the way, it's going to use ICMP version 6 for its neighbor discovery. And it does this to find routers and then to dynamically create IP version 6 addresses. Now you have to connect the host to a network that actually uses at least one IP version 6 capable router.
let's say like a Cisco router or a Juniper router, for example, and it'll send advertisement messages to the link. The connected IPv6 host or node can then self-configure with an IPv6 address as well as routing parameters without needing any further human intervention. And this is a huge advantage to IPv6. This is covered, by the way, in RFC 2462. The node can automatically configure its global IPv6 address by appending its interface identifier, okay, 64 bits, to the prefix, which is also 64 bits. So if you take the prefix of 64 and then its interface identifier of 64, that gets us 128 bits, right? And that's included in the router advertisement message. This is an important feature for allowing the rollout of new devices on the internet or with the IoT, Internet of Things. And you can also roll out these addresses for mobile phones, for different wireless devices, for different home appliances, for those IoT devices and networks and more. In this particular diagram, I just want to compare the IP version 4 header to the IP version 6 header. As you look at this, and let me get my handy laser here, notice that in the legend, the things that are in yellow are field names that were kept from IP version 4 to IP version 6. So for example, in IPv6, we still have a version field. It just so happens that in IPv6, it's the number 6, right? And we both have a source address and a destination address, okay? It just so happens that the source address in IP version 4 is 32 bits. In IPv6, it's 128 bits. We can also see in red fields that were not kept in IP version 6, and notice how many things we got rid of in IPv6. No more IHL field, no more identification, no more flags, no more fragment offset, because you know what? There's no more fragmentation in IP version 6. We got rid of the header checksum, and we got rid of those options. The options we got rid of, and we replaced that with this next header. So IP version 6 has what are called extension headers. And you can add these extension headers for a wide variety of functionality, and that ultimate packet can be as large as it needs to be as long as the routers can handle that large packet. Let's talk about IPv6 extension headers, which is a very important feature in IPv6. Remember, this really replaces and extends the functionality of the options field in IP version 4. IPv6 uses two distinct types of headers, regular headers and extension headers. Now, we saw the regular headers in the previous diagram. The extension headers, if there are any, are going to follow the original 8 fields. Okay, so for example, going back, it's going to follow these 8 fields, right? 1, 2, 3, 4, 5, 6, 7, 8 fields. The number of extension headers is not fixed, so the length of the extension header chain is variable. All that really matters is, do the IPv6 routers allow a large datagram or a large packet of that size? So here, if we go back and we take a look at the IPv6 header, there's a next header field. And basically, they just tell you where the next header is. And you can see you can stack these next headers on top of each other, theoretically infinitely, but there's not going to be infinite headers. We have a finite number of extension headers, but they are intrinsic to the protocol, and they add a lot of support for extra functionality. Here's some common use cases of the extension header in IP version 6. The hop-by-hop EH, and by the way, EH is just short for extension header, so I'm just going to use that. The hop-by-hop EH is used to support those big packets, those big jumbo datagrams. We call them jumbograms, okay? So we need that to help us with those big old packets or datagrams. We also have a destination EH. That's used to support IPv6 mobility features to help us with those handheld devices and mobile devices. One other major advantage of IPv6 is it's a lot better for mobile devices and handheld devices. The routing EH is used in IP version 6 mobility and in source routing. However, the routing EH, that header, has been deprecated. In other words, it's been removed because of security vulnerabilities. We also have a fragmentation EH and a mobility EH, which is critical, of course, in mobility services. The authentication EH and the encapsulating security payload EH basically tell us that, you know what, IPsec is now native to IP version 6. So in other words, for your IP version 6 protocol stack on your system to be legitimate, to be legal, it has to support IPsec. That wasn't the case with IP version 4, okay? It was optional. It's not optional in IP version 6. Now, it doesn't mean it has to be turned on and used, but it has to be part of the IPv6 protocol program on that system. And authentication EH and ESP EH are both very common extension headers. IPv6 also has a feature known as neighbor discovery. I mentioned that earlier. The ICMP version 6 protocol provides the same diagnostic services as ICMP version 4. In other words, it has error messages, it has informational messages. It extends the functionality for some of the specific IPv6 functions that don't exist in IP version 4. So for example, ICMP version 6 gives us router solicitation and advertisement. So for example, ICMP version 6 gives us router solicitation and router advertisement. It gives us neighbor solicitation and neighbor advertisement, and it can give us redirection of nodes to the best gateway or the best router. Welcome to Module 4, IP Support Protocols. In Lesson 8, we're going to look at IP support and management protocols. Then, in Lesson 9, we'll look at TCP/IP routing protocols like RIP version 2, EIGRP, OSPF, and BGP, Border Gateway Protocol. Lesson 8 is titled IP Support and Management Protocols. First, we'll get familiar with ICMP version 4. Then, we'll look at ICMP version 6. After that, we'll look at IP security or IPsec, and then we'll finish up demonstrating ICMP. Let's get familiar with ICMP, Internet Control Message Protocol. Remember, IP, Internet Protocol, is unreliable. It doesn't guarantee delivery. So ICMP is the feedback mechanism that offers feedback about network problems and network issues. IP also doesn't offer a direct method for collecting diagnostic information. ICMP actually resides somewhere between the transport layer, layer 4 of the OSI model, and the network layer 3. ICMP provides error messages and informational messages. ICMP directly affects network operations in both a positive way and a negative way. Most border routers and firewalls may block most, if not all, ICMP messages because they can actually be used in a wide variety of different attacks. However, if blocked, diagnostic tools like ping and traceroute won't work. There are a number of ICMP types and ICMP codes, but only a few of them are commonly used, especially in IP version 4. Let's talk about ping, which is actually an ICMP echo request and ICMP echo reply. The basic purpose of ping is to verify several metrics or indicators. For example, the reachability of an IP host, or the RTT, the round trip time of a packet, or is there any packet loss? The ping program uses the ICMP echo request type 8 and the ICMP echo reply type 0. We'll actually look at ping in a demonstration in this lesson. Here's some common ICMP version 4 messages. Echo reply is basically type 0, and this is a ping reply that returns data. And by the way, the E and the I, E stands for error, I stands for informational. One that's also very common is destination unreachable, which is type 3, which means I can't reach the host, I can't reach the protocol. Sometimes this is the only ICMP packet or message that will allow on an external or edge router or firewall. We've also got redirect, which says use a different gateway. We've got time exceeded, type 11, which is an error type that says, you know what, the TTL has been decremented. Or parameter problem, type 12, which is a malformed packet or header. Here's an example of a ping. I'm on a Cisco switch, and I'm going to issue the command ping 10.10.1.10. And notice that it's going to send 5 echo requests and 5 echo replies. Notice here that the first echo request and reply, there's just a dot there. You know why? Because probably this switch had to use the ARP protocol to do an address resolution between the IP address and the MAC address first. That's why the first one timed out. But then the next 4, those went through. As I said, I'll demonstrate ping coming up in a demonstration. This is a tool called traceroute, which actually uses the echo request, echo reply, and this is basically to trace the route of hops across a network to the destination. Here you can see we went across 3 hops to get to w3.pok.ibm.com. Traceroute can allow us to find areas of the network where there's congestion. It can also find out where the actual packet is being dropped. Here's an unsuccessful trace route. We're actually trying to get to testcase.boulder.ibm.com up here, and you can see that eventually, after it went past this hop and it got to 222 and so on, it actually timed out. We weren't able to get to our destination. So traceroute gives us congestion information in the terms of milliseconds, but it can also show us where a packet is being timed out or dropped. Let's dive into kind of the behavior of ICMP version 6. Now, what we have here, this is our original IPv6 header, okay, or the basic IPv6 header. Now, we do have a field right here. This is we'll put an N here and an H here. This is the next header field. So this says if you have an extension header that comes up after the basic header, this identifies what is in that extension header. So it says, well, the next header is number 58. Well, number 58 actually says this extension header is ICMP version 6. That's what the number 58 denotes. So we take this and expand it out, okay? So what we have is the ICMP version 6 type field, and then a code field, and for each different type of message, there's a bunch of different variables. So each message type has a bunch of different codes, okay? And that really kind of governs the granular behavior. Then we have a checksum to look for errors, and then down here is our actual ICMP version 6 data. Now let me kind of clear that out. So we know that in the type field, we can have different values there. Well, if we have a value of 1, Okay, now we know that ultimately these are just zeros and ones, right? But we have a value of 1 in there. That means this is an ICMP version 6, destination unreachable. That's very important, okay? If that is not a 1, but it's a 128, 128 says that's an echo request, okay? An IPv6 echo request. If it's 129, that's an IPv6 echo reply, okay? If it is 133, that is an ICMP version 6 router solicitation. So basically, this could be a host that's looking for a router to be assigned my IPv6 address, okay? So 133 is a router solicitation. 134 would be a router advertisement. So this would be sent from an IPv6 router saying, hey, here's part of your IPv6 address for auto configuration. Or 135 is a neighbor solicitation, trying to contact an IPv6 neighbor. Remember, a lot of this ICMP v6 behavior that we have is replacing the ARP protocol that we had in IP version 4. There's no more ARP in IPv6, and really all of it's done with ICMP version 6. So there we go. There's the ICMP version 6 extension header, number 58. Next, I want to diagram out here some of this neighbor discovery, which we know ARP used to do in IP version 4, but now we're going to use IP version 6 and its neighbor discovery process. So notice we have, here's host A, and down here is host B. So what host A is going to do, it's going to send out a neighbor solicitation. And that's one of those ICMP message types, okay, that we talked about earlier. So it says, hey, what is the address, and we're looking for the v6 address, what is the v6 address of host B, right? And then the neighbor can answer back and say, hey, you know what? Here's my link address, which we know is in hexadecimal. It's an IPv6 address. So this neighbor discovery process, we're determining the data link IPv6 address of neighbors. We can also use this to find neighbor routers, like here's router A and router B. Now remember that the router has to be configured to support IPv6. And so usually what these routers or these multi-layer switches do is they're what we call dual stack, okay? They're supporting IP version 4 and IP version 6 simultaneously, just in case you have hosts or nodes in your network that are still using IP version 4, right? So we can find neighbor routers, we can keep track of neighbors. Remember how I talked about IPv6 is really a great protocol for IP mobility, okay? Well, I'm drawing a picture of a static workstation here, but what if this device that's running v6 is a cell phone or an iPhone or a pad in a hospital, maybe a specialized Panasonic pad, okay? What if it's some other handheld device? What if it's some other type of Internet of Things component with an IPv6 address? Well, this also is going to help us with that discovery and keeping track of those IPv6 neighbors as they move around in this mobility solution. We can also use this to query in case we find a duplicate address. Now, duplicate addresses in an IPv6 network are much more rare than an IP version 4 network, but it could still happen. If we see duplicate addresses on a network in IPv6, it's often because someone's on our network running some type of malware exploit kit. They're spoofing some address. So on an IPv6 network, a duplicate address is usually something that's a sign of a security vulnerability or a security exploit. And then finally, this neighbor discovery and ICMP version 6 can come in handy because we can also leverage IP version 6 multicast addresses. Remember, multicasting in IPv6 takes the responsibility of broadcasting, okay? We don't have broadcast anymore in version 6. We use multicast functionality. So just a quick example of how ICMP version 6 neighbor discovery can help provide a lot of the tasks and a lot of the components that we saw in IP version 4, specifically with the address resolution protocol. In this lesson, we're going to get familiar with IPsec or IP security. Realize, by the way, that you can learn way more about this, for example, in my SSCP live lesson. That would be a great one to go to dig much deeper into security. I'm just going to brush the surface here. First, we'll look at the different services that IP security provides, or IPsec. It provides confidentiality. In other words, it's going to scramble up the clear text into ciphertext using things like AES, for example. It provides data integrity, making sure that the information, the datagrams, weren't messed with in transit. Typically, we're going to use what's called a SHA-2 HMAC for that. Then we'll have origin authentication. We can authenticate the origin of the packet by using a pre-shared key. We can also use X509v3 digital certificates like you use up on the internet when you go and you use SSL/TLS in your web browser. We also get protection against anti-replay attacks, and we can do key management with Diffie-Hellman protocols or elliptic curve Diffie-Hellman protocols. I want to recommend to you, by the way, here to look at some of these different types of security protocols, that you go up on the internet, maybe to YouTube, and look up Brit Cruise, B-R-I-T, Cruise, C-R-U-I-S-E, or you can go to Khan Academy. He has some great videos to help you learn about encryption and decryption. When you set up an IPsec between two endpoints, let's say two routers on the internet, you have to haggle over some details of the agreement. So you need to choose what data integrity mechanism you're going to use. You'll have to decide upon what origin authentication you want to use, the key management system, and the confidentiality mechanism. And then the lifetime can be either in seconds or it can be how much data is transmitted. So the lifetime of this first part of IPsec, that can be optional. Basically, the shortest lifetime is going to be used. But these other things, there has to be a match on both sides. So if two routers are going to do IPsec between them, let's say they both have to use SHA-2 for data integrity, elliptic curve DSA for origin authentication, they have to use ICE version 2 for key management, and AES for confidentiality. All four of those things have to match if they're going to have a profile that's being used between them. There's the main mode of what we call ICE, or IPsec phase 1. And there's a first exchange where there's peer negotiation and agreement. So before they can go any further, those two routers are going to make sure that everything's done in a secure channel. So the first thing they do is they set up the secure channel for subsequent communications, so that the subsequent or ongoing communications are done over a secure channel. Then they'll possibly do some key agreement. They have to generate some secret keys that they can use later on. And then the third exchange is building what's called a security association. So in this first phase, they're going to set this up and they're going to have a two-way security association between the two routers, we'll say. Here you can see an example of configuring this ICMP protocol, or ICE phase 1, on a Cisco router. Don't worry about these details, but just notice, by the way, that the haggle stuff is all being configured here, right? Here's the hash, here's the authentication, here's the group, here's the lifetime, here's the encryption. So that's the haggle. So both sides have to have a match, not the policy number, but the values. And so you can see these two policies match all the way across. Notice the lifetime, though. This router has a lifetime of 85,400, which is 1 day. That's in seconds. The other one has a lifetime in 12 hours, okay, or half a day, 43,200 seconds. Those values don't have to match, but the shorter lifetime is going to be used. If you're setting this up between two routers, the first thing you're going to do is you're going to ping the other router with the ICMP echo request, echo reply. Then, once you find a matching configuration on both sides, one router has policy 100 that matches policy 10. Once you have a match, then you'll have what's called this ICMP peering, or a security association, two ways between both routers. It's here idle, waiting to go into the next mode, and it's active. So that's a good sign. Once you have that set up, we can go to phase 2, which is basically negotiating the security parameters that we're going to use to actually protect that clear text information. And so these IPsec parameters are also referred to as transform sets, because often we're actually transforming clear text data into what's called ciphertext, okay? Or we're scrambling it up for confidentiality. And this establishes two security associations, okay? Two one-way or two unilateral security associations, for example, between those two routers. Or it could be between your Amazon Web Services service and your edge router or firewall at your company. And also, in phase 2, there'll be periodic renegotiation of this security associations just to make sure we have a secure environment. And here you can see is an IPsec configuration, or the second half. Don't worry about the details here, but just realize that these are the kind of things you can configure on a Juniper router or a Cisco router, and you can do it in the command line interface like this, or you can do this with a graphical interface. And by the way, as you proceed forward in your knowledge in information technology or networking, it's quite likely that eventually, whatever path you take, let's say Palo Alto networking or Juniper networking or Cisco networking, you'll have to learn how to do this on those devices. And of course, you'll have to learn how to verify your activities as well. So here's just an example of some show commands that we can do on a Cisco router, or some debug commands. And debug is going to give us a whole string of commands on what's happening in real time on that router or that firewall. So just a quick little overview of the IP security, which, by the way, you can use in IP version 4 or IP version 6. Okay, in this demonstration, we're going to look at the ICMP protocol, and remember that ICMP has two different categories of messages. One is the error reporting type messages, and the others are query messages. Now, we're going to be focusing on a couple of different query messages here, ping, the ping tool, and the trace route tool. But there are 5 types, major types of error reporting messages in IP version 4 that you might want to familiarize yourself with, and that is destination unreachable, which is probably the most common, and sometimes the firewall or the router at the edge of a branch office, that's often the only ICMP message it will allow back in, because that's actually a good one to find out if a destination is unreachable. A couple of others are time exceeded, source quench, parameter problem, and redirection. Now, like I said, the one that we would commonly use in the real world of those error messages is the destination unreachable. But I'm working now in my Windows environment, and I ran the command.exe, so you can do that. Just go down and go to your start menu if you're down there, or you can run a similar tool on your Linux machine. But the first thing we're going to look at is ping. And if I just put a ping in here, and on this operating system, / is going to give me a set of different options, okay? And these are flags, you can call them flags, or parameters that we can use, different options to modify the way ping works, okay? So a couple of things here. Ping-A will actually resolve the address to the host name. That's interesting. Count, ping-n, is going to modify the number of echo requests that you send. And by default, on a Microsoft system, it's going to send 4 ICMP echo requests. Other platforms, like let's say if you're on a Cisco router, by default, that's going to send 5 of those, and I'll demonstrate that here in a second. Some of these others we don't really use, and actually some of these others are actually kind of part of a possible attack. So most, if not all, devices are going to block certain types of pings. Let me show you how we would troubleshoot with this ping tool, which is really what it is. It's a troubleshooting tool. So the first thing I want to ping is, if let's say I'm having problems, I just can't get to anything, right? I open up my browser and it can't find anything. I try to get my email, I'm not getting any email. One of the first things you're going to do is you're going to ping the loopback address, and that's going to basically test your TCP IP stack. So if there's something wrong with your TCP IP stack or program on your operating system, when you do ping to the loopback address 127.0.0.1, it's going to send 4 pings to the loopback address locally, what we call this kind of the local link. It's going to send 32 bytes of data 4 times. And you can see that it took less than 1 millisecond, which is, the way it should be. But I got 4 ICMP echo replies, okay? And then you get kind of some basic statistics. And so what you're looking at, for example, if you use ping, and the time, the round trip time in milliseconds is, kind of high, 40, 50, 70 milliseconds, that means you've got some kind of congestion. You've got some kind of issue that's slowing down this traffic, okay? And one of the things I want to mention about ping is if you're setting up a VPN between your company and a branch office, both of you are going to have a VPN going where you can protect all your traffic, make sure you ping each other first to test the network connectivity. So for example, I know that my TCP IP stack is doing good. So let me scroll this down a little bit. The next thing I might want to ping, I might want to try to ping another host on my network. Let's do that even. That's even closer. So we ping ourselves, then we ping another host on our network to see maybe something's wrong with our switch, okay? So this is a laptop. It's on the same network. Destination host unreachable. Now I know why that is, okay? I'm using a wired connection on this workstation, and I'm trying to ping a wireless device on my same network, and my router will not let that go through, okay? So this could be a problem on your network, okay? And notice that finally it just timed out, okay? So this could be a problem on your network, and if this was a normal corporate network, that could be a problem. It could also be the way that the network's configured from a security standpoint, but I doubt it, okay? But I know on my network, because of the way my router works between the wired hosts and the wireless host, I know this is normal behavior. But that would be the second thing you do, somebody else on your own network, on this side of a router. I'm going to try some of these other options. Let's do the ping with a bigger count. Let's say we're going to do 8 of them this time. So it'd be -n followed by 8, and then we'll do the loopback 127.0.0.1. And so this time we're going to do 8 echo requests. Let's ping maybe Suddenlink, which is my provider, okay? So I'm going to do 173.219.226.169. That's my service provider, real fast. You can see some different times though. The second one took 30 milliseconds, but that's still super fast. So that's my service provider's basically edge. And we can also, remember, we can do a ping, question mark again, and we could do -a, which would resolve the address to host names. Let's do that one again then. So let's do ping -a, and then we'll do Suddenlink again. And it tells me right there, suddenlink.net. Okay, so it basically resolved it to 173.219.226.169.suddenlink.net. That's what I was looking for. Okay, and I could even go all the way up to Pearson, but I'm going to wait on that. Okay, I'm going to wait on Pearson. I think you've got an idea how ping works and echo request, echo reply. Let's clear this out.
And let's use another tool called traceroute, okay? Traceroute. Now, it may be on some systems, it may be traceroute. On the Microsoft system, it's traceRT, okay? And there aren't a whole lot of other options here, but you could say, what are the maximum number of hops I want to search for? Both ping, by the way, and traceroute allow you to choose a different source address. So you might want to do a different source address. Also, loose source routing is probably going to be blocked because that's actually part of certain kinds of attacks. As a matter of fact, when I showed you earlier ping-n, that count, if you were to try to ping a host on the internet with a really large count, it's going to block it because that's what we call a ping of death. That's actually an old type of attack that was used, the ping of death with a super high count. That doesn't work anymore because if not my local router, my suddenlink router or gateway would block that. Let's do a trace RT, and I'm going to go ahead and put in a DNS name. Okay, now I know the IP address of this host at Pearson, but I'm going to go ahead and put in www.pearson.com because I can also take advantage of DNS resolution, which is what's going to happen too. So now I'm tracing this route, and it actually resolves to e290.x.akamaiedge.net. And you can see the IP address is 23.67.158.74. Now I could actually have, put in that IP address. Akamai Edge, by the way, this is what we call content delivery networking. So Akamai, Amazon Web Services, Google Cloud, other cloud service providers offer these edge locations. So Amazon Web Services has like 5 edge locations in Dallas. Akamai has edge locations, and that's a way for them to get their content closer to end users. So Pearson uses Akamai to get their content on their web servers as close to their users as possible. And by the way, you can see that my trace is complete, and it has traced it all the way to the content servers at Akamai Technologies. Okay, so that's who Pearson uses. So I'm not actually going directly to a router or a gateway at Pearson in California. I'm going to one of their edge servers. Okay, what's cool about traceroute is that it actually uses ping. So it creates a UDP packet from my source to that destination, first off with a time to live, and you can, we had TTL in the ping. Let me just do that again, show you. TTL, time to live, okay? And you can adjust that. You can say, I only want to do 1 hop or 2 hops or 3 hops. So traceroute creates that UDP packet from my system with a TTL of 1. And so, it did that first. And so it basically does 1, it goes to the first hop, and then it times out, and then it goes to the next hop with a TTL of 2, and then a TTL of 3, and so it just keeps going with it, all the way up to 30. So it would go, if it was 30 routers away, it would go, up to 30 routers away. And you can see, by the way, that it's giving me round trip times in here. Some of these time out, but it keeps trying. At one point, I had 145 milliseconds at this quest.net. You can see I'm going to, Dallas 1, level 3. Level 3 is actually one of those companies that works with companies like Suddenlink to help get them their content quicker. Okay, so for example, if I wanted to, I could bypass the internet altogether and use the company Level 3 to actually use an Amazon Web Services Direct Connect solution. And they would actually, I would connect to Level 3, I would bypass the internet and use a Direct Connect link directly to Amazon Web Services and bypass the internet. And you can see, so there's several companies involved here, Quest.net, and then Akamai Technologies. So these are good tools. Inside your network, you could, do a trace route if you had a large enterprise to find out where your problems are, to find out where your congestion is, to find out where certain packets are being dropped. It's a tool that can be used inside your network and outside your network. One thing I want to mention as we finish up here about a firewall is that a firewall, unlike a router, does not decrement this time to live field. So one thing a router does, or the hop, every time it receives a packet, it's going to decrement this TTL value by 1 and then pass it on to the next router or the next hop. So there may be firewalls or firewall appliances that are in the path. I'm not seeing them because the firewall doesn't decrement the TTL. It just passes it through. So I'm doing a trace from my system up to Akamai, but there may be firewalls in the middle that are just simply passing this trace route or these pings through their device, and I'm not going to see them. All right.
Welcome to Lesson 9, TCP/IP routing protocols. First, we'll understand the difference between static routing and dynamic routing. Then, we'll examine RIP, Routing Information Protocol, RIP version 2, and RIP Next Generation for IP version 6. We'll look at Open Shortest Path First, OSPF. We'll look at EIGRP, Cisco's Enhanced Interior Gateway Routing Protocol. Then we'll examine Border Gateway Protocol, BGP, and we'll finish up demonstrating BGP in Amazon Web Services.
Okay, in this demonstration, we're going to look at static routing and dynamic routing. And let's remind ourselves that routing of packets or datagrams is a layer 3 process. Okay, if it's the OSI layer 7, it's layer 3, but it's also technically the third layer of the TCP/IP model, the networking or internet layer. So as these hosts over here on the right-hand side are going up and hitting web servers on the internet, those packets have to be routed across layer 3 devices. Now, layer 3 devices can be multi-layer switches, as we see here, a switch that operates at layer 2, 3, and 4 of the OSI model. It could be a router. It could be a firewall that does IP forwarding. There's other devices as well that might be involved. So for example, on the internet servers, the web servers, they may be using load balancers. They may be using other devices that also do IP forwarding. But the bottom line is, in a small organization, we can just use what's called static routing. So let's look at two different scenarios. Let's say in the first scenario, this switch is a multi-layer switch, or a switch that also can perform routing. Either it has a routing processor that you've added to it, or it's built into the switch. And so that multi-layer switch is going to be the default gateway that these hosts over here on the right-hand side are using to get out of this local area network. If that's the case, then that multi-layer switch or router is going to have to forward IP datagrams or packets up to the next hop, which is our edge firewall, which is a firewall that we either have at our organization, a device at the edge of our organization like an adaptive security appliance from Cisco, or it could be a device at our service provider, our internet service provider or our cloud service provider. But either way, we have to route packets. So we have to create static routes on this multi-layer switch or routers that points to the next hop. And then of course on this firewall, we need to set up static routes that point to the internet, and then a static route that also points back to this multi-layer switch or the router. So for example, let's say we're going to do that. On the firewall, it's a Cisco router firewall. And so we do the IP route command. And the next thing we're going to say is, what is our destination? What is our destination IP prefix, which would be a CIDR representation, let's say 67.77.32.11/32 or 24 or 23, whatever. And then that pipe symbol there says, or we could actually say what is the destination IP address and IP mask to our destination. Okay, so after the IP route, we want to put in what is our ultimate destination. And then we're going to say what is the next hop in this static routing configuration to that next router or firewall. And so we could say
we're going to send it out this particular interface. So the interface command says, okay, if it's destined for that IP prefix or that IP address and mask, send it out this interface, fast 00, gigabit 01, whatever. Or we could say, send it to this prefix, send it to this IP version 4 / something prefix. And that works really well for a small to medium-sized business to configure on your routers, your multi-layer switches, and your firewalls. So static routing is excellent for a small to medium-sized organization where you want to have total control over the configuration of the IP forwarding or routing of all your layer 3 devices. So that's the advantage. The disadvantage is it's not automatic, it's not automated, it's not scalable to a lot of routers or a lot of layer 3 devices. Also, it's more subject to human error because we are relying upon humans to do the right configuration. So here's an example of how you would do it on a Cisco router with IP version 4. You'd say, here's the IP route to this prefix, 192.0.2.0/24, and then the next hop is on our Ethernet port that has this IP address assigned to it. And by the way, the actual syntax that we're using isn't important for you, okay, because it can be different on all different types of devices. Just realize the basics are, I'm creating a static IP route to a particular network or a prefix, and then the next hop is either an interface or it could be an actual IP address next hop. And down here we can see we can do the same thing with an IPv6 command to send a route to this network at 2001 0DBD with a 48-bit mask. You can even do this on a Linux machine or a Windows machine. So for example, on a Microsoft machine, we're using the route add command, and we're going to say we're going to add a route to network 192.168.35.0 with a mask of 255.255.255.0 or /24. And to get there, we're going to go to 192.168.0.2, that IP address. And you can see we're adding the command down here in the middle, and then here's the entry in the routing table. Okay, so the path to this network 35.0/24 is basically to the next hop 192.168.0.2. And that's really what static routing is all about. If you're doing this in a virtual environment, like on Amazon Web Services, if I've got a couple of subnets down here, notice that I've got one subnet, which is the 10.0.0/24 network, and over here is the 10.0.1.0/24 network. What I would do is I would have a route table. So it's pretty much static routing at Amazon Web Services. And what would I put in this route table? Well, if this instance, let's say it's a Linux or a Windows instance that I spun up, if this wants to get out to the internet, it's going to go through this internet gateway. Okay? If it wants to go to, let's say, some branch office or some other VPN connection, it'll be routed through this virtual private gateway. So in this route table, you would just simply say, if this instance wants to send traffic out to the internet, I'll put an entry in there that points to this internet gateway, which could be an IP address or it could be some type of identifier, some unique identifier. And we could say, if I want to send traffic from this instance over this virtual private gateway, let's say over a VPN to another branch office or to my headquarters, well then I'm going to route the traffic in the route table over to this virtual private gateway, which could be an IP address or it could be some unique identifier. And notice that we have a route table for each one of these subnetworks. They could be the same entries or they could be different entries on a subnet by subnet basis. Now, static routing has advantages, and I mentioned those. You know, we have total administrative control over our IP forwarding. It's also going to be something we do manually, so we have responsibility for it. It's a good solution for small to medium-sized businesses, and even in some virtualized environments, it's the best solution. But dynamic routing allows us to take advantage of automated dispensing of the routing table information and other algorithms across multiple neighbors or peer routers. And so if it's a distance vector dynamic routing protocol, the distance from, one router
to another router is going to be based on hops, okay? Hops and other information like the distance between the hops with their bandwidth or the amount of delay. So the vector is basically based on hop count or other metrics that determine what is the best hop. A link state protocol actually builds what's called a link state database. So all of the routers in the link state domain are going to propagate their information, and they'll all have an identical database, a link state database, and identical routing table. So if it's distance vector, each router is responsible for sending updates of the routing table to its next neighbor or its next peer router. That's the way distance vector works. But with link state, you're building a database that all of the routers in your administrative domain are going to share. A common distance vector protocol would be RIP version 2, and we'll talk about that. Cisco has an enhanced version called EIGRP that you might use in a Cisco environment. And the most common link state protocol is OSPF, Open Shortest Path First. And so the advantages here are we get this automated, scalable propagation of our routing information. And this is excellent for medium-sized to large organizations because a lot of this is automated for us. We can also use authentication mechanisms and cryptographic hashes to make sure that all of the information sent between the routers, it has integrity. It has origin authentication, making sure it came from the correct peer because it has the right key or password, and integrity mechanisms to make sure the hello packet or the update or the advertisement wasn't modified by some man-in-the-middle attack. So dynamic routing protocols do have lots of advantages, but some organizations just do static and some organizations are going to use dynamic. On the internet, we'll use a combination of both. Some companies will just use a static route to their service provider. Even if it's Amazon Web Services, I can use a static route. But more often than not on the internet, we're going to use a protocol, which is a path vector protocol called BGP, Border Gateway Protocol, and we'll talk about that coming up later on in this set of lessons.
In this lesson, we're going to look at the dynamic routing protocol known as RIP, or Routing Information Protocol. And by the way, this was actually one of the early dynamic routing protocols, and it was very popular, especially in Microsoft environments. And in Microsoft, we used RIP version 2. And RIP version 2 is a standardized routing protocol that works in a mixed vendor routing environment. As I said, RIP is one of the easiest routing protocols to use, and it's really good for small to medium-sized networks. RIP version 2 is limited by a route metric based on the hop count. So it's the number of routers that these advertisements go through. And it's limited to 15 hops. But realize it's actually pretty rare for an enterprise to have a width of 15 hops nowadays. RIP is a distance vector protocol, so the vector basically tells us that we're using distance or the number of hops away. So the hop count metric actually chooses the path. RIP also allows you to load balance, so if you have a router configured for RIP, you could load balance across up to 4 equal cost paths by default. RIP does not account for things like bandwidth and other metrics that are used by, let's say, the OSPF protocol when making a decision. So it is a more simpler protocol. And as I mentioned, RIP was quite popular on Microsoft networks, especially with their servers that could actually perform as routers. Here we see a basic RIP configuration on a Cisco router. Notice that we basically get into a configuration mode and issue the command router RIP, and that basically turns on the RIP functionality. Remember, a router, by the way, can run multiple dynamic routing protocols. A router could also sit between two different domains that run different routing protocols, and they could advertise that information into the other domain, into each other. And so we're just saying we're going to run RIP, make sure it's version 2, and then we just issue the command network 10.0.0.0. And what that means is any interface on this router that has an IP address assigned to it in this 10.0.0.0/8 network, any interface that has an IP address in that network is going to participate in sending and receiving RIP information. Here we're looking at the routing table on a Cisco router. Notice we have various codes up here, and we have a code of R, specifically for RIP. And you can see right there is our RIP protocol. And of course we have codes for other popular dynamic routing protocols as well, like B for BGP, D for EIGRP. And you might be saying, why do we have D for EIGRP? Well, because EIGRP uses what's called the dual algorithm. So D stands for dual. There's also O for OSPF. Here we can also see further down in the routing table, we have entries and we have the code R. So we can see that this particular router learned these entries from the RIP protocol. So for example, it says, to get to network 192.168.1.0/24, I have to go through an interface Ethernet 0 with the IP address 10.1.1.1 to get to that network. Now, RIP was also modified for IP version 6, so we have what's called IPv6 RIP Next Generation. So RIP-NG, or RIP Next Generation, is defined in RFC 2080, and it's an extension of the RIP that supports IP version 6. The main differences between RIP version 2 and RIP Next Generation are, obviously, RIP-NG supports IPv6 networking. RIP-NG does support RIP version 1 updates and authentication, so it is backward compatible. RIP-NG requires specific encoding of the next hop for a set of route entries. And finally, RIP-NG sends updates on UDP port 521 using a multicast group. In this lesson, we're going to look at the Open Shortest Path First protocol, or Dynamic Routing Protocol, OSPF. But before we do that, I want to talk about a concept known as administrative distance. And this is used by vendors' routers to determine what is the more trustworthy routing protocol. So let's look at this from a Cisco standpoint, because Cisco is the most common network routing device in the world. So let's look at this AD value. In a corporate LAN, it's not uncommon to see multiple dynamic routing protocols and static routes configured on routers and multi-layer switches. The AD, or administrative distance, is a way to rate the trustworthiness of the source of routing information in order to choose the best path. Some vendors, like Cisco, use the AD to rank the reliability of a routing protocol. So in other words, if there are multiple entries in the routing table, it's going to choose, if it has the option, the routing protocol entry with the best AD. Now when we say best AD, we actually mean the lowest number, okay? So notice that the connected interface has an AD of 0. Well, that means it's the most trustworthy, okay? Nothing gets lower than 0. It's like a golf score, okay? If it's directly connected, that's some pretty reliable information. If you, as a network administrator, have configured a static route that says, hey, here's the prefix to get to that particular network, that's going to have a value of 1. Well, that's pretty trustworthy as well, okay? Directly connected, trustworthy. Static route, trustworthy. Then we start looking at these dynamic routing protocols. External BGP is used out on the internet with your service providers and your IT service providers and your cloud service providers. So Cisco says
If it's an external BGP route, that's pretty trustworthy, okay? Notice that if we go to the top, the least trustworthy is something that's unreachable, okay? That's the highest value possible, 255. Also, older protocols like, or internal BGP, which isn't used very often. So the higher the number, the least trustworthy. Notice, however, these two right here. If it's a Cisco router and it has an entry for a path to a network or a prefix, it's going to have a value of 90. If it also has an entry for OSPF, okay, to the same network, the Cisco router will choose the EIGRP route over OSPF. Part of the reason is EIGRP started out as a proprietary Cisco protocol. So a Cisco router is going to prefer EIGRP pretty much over OSPF or ISIS or RIP if it has the opportunity, okay? Because obviously it's proprietary. So this is a table that's used, especially by Cisco routers, when there's multiple entries in a routing table to the same location, but given to it or provided by different or more than one routing protocol. Now let's talk about open shortest path first. Now this particular protocol, by the way, is based on what's called the Dijkstra algorithm. And Dijkstra is D-I-J-S-T-R-A, okay, Dijkstra. And there may be a K in there, actually, D-I-J-K. It's the gentleman's name, okay, the one who created this particular method for finding the shortest path, okay? It's one of the most commonly used internal gateway protocols in IP networking. Now, routing protocols must detect failures as soon as possible and then quickly determine another path across the network. Remember, this is a packet switching technology. So we have multiple paths and we're going to use the shortest path first, but if one of those nodes goes down, we want to be able to quickly determine another path through the network. Packet switching, not circuit switching, packet switching. OSPF is a link state, so it knows, it has a database kind of topology of the states of all of the links of all the routers in its domain. And it offers fast convergence and scalability for multi-vendor environments. So OSPF, bottom line, is way better than RIP or RIP version 2. An OSPF router achieves neighbor adjacency, or it establishes a peering, okay, or a neighborship by exchanging hello packets, okay? And a hello packet is one of those protocols at the layer 3, the network or internetwork layer, okay? And it exchanges hello packets with other routers. Now, once a router does this with hello packets, the neighbor is put into the neighbor database. After a neighbor relationship is established, all of the routers in the OSPF area or domain will synchronize their topology, okay? So that's the link state database by reliably exchanging what are called advertisements. So the first thing is the hello, hey, you be my neighbor, okay, like Mr. Rogers' neighborhood. Want you to be my neighbor? Okay, we're going to be neighbors. We have an adjacency. Now, let's start synchronizing our databases and exchanging advertisements so that all of the routers in the OSPF domain have the same exact topology database. So here you can see the core functions of OSPF. They use the hello protocol to discover neighbors. Then they go through a multi-phase process to form adjacencies or neighborships with their peer routers. Then they'll use those advertisements to flood the link state database on all of the OSPF routers. Once that's accomplished, then they will compute the shortest path, okay? And that's where that Dijkstra algorithm comes in that Dijkstra invented, okay? And by the way, that algorithm, that shortest path, it's actually used for lots of other things besides
routing in a network, okay? A shortest path or a Dijkstra algorithm can be used in lots of disciplines besides networking, okay? Once we compute the shortest path, then we install these OSPF routes into the database, okay, or into the routing table on the router. And if there's a change, okay, then we go through this process again to modify with advertisements. We modify the link state database, we do a recomputation of the shortest path, and then we change the routes in the routing table accordingly. Here's an example of the OSPF design. I don't want you to get too hung up on this. If you're going to go and you're going to, delve farther into your IT career or networking, you'll learn about how routers do this type of thing. But there's one thing about OSPF we need to understand, is that every OSPF network has what's called a backbone, okay? We all need to have a backbone. But OSPF has what's called Area 0, and this is the backbone. And if we think about Area 0 as our backbone, this would be, let's say, our main core routers in our enterprise, the ones that are moving those packets and forwarding them very, very quickly. Then you're going to connect these other routers to that area. These are called area border routers. So think of these as like the first floor of your building, and then the second floor of your building, or the third floor of your building. Or this could be the accounting department. This could go to the call center. This could go to the R&D department. Or if it's a campus network, okay, a campus area network, this could be building 1, building 2, building 3, okay? What about a wide area network, okay? Well, area 0 is the headquarters, okay? And this is branch office 1, branch office 2, branch office 3. See, so this is a great protocol that actually can be used in a wide variety of different types of networks. Local area networks, metropolitan area networks. For example, if it's a metropolitan, this may be Area 0 or the backbone, and this could be, J1 could be the police department. This could be the fire department. This could be city government, okay? So this OSPF can work in a local area network, a wide area network, a campus area network, a metropolitan area network. It's a very powerful and flexible dynamic routing protocol. Let's talk about the EIGRP routing protocol, which is an enhanced version of Cisco's original interior gateway routing protocol. So not used out on the internet, but used inside organizations, inside an autonomous system. And so this is actually has an RFC, so it's not totally proprietary anymore. EIGRP has an informational RFC number 7868. So it's not totally open source, an open protocol, but it's kind of somewhere in between, right? And so it's defined in 7868. We call EIGRP a hybrid routing protocol, okay? A hybrid, because it uses different aspects of different routing protocols. It is an advanced distance vector protocol. So it basically uses advanced mechanisms to figure out the distance between hops. Okay, and I'll talk about that here in a second. But the algorithm that it uses is called the dual algorithm. What that stands for doesn't matter, but when you look at EIGRP in a routing table on a router, there'll be a Cisco router specifically, there'll be a D next to the entry for any EIGRP entry or prefix, because D stands for dual, okay? So there's not, E will not be EIGRP in the routing table, okay? That's something else. It'll be dual. Now, the good thing about EIGRP is it's very efficient and it converges very quickly. It's also classless, so you don't have to use Class A, Class B, Class C, so they can support things like CIDR and something else called virtual linked subnet masking that we can use. And again, these are mechanisms that are IP version 4 mechanisms that with IP version 6, we don't have to use these anymore. But EIGRP doesn't need to use those classes with its IP version 4 addresses. Also, when an EIGRP neighbor is sending an update to its neighbor, it only sends a partial update. It just sends the information that's changed, and it's only on an as-needed basis. Other protocols like RIP and RIP version 2 will send the entire routing table on a regular basis. EIGRP doesn't work that way. It only sends the partial necessary information when it's needed, when there's a change to the topology, which, by the way, may not be very often, okay? It supports multiple protocols. So EIGRP can support IP, which is why we're here. It can support AppleTalk. It can even support the older IPX, SPX protocol that was from Novell. Novell Networks came up with their own protocol. So it's multi-protocol support. It can support those things. It supports several different kinds of metrics. So these numbers here that determine what we would call the metric between hops. This is a very simplified version, by the way. I'm keeping it simple, but the attributes or the metrics that go into determining this number 5 and this number 10 can be a combination of what we call bandwidth, delay, load, and reliability. Usually it's just bandwidth and delay, but we can use these to create very complex metrics. So this topology for EIGRP will support up to 255 hops or 255 neighbor routers, which is way more than enough for modern networks. And we have a new version of EIGRP for IP version 6, and that's called EIGRP v6. Now, one thing we see here, these routers will determine the metrics between their hops. So we can see to get from router A to router Z, okay, we can see that the best hop that has the lowest metric is from here to here to here to here, because we have 5 plus 5 plus 5 is 15. If we go that direction, if we go down to this router, we're going to go 10 to 10 to 5. Well, that's 25, okay? So this is a better path because it has a lower metric, okay? And so that's the preferred path. We call that the successor, okay? Successor in the sense that it's the successful path, okay? So the successful path of the successor is the one with the better metric, okay? And the other one, if this one goes down, remember this is a packet switching network, we want to have another path. If this one goes down, we'll use this path. It's a higher metric, but this is our feasible successor, okay? This is the feasible successor. EIGRP, by the way, like other routing protocols, uses multicast addressing, okay? It uses multicast addressing to send information from router to router, okay? RIP version 2, EIGRP, OSPF, they all send destination multicast addresses, starting with 224, to send to a router or groups of routers in a routing domain or a multicast group. And so that's, in a nutshell, how the enhanced IGRP protocol, originally from Cisco, how it works. In this lesson, we're going to take a very brief look at the Border Gateway Protocol, or BGP. And the reason why it's going to be a brief look is this is the main protocol that's used by service providers and large enterprises. So I don't want to get too ahead of ourselves, okay? We're still just starting out with this TCP IP thing. But it's important to know about BGP because it's one of the original foundational protocols of the internet. It's complex, so it's excellent for the internet and the routers of the internet. It's very scalable, so it can scale up to many, many different points of presence and routers on the internet. It's reliable, it's secure, and it's TCP based. So there's a TCP handshake that happens between BGP neighbors. Very important protocol. External BGP, or eBGP, is a part of the Border Gateway Protocol that's used for exchanging routes between the different autonomous systems, or ASs, of the internet. An autonomous system is a collection of networks under a single technical administration domain. So for example, Amazon Web Services has their own AS. Google has their own AS or more. BGP provides the routing between these autonomous systems. By the way, you could have your own autonomous system at your own enterprise or your own organization. BGP can be internal or it can be external. So we could use an internal protocol, let's say OSPF or RIP, and then we could use BGP as our external protocol. So here's an example of where we got these two autonomous systems. On the left-hand side, we have Autonomous System 65,000. On the right-hand side, we have Autonomous System 65,001. Between those two ASs, which again could be two large companies, two large corporations or organizations, they're going to use the external gateway protocol BGP. Notice that internally, they're using something like OSPF or EIGRP, or they could use RIP version 2 if they wanted to. But again, BGP offers reliable updates using TCP port 179. BGP can be internal, an IGP, or an EGP, which is much more common. Customers can exchange the routed information with service providers. Service providers can trade the routed information with other ISPs. It's highly scalable, which means it can be expanded to a lot of routers, a lot of autonomous systems. You get security through authentication of the peer router and route filtering, and it's complex. It supports advanced routing policies and route manipulation between the peers. Okay, if you remember in lesson 6, we came in here and created our own virtual private cloud. And in that virtual private cloud, we had one public subnet. And they tried to give us initially the RFC 1918 10.10/16 network, remember? But we went ahead and said we're going to go ahead and use 192.168 for our VPC. So we had 192.168.0.1.2 and so on as our subnetworks, and each one of those subnetworks had over 250 possible IP addresses in them. Well, now we're going to mention Border Gateway Protocol. And when you use Amazon Web Services to create a virtual private network, you only have for your dynamic routing protocol, if you use what's called the managed VPN from Amazon, you only have the ability to use Border Gateway Protocol. So let me show you that real quick. The first thing you're going to do is go create under VPN connections down here. You want to create your gateways. Now the virtual private gateway is basically the gateway here at Amazon Web Services that my data center connects to, or my headquarters or my branch office or whatever, to get that AES 256 IPsec IC version 1 protection. So I'll click on virtual private gateway and we'll create one, and we're going to name this HQ. Okay. And we could use the Amazon default ASN. Remember that Border Gateway Protocol uses an autonomous system number, right? And we can go ahead and use that one, or we can say, let's use a custom ASN. And it's going to tell us that you have to use a private ASN for this. So anything above 64,512 I can use. So I'm going to go ahead and just let Amazon use their default ASN that they use as part of their infrastructure and create the virtual private gateway. And so here's the unique identifier, which is a unique Amazon identifier. Okay, so if I want to, let's say for example, route traffic out of my public subnetwork to the VPN gateway, I would just route it to this VGW, so on and so forth. So remember earlier, we created that public subnetwork. And if I put a Windows instance in there or a Linux instance in there, and I wanted that particular operating system instance to actually connect over the virtual private gateway and get access to, you know, my data center or a branch office over that IPsec connection, then I would just point in the routing table to this if I'm going there, okay? Well, I created that, so let's close out of here. And now let's create the customer gateway. And this is what's going to be the information about my side, okay? So I'll just say this is my data center. And I can do static routing, but I'm going to do dynamic. This is all about BGP, okay? They're going to try to give me the BGP autonomous system number of 65,000, and it tells you the Border Gateway Protocol BGP autonomous system number of your customer gateway should be entered here. Now you can use an existing ASN that's assigned to your network, and if you don't have one, you can use a private ASN in this range of 512 to 534. So let's say I don't have one, and 65,000 is the default of Amazon, but I'll say 514. Then I'm going to put the IP address of my customer gateway in here, which is the router at my headquarters, and we'll create customer gateway and then close out of there. So now my virtual private gateway created and my customer gateway created using Border Gateway Protocol, I can now go and create a VPN connection, and I can just say my VPN. And then the virtual private gateway, I already just created that, right? So I'll choose the one that I created right there. And I can say customer gateway, I'll use an existing one which I created, which is right there, right? Or I could create a new one. And of course, the routing options is to use dynamic BGP. And those settings are already set in there. Notice down here that you're going to customize a tunnel inside CIDR and pre-shared keys for your VPN tunnels. So you're going to have two tunnels. That's going to be for failover purposes. So from the VPN gateway, there'll be two different tunnels that are going to your headquarters. So I've already provided the public IP address of my router, so there'll be two logical tunnels. This tells you you can let Amazon generate this for you, or it tells you it's going to be a /30 CIDR in what's called the 169.254.0.0/16 range, which is actually something called a PIPA, APIPA. And if you, for example, run a Microsoft environment, let's say it's your company, and your workstation or your laptop wasn't able to get to the DHCP server, it would still let you boot up your system, but it would give you one of those 169.254 addresses so that you could at least get your machine up and running, get the TCP IP stack up, and you could, troubleshoot your workstation or your laptop. So I can let Amazon generate all of these and the pre-shared keys, or I can come up with my own. Now, I'm not going to create the VPN connection here because it's going to apply charges, and I don't really want to do that. But you see the steps here, and you see how we use dynamic BGP. Now, if for some reason at your headquarters you wanted to use a VPN that was using, let's say, EIGRP for the dynamic routing protocol, or open shortest path first, and maybe you already have your own kind of multi-point VPN set up, and now you just want to include Amazon, well, you have to spin up your own servers and everything in your own VPC, in your own public subnets. You have to really kind of manage that VPN on your own, right? You couldn't use this managed solution. But let's go back to this area and just remind you that there's several ways. Remember that public subnet that you created in the previous lesson? There's several ways for your instances that you spin up to communicate outside of that, or to get out of that public subnetwork. If you wanted to get out and communicate and just go to the internet and go to web servers on the internet, or maybe access your own site or branch office in just a public way without a VPN, you would just create an internet gateway or use an existing internet gateway and just point to that in the route table. And here's where your route tables are. So you just simply, wherever you want to go to, you're just going to point to that object in the route table. So if you have an egress only Internet gateway, this would be for an instance that you spin up in your public subnet that is going to be an IPv6 host. So if it's going to be using IPv6 addressing and you want it to use that and you want it to go out to the internet, you need to use an egress only internet gateway. What if you had a private subnet? Okay, not a public one, but a private subnet, and you had servers in there like web servers or database servers, and they needed to go and connect to the internet for, let's say, Windows update services, or to download service packs or hot fixes, or they need to have updates. Well, then what you would do is you put a NAT gateway in your public subnet, and then have those servers in the private subnet point to, in their routing table, the NAT gateway to get out to the internet. Now, nobody outside will be able to access those servers, the web servers or whatever, SharePoint or database servers, but they'll be able to get out through the NAT gateway and get access to some service on the internet so they can download their hotfix. And then for various connections from your private and public subnets, you can use endpoints and endpoint services to bypass the internet and just connect directly to, let's say, other VPCs that you create or other services within Amazon Web Services. And then the last thing is the elastic IP. Remember that subnet I created, right? Which I did earlier in lesson 6, I believe. That subnet, if I want to allow those instances to be accessed by the public on the internet, I need to go get an elastic IP, and I need to assign that elastic IP to that subnetwork. And it'll be some publicly routable IP address that's part of Amazon's pool. So the instances in the public subnet now, they can get out. They can communicate with the internet, but hosts on the internet cannot communicate to them because, remember, they're using 192.168 addresses. To expose those addresses on those instances in the public subnet, I need to go get elastic IPs and allocate a new address. That's going to cost you money. It's going to cost me money, but it's going to be a public IP version 4 address that hosts on the internet or at my headquarters or anywhere can use now to get to those Linux and Windows instances in that public subnet that I created earlier in lesson 6. All right.
Module 5 covers 2 main transport layer protocols. First off, we'll look at a wide variety of information concerning TCP, Transmission Control Protocol. Then we'll look at the ins and outs of the very popular UDP, User Datagram Protocol. Lesson 10 is titled Transmission Control Protocol, TCP. We're going to understand ports and sockets. We'll look at the TCP behavior, attributes, and characteristics. We'll examine TCP operations, and then we'll finish up demonstrating those operations. Okay, let's talk about sockets, and sockets, not sprockets, which was that old Saturday Night Live skit. This is sockets, okay? And let's talk about what a socket is. Let's look at this host up here. So I'll come over here. We have this, I'm going to do a laptop this time, okay? So we have this laptop that's maybe at some office somewhere. And they've got an address of 10.10.10.100/24. Now looking at that, we know that that's one of those RFC 1918 private addresses, right? So we're going to have to do some network address translation or port address translation here on this router, because this address, this IP address will be blocked either by something on this router or definitely when it gets to a router at our service provider on the internet. But let's talk about what a socket is, okay? So let's say with this laptop, I'm going to go up to Amazon Web Services, right? And I have created up at Amazon Web Services my own kind of virtual private cloud,
right? So I just got just a basic account, and I can get some free stuff. And I'm going to create a secure shell server there, okay? So I'm going to spin up, let's say, a Linux instance. And I'm going to turn that little Linux server into what we call a bastion host. A bastion host or a jump host. In other words, I want to use this Linux server to connect to other servers inside my virtual private cloud. So what's going to happen is Amazon is going to allow me and allocate me what's called an elastic IP address. Let's say it's 77.63.2.129. That's a publicly routable, valid address out here on the internet, okay? So I want to connect to this secure shell server with a secure shell client on this laptop, right? So that I can, jump in here to these subnetworks and I can configure those instances. Here's the deal. When I want to connect to this secure shell server, the first thing I'm going to do is I'm going to do a TCP handshake, okay? A three-way handshake between this host right here and this secure shell server up here. The problem is this is a private address. Okay, it's not going to get past that router. So this particular host is going to say, look, I want to go to 77.63.2.129 and the service port that I want to hit is 22. So I'll just put :22 because 22 is the port that Secure Shell uses, right? So that's the socket that this particular host wants to get to. So the source IP address is going to be 10.10.10.100/24, and it's going to just choose some random ephemeral port. We'll say it chooses 3333, okay? So the source port will just be some random port, something above 1024. That's the source socket, okay? 10.10.10.100:3333. That's the source. The destination, we've already established that. Now, when this packet goes, it'll first go, the frame will go through the switch, the frame will leave the switch, the frame comes to this router, or what's called my default gateway, okay? The way I get out of my local area network. When it comes to the router, it's going to have to translate this private address to something public, okay? So let's say on this router, I've got some public address of 67.22.10.33, okay? And it can be a pool of addresses that this router has, or it could even be a wireless access point. But let's say it's a router. So it could be a pool of addresses, like a /24, 254 addresses, or a /23, which gives me 510 addresses. Or I could just have one address on this outside interface that's been assigned from my service provider, okay? Either way, if I have a pool of addresses, I'm going to do network address translation. If I'm just going to overload a single address, we call that port address translation. Bottom line is, this router is going to change the source IP socket from this to 67.22.10.33:3333. And it keeps a table on here so it knows the translation, okay? It knows that it translated this to this, so it keeps up with that, okay? It keeps track of it. So this becomes the new source IP address as it goes out to the internet, but the destination IP address still stays the same, okay? And so that's the way that sockets work. A socket is a combination of an IP version 4 address and then some port, okay? The client chooses some random source port, but the service port, it depends on the service, okay? If it's Secure Shell, it's 22. If I'm going to go hit a web server up here, and this is a public address. If it's a web server, then the service port or the destination port is going to be port 80, okay? If I'm going to use SSL TLS, and this is a secure web server, then it's going to be destination port 443, okay? And so as this host gets translated, it goes out on the internet. Now, if it goes to a branch office, okay, I could be doing translation here. So notice that this laptop down here, this is one of those RFC 19 private addresses, right? So there'll have to be some translation that's done, some network address translation or port address translation on that router, or it could be a firewall appliance, like a Cisco 5515X, something like that. And so remember that the socket is the combination of the address and the port. The source port number, the client just chooses something above 1024, but the destination port, it is usually the standard port, okay? 80 for HTTP, 22 for secure shell, and if it's, if it's email and it's going to an SMTP out there, that has its own port. And we'll talk about those ports in a different lesson, okay? But I wanted to give you an idea of kind of how these sockets work together, either as you translate or you don't translate. So for example, if I was coming from this elastic IP address through this gateway at Amazon Web Services, coming down to this web server here, there would be no translation. This is a public IP address routable on the internet. This is a public address routable on the internet, okay? So sometimes we do translation, sometimes we don't, right? So there we go, sockets. Let's look at some functionality or characteristics of TCP. Obviously, TCP is involved in addressing, and it does that in the form of ports, but it also does multiplexing, and multiplexing is really a cool feature. If you think about it, let's say on your workstation or your laptop, you decided you were going to bring up, how about 3 different browser sessions. So you open up Chrome, and Chrome goes to its home page, which we'll say is google.com. And then you open up maybe, let's say, a Mozilla Firefox browser, and that goes to, let's say, the home page of yahoo.com. And then you open up an Internet Explorer browser, and maybe that IE browser goes to its home page, let's say Bing, that search engine. So you got 3 browsers opened up. They all go to 3 different home pages. And then maybe you decide to open up your corporate Outlook on the web email through a Tor browser for security. And then maybe you have Mozilla Thunderbird, and you bring that up to go to your email, to your POP3 account. So you've got like 5 different applications open that are going to different IP addresses on different ports. So it's that multiplexing of all those different applications that are running. TCP helps provide that for us. It also handles the connection because TCP is connection oriented. Later on I'll show you in the Wireshark tool. Actually we'll dig under the hood and look at a TCP 3-way handshake and setting it up and going to a web page and getting some web pages and tearing it down. So it handles the connections. It will package and manage data. And remember, TCP puts it into what are called segments, okay? Or it provides segmentation. It helps transfer data logically between different ports on different systems, clients and servers. It provides reliability and transmission quality. So for example, it can ask you to resend a segment. If it didn't get there, it can reassemble the segments and put them back in order on the server, for example. It also provides flow control and congestion avoidance, primarily with a tool called windowing. So let's imagine that you rented a beach house, okay? And at this beach house, the wind can go between 5 miles an hour and 25 miles an hour, right? And you get those cool breezes coming in through the house, but as the wind picks up, you go and you kind of lower the windows a little bit so you get less of that air. Let's say the wind goes down to 5 miles per hour, you want to get more wind, you open up those windows. So TCP clients and servers can also do this windowing, so they can say, I'll send more segments if it's not congested. If it gets congested, I want you to close the window and send me fewer segments. So TCP provides that service as well. What does TCP not do? okay? TCP does not determine how applications actually use TCP, okay? So it's up to the upper layer applications to determine, number one, if they're going to use TCP at all, or number two, they're only going to use TCP for certain functions or certain activities, okay? And that can be the case, okay? Remember DNS, which is a very popular protocol, it can use TCP if it has to set up a connection and transfer the DNS database between DNS servers. But if you're going to do a DNS query out on the internet, DNS is not going to use TCP. It's going to use UDP for that. So TCP doesn't decide how the application actually uses it, right? It doesn't ensure privacy or authenticity. So technically, we're going to use either something at layer 5, like SSL TLS to do that, or we could use IPsec at layer 3 to do that, okay? TCP sends data as a continuous stream of segments instead of as discrete messages. So the application will decide where one message begins and one message ends. Also, TCP doesn't actually guarantee delivery of segments, okay? It provides reliability by detecting a failed transport of a segment and then resending it, okay? So it's not a guaranteed service, it's just a reliability service. Some other characteristics of TCP, as we know, it's connection oriented, so there's a three-way handshake that sets up the connection. It's stream oriented, so it's a stream of segments. It has to be reordered and reassembled in the right order when it gets to the server. It has bidirectional transport, so it's a socket that's set up between two endpoints. It also allows multiple connections. Going back to my previous example of I've got a bunch of web browsers opened up and a bunch of other applications, maybe a telnet session, a FTP session. TCP can handle all that with its different port numbers and sockets. It's reliable and acknowledged. It's not guaranteed, okay, but it's reliable and it's acknowledged. It provides unstructured data in the form of segments, and it manages the data flow with using sequencing numbers and windowing techniques. Let's examine TCP operations. TCP takes the bytes from upper layers and then sends it on to the network layer protocol IP. Now, since applications are sending data to TCP as a stream of bytes instead of pre-packaged messages, each application will typically use its own mechanism, its own scheme to decide where one application data element ends and the next element begins. Once it comes to TCP, the bytes are divided into segments, and a segment's a discrete piece of a stream. Then, the Internet Protocol places them into datagrams and passes the encapsulated packet to the link layer to be framed with a header and a trailer. Let's say that our application protocol is going to be HTTP, and HTTP is going to send a byte stream down to TCP, as we see here. Realize that TCP is different from other protocols because it doesn't require the applications to send data to it in messages. Once a TCP connection is set up, the application can send TCP a steady stream of bytes without having to conform to any certain structure. TCP packages these bytes into segments, and they're sized based on a number of different parameters. For example, TCP uses a sliding window acknowledgement system, kind of like if you're on the beach and it's windy outside and you want to open and close your windows accordingly. If the winds pick up, you can close the windows a little bit. If the wind dies down, you can open up the windows a little bit. So this is done for reliability and data flow control. Eventually, these segments are passed to the IP protocol, where they get encapsulated into datagrams. So over on the other side, the receiving device is going to do this in reverse. The segments are removed from the IP datagrams, and then the bytes are taken from the segments and passed up to the proper recipient application as a byte stream. In this case, it's HTTP. Now, something else that's interesting is that since TCP works with individual data bytes instead of discrete messages, it has to have some identification method, some scheme that works at the byte level in order to do its data transmission and tracking. How does it do this? It assigns a sequence number to each byte that TCP processes. So at the very beginning, when that TCP three-way handshake happens, the sender, or the client, will actually have an ISN, an initial sequence number. Now here's something that's kind of interesting. If you have a firewall in the middle of the client and the server, what most firewalls will do is they'll take that initial sequence number and they will run it through some pseudo-random generator, and then they'll spit out some random number, and then they'll take the delta, or the difference of that initial sequence number, and store that difference in RAM memory on the firewall or the firewall router. And it does that as a security mechanism to prevent people, let's say malicious man-in-the-middle attackers, from injecting or guessing the sequence number and guessing the window size and injecting themselves into the process or taking over the connection, for example. Kind of cool. As mentioned, TCP is reliable, so it tracks each byte of data with a sequence number. Sequence numbers are used to make sure the segmented data can be reassembled and then retransmitted if necessary. To provide reliability and flow control, TCP uses an advanced and complex sliding window acknowledgement system. This is actually a pretty complicated process, so if you want to know more about that, I might recommend a book to you called The TCP/IP Guide by Charles Kozarok. Each node's TCP stack uses a transmission queue. Each sent segment is then placed in the queue and a retransmission timer is started. When an ACK or acknowledgement is received, the data is then removed from the queue. If the timer expires, then the segment is retransmitted. Here's our TCP header. We can see that we have our source port number and our destination port number. So the source port is 2 bytes or 16 bits. That's 2 to the 16th power. So you've got 65,536, or really 35 ports, source ports and destination number. The sequence number is pretty big. It's 4 bytes. It's as big as an IP address. And the acknowledgement number is also 4 bytes or 32 bits. The control flags are very important. There's 9 different bits there, and the options are either 0 or 1, and those are going to contribute to what's called the TCP finite state machine. In other words, knowing the different state of the connection, the status of the software on the particular client or server, the transition stage, the events and actions that take place. Now, there are several bits in those control flags, but the ones that we're concerned with are 3 of them. There's a SYN bit, which is SYN. If that's turned on, it's a synchronized message, basically initiating and establishing a connection. Its function is to synchronize sequence numbers between the client and the server. Next, we have an ACK, an ACK, an acknowledgement message. This indicates the receipt of a message, such as a SYN, or the third one, a FIN, F-I-N, a finish message. This is a TCP segment where the FIN bit is turned on, and it indicates that the device wants to terminate the connection. There's 3 other control bits we see here. URGE, or urgent, indicates the priority data transfer feature. PSH, push. The push feature requests that data be pushed to receiving applications immediately. And RST, or reset. This means the sender's encountered a problem and needs to reset the connection. And again, each control flag subfield is 1 bit in size. Here's the process of the TCP handshake. We'll see this in Wireshark in an upcoming demonstration. Realize that before you can use TCP to actually send data, you have to set up a connection between 2 devices that want to communicate. This is typically called connection establishment, but we also call it the 3-way handshake. We have host A, the client, on the left, and host B, the server, on the right. Host A will first send a control segment with the SYN bit turned on or flipped from 0 to 1. This basically says that this segment's being used to initiate a connection. It wants to synchronize. And it's also referring to a sequence number. For example, in this case, it's 100. Host B receives the SYN segment It will acknowledge that by turning on the SYN flag and the ACK or acknowledgement flag. ACK indicates that the server sending back this segment is basically conveying an acknowledgement that it received the message. Host A receives that. It establishes the connection. Notice we have a sequence number, an ACK number, and then data can now be sent from the client to the server, or vice versa. So in a nutshell, the client sends a SYN message, the server sends a message that combines an ACK for the client's SYN, and it contains the server's SYN, or synchronize, and the client sends an acknowledgement for the server's SYN. That's really the three-way handshake in a nutshell. Okay, in this demonstration, we're going to get a simple look at the TCP protocol, its operations, specifically with an extremely popular application layer 7 protocol that uses TCP, and that is HTTP. And you can see I've got this http.cap file. I downloaded this from the Wireshark wiki, and I highly recommend that you do this yourself when you get Wireshark. But I want you to notice at the top here, what we're going to see right off the bat is what's called the TCP three-way handshake. So our source, or our client, is at IP address 145.254.160.237. It's an IP version 4 address, and it wants to go get a web page from a web server at 65.208.228.223. So the first thing it has to do for this connection-oriented protocol is to set up the three-way handshake. So it's going to choose for its source port some what we call ephemeral port number above 1024. So it's going to choose 3372 as its kind of random source port, but the destination port is 80. So what this creates is what we call a socket. So the socket from the client's point of view is going to be 145.254.160.237:3372. Now, let me just mention something. If you were doing this yourself, let's say from home or a small business, and you're behind a router that's using network address translation or port address translation, what's going to happen is most likely the source IP address is going to be something from the RFC 1918 private address space. So 192.168.0.something/24. If it's a company, maybe 10.10.10.30 or 10.10.10.237, something like that. So let's assume for a second that's the case. Let's say I'm behind a corporate firewall, and my source address is a RFC 1918 address. So it's 10.10.10.237. Okay? The socket that's going to be created is I'm going to go ahead and still choose 3372, but the router or the firewall is going to actually translate that into this public address, let's say 145.254 and so on. If I'm using port address translation, where my firewall or my router is basically overloading that one IP address that's assigned from the service provider, so if I did this from my home, I know that I've been assigned an address 173.219.226.something. So basically, I would be creating a socket, but the translating router would still use this same source port number, 3372, if it's available. So it'll do a translation of the private address to the public address, but it'll still, if it can, it'll keep this port number. Okay, so make sure you understand that. But the destination is port 80, and that's the service port for HTTP. So the first thing is what we call a TCP segment with the synchronization bit or flag turned on. So it takes that flag in the TCP header and it turns it from a 0 to a 1 in the flag field. Okay, so then the web server, which is at 65.208 and so on, it's going to obviously send from port 80 its socket 65.208.228.223:80 back to 3372, and it's going to send a TCP segment, and it's going to turn on the SYN flag from 0 to 1, and it's going to turn on the ACK flag from 0 to 1. And so that's the SYN-ACK. And by the way, this is actually a very common type of attack. If someone's trying to attack your router or some other server at your company or whatever, what they'll often do is they'll flood that device with a bunch of bogus SYN-ACK segments, or TCP SYN-ACK. That's called a SYN-ACK attack. It's very common. Most of your modern routers can easily deal with that denial of service attack. It uses several different mechanisms, cookie, to make sure that this is actually legit. But then notice that the original client, HTTP client, is going to go ahead and send an acknowledgement. So once the server gets this acknowledgement, then the TCP three-way handshake is complete and the session is set up. And now the client can get something from the web server. So it's using the HTTP GET method to attempt to get some content from the web server. And if we go down here, we might see also that, this client is trying to go maybe either through that web server or through a link to some other site, like, googlesyndication.com. And so there may have to be a DNS resolution. And so there are a couple of other DNS resolutions that take place in here. Once those resolutions occur, now you can see the client is going to a different IP address, 216.239.59.99, and it's getting something else, okay? Some advertisement or some click-through. Again, another example of using the domain name service to resolve this pageadd2.googlesyndication.com to its IP address so that this client could then go to a different IP address, right? And so what we'll see at the bottom here is that eventually this is going to wrap up, okay? It's going to go and hit some websites and grab some content from the web server, but eventually there's going to be a tearing down of this TCP connection. So when the source client is done, it's going to say, look, I'm going to send you a TCP segment, and I'm going to turn on the FIN flag from 0 to 1, right? And I'm going to acknowledge that with the acknowledgement flag turned on, and then that TCP handshake is torn down. And, it can be torn down gracefully like this, or it can just be shut down by a timeout on the server side, and it just stops the connection, okay? But often we'll see, a graceful teardown of the connection by this type of activity. And if I double click on one of these, it brings up a window where I can actually dive in deeper, okay, and see the internet protocol activity going on here. And so, we can see that as far as IP is concerned, in the internet protocol header, there is a field called protocol. And so you can see that in that field, it says it's going to be the number 6, which says this is TCP, okay? So again, you can kind of get a little bit deeper into these activities by just clicking on this, right? And notice this right here where it says 2 reassembled segments. Realize on the server side that the server has to reassemble those segments so that they're in the proper order so it can actually process whatever the data payload is, all right? So here's an example of one of the most common, if not the most common, TCP protocol in the world, and that's HTTP, and using Wireshark to see the three-way handshake to set it up, its activities of getting pages from the web server, and then gracefully tearing down the TCP connection. Excellent.
In Lesson 11, we're going to look at User Datagram Protocol, UDP. First, we'll compare UDP to TCP. We'll understand the different UDP ports and explore common UDP services. And then we'll finish up demonstrating Datagram TLS or DTLS. In this lesson, we're going to look at some of the things that make UDP, User Datagram Protocol, different from TCP. So for example, UDP does not ensure data delivery like TCP does. Remember, TCP gives us reliability and acknowledgement.
If TCP is used, the transport layer has those additional responsibilities. UDP does not provide segmentation services. The behavior of UDP is basically best effort and connectionless. In other words, it's kind of like if I want to send my neighbor Peter a message and I write it down on a piece of paper and fold it up into a paper airplane and throw it over the back fence. That's kind of the way UDP works. There's no sequencing of segments with UDP. And it is best for video and voice streaming, audio streaming, conferencing, and then ping-pong services like DNS queries, for example, and trivial file transfer protocol, TFTP. Remember, nowadays, UDP is used a lot more because some of the connection-oriented and reliability is actually built in at the upper layer protocol. So they'll build that in the upper layer protocol and go ahead and use UDP. In real-time applications, drop packets can be accepted as long as the overall percentage of drop packets is relatively low. So for example, if you're watching a streaming video, for example, if some of those UDP packets are dropped, your brain will fill in the gaps. I think we call it the Gestalt effect. But if you're watching a video or you're listening to music that's being streamed, if a few of those UDP packets don't make it, you'll fill in the gaps with your mind. It's a very cool thing. That's why it's commonly used for those types of services. Even with voice over IP, if I'm talking to you with internet voice over IP, if a few of those packets are dropped, you're still going to get the conversation and you're going to understand what I'm telling you. A connectionless protocol is appropriate for programs that need faster communication without necessarily verifying the receipt. So again, an analogy, TCP is kind of like sending certified mail or maybe sending something by FedEx or UPS, where UDP is like getting those advertisement flyers in the mail once a month. Okay, we're going to talk about UDP ports here specifically, and we know that on our systems that the MAC address, the media access control hexadecimal address of the network interface card, is mapped to an IP address. We know that the ARP protocol helps us make that mapping in version 4, and we know that ICMP version 6 helps us make that mapping in IP version 6. But how does the computer, how does the system know which service or application it's bound for? Well, that's where our ports come in, right? Now remember, in the UDP header and the TCP header, there's a source port field and a destination port field. Both of those fields are 16-bit fields, right? So 2 to the 16th power. So what that means is we have 65,536 possibilities. So we have over 65,000 possible UDP ports, and we have over 65,000 possible TCP ports. Now with UDP, we actually do use a lot of ports that are kind of way up there in different random ports, right? But we never use all of these different ports. Some of these ports are assigned though. And so I want to make sure we understand some of the most common assigned UDP ports, okay? One of them, probably the most common, is the domain name service. And so that's going to be port 53 UDP. Now remember, some of these protocols and services, they can use UDP and or TCP. So DNS uses UDP 53 for its queries. Okay, DNS queries for its ping pong services. We can call it that, okay? So DNS service uses that. DHCP also can use both UDP or TCP for its kind of basic discovery process. DHCP can use port 67 or port 68 UDP. If you don't want to use the FTP protocol and all you want to do is just go up to a server and just grab some configuration file, often we do this with routers and servers, we can use what's called the trivial file transfer protocol, TFTP. That's a much more basic and fundamental. It doesn't have all the bells and whistles that FTP does. If you're going to use trivial FTP, that uses UDP port 69. Some database services will use UDP, basically to just query or get information, like the structured query language, SQL, which is a very popular relational database service. SQL can use port 118. It might use port 156. So some of these database services will also use UDP. The network time protocol, okay, which allows these particular hosts or routers that they're working with to synchronize their time. Often what they do is they connect to an NTP server up here on the internet, and that's connected to an atomic clock, right? That way they can have their time synchronized down to the milliseconds, okay? So NTP, Network Time Protocol, we can use, that's on port 123, UDP port 123. The Microsoft world, Microsoft used to have a protocol that was very popular. It was called NetBIOS. It's still used on, even on server 2012 and 2016, but it's kind of rare, but you know, you might still be using Microsoft NetBIOS. That used a couple of UDP ports, 137 and 138. SNMP, Simple Network Management Protocol, okay? SNMP, a very important protocol. When it sends its traps, it'll use UDP port 161, okay? And then finally, you might be using Internet Relay Chat, IRC, very popular service that's used with internet chat, and that'll use UDP port 194. Now, something else about ports that's very interesting is that most organizations, either on this router right here or a separate device, will be a firewall, okay? Now, the firewall service can run on the router. It could be like a little module you attach to the router. It could be something the router connects to, or it could be a dedicated box that's a firewall, right? These particular devices, and whether it's on behalf of UDP or TCP, they often have to permit and deny, or what we call whitelist, certain traffic. And so they whitelist that traffic, the classic stateful packet firewall, based on the common service numbers, the port numbers that they use. So firewalls are also aware of the ports that these different services use, so they can open up the firewall, they can open up those ports to allow that traffic to come in and go out of the organization. UDP. In this lesson, I want to delve deeper into User Datagram Protocol, or UDP. So first off, when do we use UDP? Okay, when you need a rapid response from a server, okay, for example, like a DNS query or a type of ping pong service, that's great for UDP. It's also preferable when the response comes back in just a single packet. That's a good usage of UDP. Connection costs are too high with TCP connection-oriented services. If that's the case, then we'll try to use UDP. When you can afford to lose some data, let's say it's a stock ticker that's kind of streaming stock quotes, or weather data, weather information, or maybe gaming data, or audio or video streaming, or conferencing. You can lose a few packets there. UDP works great for those types of services. And UDP can be multicasted to more than one host. So we know that UDP does unicast, but it can also be part of a multicast. For example, let's say you have a group of individuals that are getting a web conference, okay, and they're in a multicast group. UDP, awesome for that. We use UDP for DNS queries. It's also used in Simple Network Management Protocol to send traps, okay, on UDP port 161. Routing Information Protocol, RIP version 1 and RIP version 2 uses UDP. The Dynamic Host Configuration Protocol, DHCP, can use UDP. Datagram TLS, where we're using transport layer security, where we initially set up a three-way handshake with TCP, then Datagram DTLS takes over. I'll actually show you this later on in a demonstration. Or real-time audio and video streaming protocols love to use UDP. Let's talk about UDP Lite, which is out there and commonly used. Certain programs can still function even when there are partially damaged payloads involved, okay? If your partially damaged payload is delivered instead of being discarded, well, these applications can tolerate some payload corruption. And they might use what's called the Lightweight User Datagram Protocol, or UDP Lite. A couple of RFCs for that, 3828 and 4505. You might want to check those out. It modifies the UDP payload length field to basically what's called checksum coverage length. That's not that big of a deal for you to remember, but it is an important protocol. We also have what's called DCCP, which is part of the UDP family. This is the Datagram Congestion Control Protocol, and this offers a more refined and advanced datagram service. It's mainly geared towards unicast streaming services on the World Wide Web. This protocol is covered in RFC 4340. Let's talk about a very important protocol that uses UDP, and it's a protocol that we could talk about, I guess, along with HTTPS or SSL-TLS, but since it does leverage the UDP protocol in such an elegant way, I'm going to talk about DTLS here. DTLS provides security for datagram-based applications, so that's TCP/IP Layer 3, and it prevents eavesdropping, tampering, or message forgery. However, beyond that, the DTLS protocol is based on the stream-oriented transport layer security TLS protocol and is intended to offer similar security. It preserves the semantics of the underlying transport so that the application doesn't suffer the delays that come with streaming protocols. And so you'll probably be using DTLS if you work for a company and it has a VPN client running on your laptop or on your workstation or on some mobile device. And you'll be using DTLS without even really knowing it. You think you might be using SSL-TLS, but to help provide better performance for those audio streaming, video streaming, conferencing programs, you're most likely using Datagram TLS under the hood. And since DTLS uses UDP instead of TCP, it avoids the problems that happen when TCP is used to create a VPN tunnel. DTLS 1.0 is based on TLS 1.2, and then DTLS 1.2, which notice they skipped a number, is based on TLS 1.2. So most likely you're using Transport Layer Security 1.2 over TCP/IP initially, and then your system will switch over and use DTLS 1.2. There's no DTLS 1.1 as that version number was skipped in order to harmonize the version numbers with transport layer security. Companies like F5 Networks Edge VPN Client uses TLS and DTLS. Citrix Systems NetScaler uses DTLS to secure UDP. Web browsers like Google Chrome, Opera, and Firefox support DTLS SRTP, or Secure Remote Transfer Protocol, for what's called WebRTC. And the Cisco AnyConnect VPN client uses TLS and DTLS, as does the open source OpenConnect client. As a matter of fact, that's what I'm using on my laptop, and it looks just like this. When I connect using my Cisco AnyConnect Secure Mobility client to a corporate VPN, I'm also using Cisco Umbrella, which means all of my DNS queries are going to Cisco's secure encrypted DNS servers. But then when I look at the status of my VPN network, I can see the protocol I'm using is not TLS, but actually Datagram TLS with a very strong cipher, RSA, and AES 256.
Throughout this entire series, I've been mentioning several different requests for comments, RFCs. So here's the one, 6437, which is the RFC for Datagram Transport Layer Security version 1.2. And this is basically DTLS with UDP. And so I really highly recommend that you go up and get this request for comment, or just take a look at it and kind of familiarize yourselves not only with the protocol, but also with understanding how these RFCs can be such valuable resources. In our final module, Module 6, we're going to look at various TCP/IP application layer protocols, biggies like DNS, DHCP, SMTP, and of course, HTTP, what we use on the World Wide Web. The title of Lesson 12 is Surveying the Application Layer Protocols and Services. In this final lesson, we'll introduce DNS, Domain Name System. We'll introduce FTP, File Transfer Protocol. We'll look at DHCP, Dynamic Host Configuration Protocol. We'll explore SNMP, Simple Network Management Protocol. We'll look at email or electronic mail. Then we'll introduce Hypertext Transfer Protocol, HTTP, and the secure version, Hypertext Transfer Protocol Secure. And then we'll finish up this lesson with a demonstration of the Wireshark Packet Sniffer tool. Well, we're going to be looking at application layer services, and we're going to probably start out here with what I think is one of the most important services, and that's the domain name system, and DNS is how we refer to it. Now, why is it so important? Okay, well, because as human beings, we like to use user-friendly names to refer to things. Okay, you know, my buddy Pete back there who's producing this with me, you know, I could refer to him as his social security number. You know, I could memorize that, or he could give me his driver's license ID number and I could refer to him as that, or maybe his phone number, you know, hey, what's up, 512 or whatever his 503, whatever his phone number is. But, you know, we like to use friendly names, and so that's what the DNS service does for us. Things that are easy for us to use and easy to recall. Host names or friendly names are often used to represent clients and server nodes, as well as other things, okay, like even a router, for example. The conversation process between the nodes or the hosts is called name resolution. And there are several types of name resolution that can be used with the internet and with other networks, but for us, DNS is the most common and the most important by far. DNS is a distributed database, and it's used by TCP/IP applications to map IP addresses to host names, otherwise known as friendly names, or you might even hear the term FQDN, a fully qualified domain name. And it facilitates the routing of email services, also World Wide Web identities, web servers, for example, and much more. Each site can keep its own database so that internet clients could query them as needed. DNS is also an application layer protocol, and that's similar to other application layer services. Sometimes the Layer 7 service is also a utility or a tool as well as a protocol. Okay, for example, we might refer to ARP as a protocol or service, but ARP is also a program that you can run on your workstation or your PC. And DNS helps us manage and replicate and query that DNS distributed database. Now there's top echelons, what we call the namespace of domain name service. We have what are called generic top-level domains, GTLDs. Those are the ones you're most familiar with, okay, like .com. We also have country code TLDs or CCTLDs. Different countries will have their own country codes, you know, like UK, for example.
We have internationalized country codes, which are IDNs, and then we have special historical infrastructure TLDs, and those go back to the early days of the ARPANET, and those are called ARPA. The generic, or the GTLDs, are further grouped into three categories: generic TLDs, generic restricted, and sponsored. Here are some common GTLDs. And by the way, I'm also showing you here the estimated first use. So if you go down to the fourth row, there's .com, which was first used in January of 1985. And that's just generic commercial. And you might be familiar with EDU. That's another one from 1985, okay? Basically, United States Post-Secondary Educational Institutions. There's .gov, also from 85. You'll see there's info, which is relatively new, 2001. The military has their own .mil. Another one that's kind of new is MOBI, for mobile products and services. And then, of course, there's the .net and .org, which I'm sure you're also familiar with. To register a TLD or a generic TLD, you go to the ICANN organization. What we're looking at here is some case studies. This is one of the pages, so let me grab my laser pointer. I'm over here and I'm clicking on this case studies, and you can see these are some ones that, in the fall of 2018, these are proposed top-level domains like .bank, one of my favorites. I think maybe even Pete would like this too, .bar, which is, home for fun and social engagement. So .bar, then some organizations, some companies may even have their own TLD. So there we go. Let's look at the DNS naming structure. The names below the top-level domains are further grouped into subdomains. And this is especially true with the CCTLDs. A fully qualified domain name, or FQDN, consists of a list of labels separated by periods. So here's a domain that I own, Trainology.com. So a fully qualified domain name to publications on my web server at Trainology.com would be www.pubs.trainology.com. Names are case sensitive, and each label can be up to 63 characters. An entire FQDN is limited to 1 byte. Let's look at DNS administration. Individuals, entities, or organizations should take responsibility for parts of the namespace, which means one or more domains, like, for example, Trainology.com. You should have at least 2 DNS servers, or you should be using a service provider that will offer that for you to respond to queries on UDP port 53. So that's that ping-pong query service that DNS uses. Now, the DNS servers, they're going to store what we call the zone databases. You'll have a primary server and a secondary server, and obviously you're going to replicate information between those servers. Now, when that happens, you're going to use DNS TCP 53. So when you transfer that database information, we call it a zone transfer, let's say from a primary to a secondary, so that you have kind of a failover mechanism, that's going to be TCP. So DNS is one of those services, one of those protocols that can use UDP on port 53 and TCP on port 53. And a zone is a unit of administrative delegation, and it's a subtree of the DNS namespace. Every domain name, like Trainology.com, resides in some zone. Now, TLDs, the top-level domains, those reside in what we call the root zone. A DNS server can hold information about more than one zone. That's very common. For example, if you use Amazon Web Services cloud-based Route 53 DNS server, they're going to store information about a lot of zones. Each zone has a designated responsible entity who has authority to manage the names, addresses, and subzones. And we typically store that in a database record known as the SOA, the Startup Authority.
By the way, here's that URL to who is at ICANN. And you can use this search feature to go find out information about different domains out there. For example, when you register your own domain, it will store this information and people can do a who is and find out about the person that administers that domain. Now you can pay extra money and you can hide that information, and by the way, not a bad idea. Now, one thing DNS does very well is it caches information so it's readily available to those end hosts so that they don't have to query all the way up the DNS tree to the root servers. That information gets, as resolutions are done, as queries are done, it gets cached on lower level DNS servers. And so your name to address mappings typically come from three sources. One, it'll come from another DNS server that's resolving a query, or two, it'll be as a result of a zone transfer, or three, you'll get that most often directly from cached data in a zone database on a DNS server. Most name servers will cache zone transfer data up to a setting known as the TTL, or the time to live. Each DNS record has a TTL value that dictates how long it can be cached. When responding, the server indicates if the data is an authoritative copy or if it's from the nearest cache. If cached, usually the list of contacted name servers is also included in the DNS response. Here's an example of a UDP IP version 4 datagram with a DNS message, again up to 512 bytes. And we see this as a UDP datagram for DNS. So what that means is it's most likely a query, okay, or a response. And you can see that we have a UDP header, right, which is 8 bytes. And then we have the DNS fixed header, we have a question section, we have an answer section or a query and response. The authority section, which will provide information about who's the authority of that information, and then additional information. Okay, so that's not something you have to memorize for the real world, but just wanted to give you an idea. This could also be a TCP datagram if this was two servers that were transferring zone information, for example. And like I said, this is a distributed database, so there's different types of records in that database. One of the most common is the A record, and RR stands for resource record. That's basically the IP version 4 address, a 32-bit. You've also got NS, the name server. Okay, that's an important one. The authoritative name server for the zone. Maybe it's Amazon Web Services. An alias is a C name or a canonical name. Sometimes web servers will have an alias or a canonical name that they use for marketing purposes or for business purposes. That SOA is important because that designates the start of authority for that particular zone information. Then an MX record is basically the email mail transfer agent that's used by the SNMP protocol. Another one that's important that I'm going to show you here is the quad A, or 4 A's, AAAA, and that's the IP version 6 address record, and that's defined in RFC 3569. And you can also see other things for zone transfers of the database, like an IXFR is an incremental, just the changes transferred, and AXFR is transferring the full database. And again, as I mentioned, you're going to be using TCP 53 for that. In this lesson, I want to introduce the File Transfer Protocol, or FTP. This is actually one of the earliest TCP/IP applications, and early on it was used at a console or a command line, way before we had the operating systems with the graphical interfaces and all those good things. So it's old school. FTP uses a client-server architecture, so we've got FTP client and we've got an FTP server. Now,
Nowadays, the client, you could use your console session, like you could open up a console session on your Linux machine, or you could run cmd.exe on your Microsoft machine, or you could use a graphical tool, like I like to use FileZilla. Obviously, this is a Mozilla product. So I like to use the graphical tool FileZilla on my machines. And so what happens with FTP, the architecture uses a separate control connection and a separate data connection between the client and the server. So historically, the client and the server, this FTP is a TCP, connection-oriented protocol. So there's going to be a three-way handshake between the client and the server. Once that three-way handshake is up and the TCP session is ready to go, then we use port 21 for the command and control process. And then once we kind of exchange information, command and control, then we use port 20 to do our sending of data or receiving of data. So obviously there's different commands. The client could be putting data up on the FTP server, right? Or it could be getting data from the FTP server. And that's all figured out with the command and control channel. Now, FTP clients can authenticate themselves with a clear text sign-in protocol, typically in the form of a username and password. But the user of the program can also connect anonymously. So we have a thing called anonymous FTP. We don't see that as much anymore because it's just a security vulnerability. But back in the day, there was a lot of anonymous FTP, and you could just download those programs. Now, today, we often use secure transmissions to protect the username and password, and we might encrypt the content. So we might use SSL/TLS, so that's FTPS or FTP Secure, or you could replace this with Secure Shell File Transfer Protocol, and that's SFTP. So just to let you know, FTPS, which is SSL, okay, that's going to use port 443 as its data service port. If you use Secure Shell FTP, so that's SFTP, that's going to be port 22, okay, for the service port to send the data on. Now, when you're sending data over the network, there's really four kind of data representations that can be used in FTP. First, we have what's called ASCII mode. And I mentioned ASCII early on in this course when I was talking about, remember Matt Damon in The Martian and using ASCII to get information from NASA. So there's ASCII mode, and that's used for text. There's image mode, which is commonly called binary mode. So the sending machine sends each file byte by byte, okay? There's also, let me see, EBCDIC mode, okay? EBCDIC mode, okay? And that's used for plain text between hosts that are using this character set as opposed to the ASCII character set. And by the way, there's lots of different character sets out there. There's Unicode, there's ASCII, there's quite a few of them. Then there's a local mode. Local mode allows two computers that have the same setup to send data in a proprietary format without having to convert it to ASCII mode, okay? So those are four kind of behaviors of FTP. Now, data transfer can be done in any of three different modes. There's stream mode, okay? And that's where data is sent as a continuous stream. And that basically relieves FT from doing a lot of processing. There's also block mode, where FTP server breaks up the data into several blocks. Then there's a compressed mode, and that's used over slow links, right? Like a dial-up modem or an ISDN link, where the data is compressed using a simple algorithm. Realize that most common web browsers, i.e. Mozilla Firefox, Chrome, they can retrieve file that's hosted on FTP servers, although they may not support the protocol extensions like FTPS that I mentioned, okay? But a lot of web browsers will be able to grab content off FTP servers as well. A full-featured FTP client like FileZilla, however, can be run and do everything that FTP can do. So I highly recommend getting a standalone separate FTP client as opposed to using the web server. As a matter of fact, some web servers out there on the internet, they won't allow web clients to use FTP to get files, okay? They can actually control that on the web server. So something else I want to leave you with as far as FTP goes is two modes called active and passive mode. So let me just write those over here. And this is determined on the server side. Active or passive. And it used to be this was a big thing because firewalls used to have issues with this, but our new firewalls that are stateful and do packet inspection, they can handle either one of these modes. But in active mode, the client establishes the command channel, the command and control channel, but the server is responsible for establishing the data channel, okay? Now, as I said, this historically could be a problem if, for example, the client machine was behind a firewall and it didn't allow unauthorized session requests from external parties. Passive mode is where the client establishes both channels, okay? The command and control channel and the data channel, right? So we already know it establishes the command channel in active mode, and it does the same here. However, it then requests that the server, okay, on the command and control channel, which here is port 21, it asks the server to go ahead and start listening on a port of the server's discretion. So it can just pick some random port like, 3500 instead of trying to establish a connection back to the client on the standard port, okay? So those are a couple of things. You can find out more about this FTP behavior in RFC 959, okay? And so that is kind of our FTP behavior. Realize that we don't have to use FTP. If you just want to grab a configuration file or just some simple grabbing of a file, we can use what's called trivial FTP. And routers often do this. They need to go get a configuration file or some other file. They need to load it up into RAM memory on the router. They'll just use TFTP, and that uses UDP port 69. Also, I want to leave you with this. This FTP sharing of files, putting up files and getting files, this is not the same thing as what we call peer-to-peer file sharing, okay? That's a whole different animal, uses all different port numbers. Maybe you've heard of things like BitTorrent, okay, and things like that, right? So there's all these peer-to-peer file sharing. Kazaa is another one of those. There's a bunch of them out there. Peer-to-peer file sharing is a totally different thing. They often use really high up port numbers, way up there, in the tens of thousands. And in a P2P environment, every participant, every node in a peer-to-peer file sharing network is a server. So everything's a client and a server. So if you put a bunch of files on your system and it's part of a peer-to-peer network, it's serving files. People can come grab files off that device, and it's a client as well. So don't confuse file transfer protocol and its secure variants or trivial FTP with P2P, peer-to-peer file sharing.
In this demonstration, we're going to survey the very important DHCP, Dynamic Host Configuration Protocol. Every TCP/IP host needs a certain amount of configuration information once it comes onto the network. Maybe you're installing a new workstation at your business, or maybe someone's bringing in their laptop or their mobile device into the enterprise. It needs more than simply its IP address and subnet mask. For example, it might need to know where's the DNS server so I can do name resolution, or what's the IP address of my default gateway in case I want to get out of this local area network and get out onto the internet or connect to some branch office. DHCP is based on an earlier Internet Bootstrap Protocol, or BootP, from RFC 1542. BootP, for all practical purposes, is pretty much obsolete now. DHCP has two main parts:
Its primary purpose is to manage addresses and masks, and it stores those in what's called a scope, and then it leases them out to endpoints. The second part is to distribute configuration information, like the DNS server, the default gateway, the network time protocol server, and other attributes. The options field in the DHCP header is an 8-bit field, which means there's about 255 options that it can give out to the DHCP client. So for example, notice we have different codes here, and data length. The data length portion is in bytes, by the way. So for example, notice that code 1 is the subnet mask, and it has a data length of 4. So as you remember, the subnet mask is 4 bytes or 32 bits, just like the IP address. Code number 3 says here's your router, the layer 3 device that you use to get out of your local area network. Number 42 is NTP servers. That's important to synchronize your time. Number 6 is the domain name server DNS. 7 is your log or syslog server. That's important for logging and monitoring and reporting. Code 81 is the FQDN. Here's your fully qualified domain name. You could also use 15 for domain name. Code 19 says, I'm going to enable or disable IP forwarding. So the DHCP server could actually tell the DHCP client, you're going to be a router. Code 69 is the SMTP server. That's important. Or the Post Office Protocol server POP, number 70. Number 50 is the requested IP address. And number 51 is the IP address lease time. And the lease could be a matter of minutes, or the lease could be a matter of days. The DHCP client's going to discover one or more DHCP servers by sending out broadcast messages. Typically, it begins with a 0 IP source address. If it's been given a lease in the past, it will request the same address, however, as previously configured. So the DHCP client on the right is going to send out a broadcast DHCP discover message. The DHCP offer from the server, which can come either directly from a server or it can be relayed by a DHCP relay server or a router, is going to include the your IP address field, as well as other configuration settings as mentioned, like the DNS server address, the subnet mask, the SMTP server, etc. It'll get this information from the lease scope on the server, along with a lease time, T, a renewal time, T1, and the rebinding time, T2. Be careful, other servers, even rogue DHCP servers, could offer this as well, and this could be in a wired network or a wireless network. The client on the right-hand side will collect the replies in a broadcast to all the offering servers, but only the selected server identified in the DHCP request will commit to the IP address binding. The others are going to clear out that state information from their memory cache. Now, if the server can't allocate the binding to the client, it may send a DHCP NAC. In other words, it's a negative or it's not going to acknowledge it. And sometimes extra verification can be added. For example, Microsoft Active Directory can make sure that the client and the server are both authorized members of a domain. A switch could also use a feature called DHCP snooping, which builds a binding table in the switch memory to make sure that there's no rogue devices or that an attack is not occurring. The address of the DNS server, or option number 6, is a very important interaction between DHCP and DNS. Remember, without DNS, the system would be pretty much useless for finding hosts on the internet beyond its local area network. A lot of organizations actually combine their DNS and DHCP servers. For example, this is a Linux package known as DNS MASQ. Or they could use a feature called Dynamic DNS. Microsoft uses this, where it will automatically update the DNS database on a server based on information in the DHCP request packet. Here we see an ipconfig/all, and we can see that DHCP is enabled. It was given an IP version 4 address of 192.168.0.114 with a 24-bit mask. You can see when the lease was obtained and when the lease expires. You also see that it was given some options, such as the IP address of its default gateway, and the IP address of the DHCP server shows up here as well. SNMP stands for Simple Network Management Protocol. This is a very important protocol that's used almost exclusively in TCP/IP networks. SNMP offers a means to monitor and control network devices and to manage configurations, collect statistics, manage performance, and to some degree security as well. SNMP operates with UDP on port 161, and it's an application layer protocol that facilitates the exchange of management information between network devices. SNMP enables network administrators to manage network performance, to find and solve network problems, and plan for network growth, as well as remotely configured devices like routers and switches. Here's an example of the components of SNMP operations. Over here on the left-hand side, we have the manager, and this is basically going to be some type of command line tool that you run on your Linux machine or your Windows machine. It could be a graphical user interface management tool as well. And this SNMP manager basically is going to exchange different messages with different devices. Now, if a device is a managed device, and it could be a server, it could be a router, it could be a switch, it could be a load balancer, it could be a firewall, all different types of network devices. If it's an SNMP managed device, it'll be running an agent on there, which is really just a software package that's installed. And that agent has included in it what's called the MIB, which is a management information base, or a database that's set up in a tree structure. So in other words, if that's managed devices, let's say a Cisco router, the MIB is going to pretty much have all of the configuration information about that particular platform of router. And remember, there's lots of different brands of routers, there's lots of different versions and platforms within each vendor, whether it's Juniper or whether it's Cisco or 3Com or whoever. And so that management information base has a tree structure of all the configurable elements. We call them configuration items on that router. And what's important is that information can be retrieved. You can pull information from that agent on that device, or you could make changes. And the way that we do this historically is using kind of a password called a community string. And the community string can be a read-write type of string or a password, and if it is, this manager can make changes. If it's a read-write string, they can make changes on that managed device. If it's just a read-only string, all they can do is pull information. Okay, and we call that pulling of information or sending of information from the managed device to the manager. We call that a trap, okay, an SNMP trap. There's several versions. When I first got into networking way back, okay, my first job was with a telecommunications company, which is now defunct. They're no longer in business. But I was a network technician, and I transitioned from a studio engineer. And it was a pretty smooth transition, working in a studio, dealing with boards and plugging in to patch panels for compressors and all different types of effects units. That concept of networking was a really, a smooth transition for me. But when I went to work at my first job, we didn't even have switches, okay? We had bridges that would bridge between like an Ethernet network and a token ring network. And we had hubs, and they were called intelligent hubs. And they were intelligent hubs because they ran SNMP version 1 on them. And so SNMP version 1 used plain text community strings, okay? So in other words, there was no encryption there. If you wanted to have security, you had to have some other layer of security working with that. For example, maybe IPsec. You had read-only, you had read-write, and we used traps back then. Then we had SNMP version 2, and then they upgraded that to 2C, which became the most well-known and most popular version of SNMP. And probably still, at this point in time, it's the most widely deployed version out there. It included a bunch of improvements to the protocol. It still uses community strings, but it's the most common version, SNMP version 2C. A few years ago, SNMP was upgraded to version 3, and what they did was they enhanced the security with strong encryption and authentication, and we're going to talk more about that in a couple of lessons. I'm going to be looking at HTTPS, okay, which is SSL TLS, and I'm going to give you a quick little tutorial on cryptography. Okay, so that's coming up later on in this lesson. And SNMP version 3 also supported users and groups, policies and views, and it provided security mechanisms for confidentiality, integrity of that information being sent from the manager to the managed device, but also it provided origin authentication. So you could make sure that that trap was coming from the device it was supposed to come to, or the managed device really was qualified to manage that particular device. Here's an example of the SNMP MIB tree. So this information is obviously represented as a tree, but it's stored in kind of a database in the MIB on all of the managed devices, right? So if your switch or your router or your firewall supports SNMP, well, it's going to have this tree structure on it. And notice as you kind of move down to, let's say, the Cisco device, underneath Cisco, it's got its own CIs or configuration items. So if I wanted to go into the tree to configure something on a Cisco router, I would basically tell in that particular information I send to the managed device, I would say, hey, let's go up to root.1.3.6.1.4.1.9. whatever. Okay, so that's how you follow that tree down. I send that information over to the managed device, and let's say there's a bunch of information under Cisco or Juniper or Microsoft, or maybe it's a server operating system, and of course below that I'll just follow that tree down and either read that information and get it, or if I'm doing a read-write, I can change that information. That's why SNMP is so powerful, but it's also a dangerous protocol, because with the capability of changing the configuration on pretty much any device from pretty much any vendor, somebody who can compromise your SNMP 2C environment can do a lot of damage to your infrastructure. In this lesson, we're going to get an introduction to electronic mail systems, or email. Now, trust me, I could do an entire live lesson series on email, and there's live lesson series out there on Microsoft Exchange, and if you want to know more about a great email system, probably considered one of the best ever developed, that would be Microsoft Exchange. What we're looking at first here, though, is sending email. So let's say here I am, here's Michael, and I am the SMTP sender of an email. The recipient of my email is down here, and that's my buddy Peter, okay? So I'm going to send an email to Peter. Now, I'm using some type of SMTP user agent. Nowadays, that SMTP user agent is typically some type of graphical user interface, right? Back in the day, didn't have to be. It could be done, on a command line in a console in the early days of the internet. But nowadays, we're using something like Microsoft Outlook, okay, for example. And so I have my user agent, then I have the emails that I'm sending, emails I'm sending to Peter, and those are going to go to what's called a local MTA, which is a message transfer agent. One of the most popular MTAs on the planet, Microsoft Exchange, okay? Now the local MTA could then go to a relay MTA, and now the relay MTA could be on my site. It could be, let's say, in a DMZ zone at my company, my enterprise. It could be up at the service provider I could be sending it to. It could be a cloud provider. But the bottom line is, SMTP is TCP oriented. So remember, a three-way handshake is going to happen before me and Peter, the recipient. Specifically, the three-way handshake will happen with the MTAs. But we're using TCP port 25, okay? That's what Simple Message Transfer Protocol uses. And then, of course, over the internet, I may go through one or more multiple relays or relay MTAs, okay? Now, once I get to my destination, it's going to go eventually to that local MTA. And at Peter's, he may have, several levels of message transfer agents. It gets sent to Peter's user mailbox, okay? Now, here's the deal. Once that email message gets to Peter's mailbox, he's not going to use SMTP to go get the messages out of the user mailbox. Okay? Remember, SMTP is only used to send messages. Now, if he's going to respond to me, if he's going to reply to my email, then of course he'll use SMTP in the reverse direction. But we're going to talk about four main types of client or email clients that Peter could use to go as his agent to go retrieve those messages out of his mailbox. Okay? Now, SMTP was the original protocol. A few years back, they extended the functionality of SMTP. So nowadays, most likely than not, what you're actually using is called ESMTP or extended. Okay? So it added some extra commands to SMTP to just provide functionality. Also realize, and by the way, it still uses port 25. Also realize that with SMTP, you could also use, along with the extended commands, you may also get security of your email. And one way to do that is with a service called SMIME, okay? SMIME is a way to secure your mail, okay? And you might want to check that out. It's kind of beyond the scope of this TCP IP course, but we can use that. Or if we wanted to, we could have that SMTP information wrapped up inside of an IPsec VPN, okay, at layer 3. Or we could use, and this is very common, we could send the email and have it be over TLS, or Transport Layer Security 1.1 or 1.2. Also remember, and it's in the DNS lesson that we talked about, but there's a record. So we can use DNS along with our SMTP. There's a record in there called an MX record. And the MX record of DNS actually stands for Mail Exchanger. And so whatever user-friendly name we give that MX record, that is going to be the friendly name of our MTA, either our local MTA or a relay MTA. So that MX record, Mail Exchanger, points to this particular, and it's such an important marriage between DNS and email and SMTP. So that's the sending of email from me, the client, down here to Peter, the recipient. Let's look next at our three main protocols that we're going to use from the client side to retrieve or get our email from our mailbox. Okay, here's our four main protocols. We've already talked about SMTP, and we know that we're actually using ESMTP, and this is used by the message transfer agents, okay, and the relays to send email on the internet. Okay, it's only used to send email, not retrieve the email from the mailbox. ESMTP is often very tightly controlled by your perimeter routers and firewalls. Okay, so it's one of those things that's typically very well protected with firewall policies, with inspectors, and something we call DLP, okay, data loss prevention. This is very important nowadays in enterprises because they don't want you to send email out of your company that has, let's say, credit card numbers in it, or personal health information, or maybe, corporate keywords, intellectual property. So these often will work in concert with some type of email security appliance
or data loss prevention system to make sure that you're only sending stuff out of your company that's legal and that should be sent out according to your AUP, your acceptable use policy, okay? Now the other protocols, these are client-side protocols, and these are the ones that, Peter is going to use to go retrieve his email. One of the most popular and probably one of the original ones was Post Office Protocol. And you can see it's already been in a couple of versions, POP1, POP2, and POP3. We typically use Post Office Protocol version 3 now. And this actually allows you to kind of access that mailbox and then download messages, right? And you can say, I want to download all the messages from my mailbox, or I just want to download a few of them and leave the rest of them up on the POP server. So you connect to the POP3 server, you download, and then you disconnect, okay? And by the way, you can use security along with POP3 as well. In your enterprise, at your company and your business, most likely what you're using is IMAP, okay? And I think IMAP 4 is the most common version out there, IMAP 4, Internet Message Access Protocol. This is a client-server protocol that allows you to access messages in the mailbox from your local MTA. IMAP has a lot of features, so we call it feature-rich, okay? It's very flexible. It's used, for example, by Microsoft Outlook and lots of corporate solutions, and it works very well with like your antivirus and anti-spam solutions as well. Another cool thing about IMAP is that you can just go view the headers, okay, the email header information in your client, and you can pick and choose from the headers what you want to download. With POP3, you connect, you download all your messages, and that's why with POP3 it's more common that you get lots of spam, and you may even get a lot of stuff you don't want. With IMAP though, it's much more of a secure, feature-rich solution, and you can just simply look at the headers and go, I don't want that, I don't want that, I don't want that, I do want that. So it's much more flexible. Very popular corporate solution. What's becoming, I think, even more popular now is using HTTP for email. We call that webmail, right? So this is using, port 80, for HTTP, or if you're going to do it securely, SSL TLS 443. And that's using, something like Gmail from Google, or Yahoo Mail, or Hotmail from Microsoft. There's Yandex, which is very popular. Also, there's Outlook Mail on the web. I use one called Zoho, okay? Z-O-H-O. And so obviously this is going to use HTTP, right, to go up and retrieve the email from the mailbox, and HTTP to place email and send email over the World Wide Web. So there you go. There's our email main protocols. Like I said, if you want to dig deeper into email, electronic mail, and all the different security aspects of that, check out a live lessons on Microsoft Exchange. In this lesson, we're going to be looking at HTTP, the Hypertext Transfer Protocol. And this is one of those protocols that if you're going to continue along in your IT career or your technology career or getting into the Internet of Things or the Web of Things or maybe become a programmer, whatever you're going to do involving information technology, this is one of those protocols you want to run with. You want to get deeper into not only HTTP, but the secure version, HTTPS, that uses Transport Layer Security, or TLS. Well, that being said, HTTP is defined as an application level service. It's used for distributed, collaborative, and hypermedia information systems. And hypermedia really is the hypertext. When you see those hyperlinks on web pages and you click on those hyperlinks and those take you to other pages, that's what we're talking about here. It's the foundation protocol for data communication for the World Wide Web since around 1990, and it's defined in RFC 2616. HTTP is a generic and stateless protocol. It actually has to use TCP, and it can be used for other purposes as well, using extensions of its request methods, error codes, and headers. Now this tutorial
is based on the 2616 specification. It's referred to as HTTP 1.1, which is a revision of the original HTTP 1.0. There are newer versions of HTTP out there. Like I said, you're going to want to explore those as you go farther with your information technology. Hypertext Transfer Protocol is a TCP/IP-based communication protocol used to deliver data, such as HTML files, hypertext markup language, image files, the results of queries, and more, on the www World Wide Web. The default port of HTTP is TCP port 80, but other ports can be used as well, as long as the client and the server agree. The HTTP specification designates how client request data will be constructed and then sent to the server, and how servers respond to these requests. There are three basic features that make HTTP a simple but powerful protocol. HTTP is connectionless. The client, for example, the web browser, initiates an HTTP request, and after the request is made, the client disconnects from the server and then waits for a response. The server processes the request, then reestablishes the connection with the client to send back that response. It's also media independent. That means pretty much any type of data can be sent by HTTP as long as both the client and the server agree and know how to handle that data content. So, for example, both of them using the appropriate MIME type. HTTP is stateless. As mentioned, it's connectionless, and it's a direct result. The server and the client are aware of each other only during a current request. Afterwards, both of them pretty much forget each other, and due to this nature of the protocol, neither the client nor the browser will really retain information between different requests across web pages. Other mechanisms are used for that, for example, cookies. In a nutshell, the HTTP protocol is a request-response protocol based on the client-server-based architecture where things like web browsers, robots, search engines, and other web-enabled applications perform like HTTP clients, and the web server acts as the server. Notice on the left-hand side we have HTTP clients. The most popular is the web browser, like Mozilla Firefox, Internet Explorer, Safari, Google Chrome, and others, but it can also be other web-enabled applications. Notice that the client on the left sends a request to the server. This will be in the form of a request method, a URI, a Uniform Resource Indicator, a protocol version, followed by a MIME-like message that contains request modifiers, client information, and possible body content over TCP/IP connections. The server responds with a status line, including the message protocol's version and its success or error code, followed by a MIME-like message containing server information, entity meta information, and possible entity body content. So, for example, on the left-hand side, the user issues a URL from a browser. Let's say http://trainology.com/path/file. In step 2, the browser sends a request message. Notice it's using the GET method, and it's using HTTP 1.1. It also has the host IP address and the host port. In step 3, the server maps the Uniform Resource Locator URL www.trainology.com/path/file or program under the document directory. In step 4, the server returns a response message. In this example, it's HTTP over TCP/IP version 1.1 using code number 200. And then finally, the browser formats the response and displays it to the client or the end user. Notice in the middle where we have the browser request and the server response, there's going to be header fields used here, and they provide necessary information about the request or the response or about the object being sent in the message body. And there's basically 4 types of HTTP message headers. There's a general header, and these fields have general applicability for both the request and the response message. There's a request header, where basically the fields are applicable only for request messages. There's a response header, which has fields for response messages, and then there's the entity header. And these fields define what we call meta information or metadata about the entity body. Or if there's nothing in the body, it'll be about the resource identified by the request. For example, the path and the file. HTTP also uses several popular parameters. So for example, the version, which is typically going to be 1.1. There's also URIs, Uniform Resource Identifiers. This is basically simple, formatted, case-insensitive string information that contains the name and the location to identify a resource. For example, http://www.trainology.com/path/file. The path could be, let's say, mshannon. The file could be home.html. You also have date and time formats, and all of those date and time stamps must be represented in Greenwich Mean Time, or GMT, without exception. We have character sets like ASCII or ISO 8859-1 or ISO 8859-7. We have content encodings. For example, we're going to compress it. It'll be with gzip compression, basically indicating that an encoding algorithm has been used to encode the content before it gets sent over the internet. And then different media types. HTTP uses internet media types in the content type and accept header fields to provide open and extensible data typing and type negotiation. It could be different types of media, like a GIF file or a JPEG. It could be different languages used, for example. The HTTP message has a message header, then a blank line that separates the header from the body, and then an optional message body. And remember, the message body is optional. Over on the right-hand side, we see a basic, simple example of content in a message body with the HTML tag, followed by the body tag, and then the header 1 tag, which just simply says, Hello World. So if you went to this website and saw this web page, all you would see was the text hello, world, ! on the website. HTTP uses different request methods. The two most popular are the GET method and the HEAD method. Sometimes these are the only ones that are allowed by firewalls or other content security applications. GET is used to retrieve data from the server using a given URI, as mentioned earlier. Head is the same as GET, but it just transfers the status line and the header section only. Post is used to send data to the server, like customer information or something that you fill out in an HTML form. Put replaces all the current representations of the target resource with the uploaded content. Delete removes all the current representations of the target resource given by a URI. This one's often blocked. Connect establishes a tunnel to the server identified by a given URI. Options will describe the communication options for the target resource. And trace performs a message loopback test along with the path to the target resource. Here we see an example HTTP request. We're using the GET method. Notice the request line, there's the URI, and the HTTP version. We can also see request headers like accept language, accept encoding, user agent, and content length. Then there's a blank line that separates the header and the body, which is optional. A response has a status line, followed by response headers. That's the response message header, then a blank line, and then the optional response message body. Here's an example HTTP response.
Before we dive into HTTPS or HTTP Secure, I want to give you a quick little tutorial on cryptography. Now, realize that encryption is just one of the things that cryptography does. And encryption actually hides the original data or the message content by scrambling that clear text into what seems to be a random string of characters, and we call that ciphertext. Now, let me just say this real quick. If you decide that you want to go beyond this TCP/IP training and get into security, let me recommend to you one of my live lessons. and it's a live lessons for the Systems Security Certified Practitioner, SSCP, which is part of the ISC squared family. I highly recommend that live lessons for you as an introduction and to kind of get you up to the medium level of security. You can also go to Khan Academy, KHAN, and you can also get some training up there as well. But I do want to recommend my live lessons from Pearson, SSCP, so go check it out. Now, decryption is the reversal of that process, where you basically take the ciphertext and you use some key or some string of alphanumeric characters and you decrypt that information to get to the clear text. Examples of applications that need cryptography because they send traffic in the clear would be things like Telnet, which is a terminal emulation management protocol. FTP is clear text. Trivial FTP, which uses UDP as clear text. Email, using POP or SMTP, and the biggie, HTTP, by default is the clear text protocol. And that's why we're here talking about HTTPS. Many applications store and send information in clear text, and there's two ways to get encryption. You could do it at the link level, okay, so at layer 2, you could encrypt the frames. That's one way to do it, or you could actually encrypt the packet payload. And that's where things like SSL, TLS, and IPsec come in, or HTTPS. A symmetric key crypto system is where you use the same key to encrypt and decrypt. It's also called secret key or private key encryption. The sender and the receiver have to share the same secret key before they can have a secure communication. So protecting the key in a symmetric key crypto system is tantamount. We often use symmetric key to protect data in storage, also bulk messages, and we also use it with information sent over virtual private networks. Key management with symmetric keys can be a challenge. And by the way, the real weakness in most crypto systems is not what we call the cryptographic primitive or even the algorithm or the protocols that's being used. It's actually key management. It's protecting the keys and the keying material. Symmetric key crypto systems are fast and they work well for bulk encryption when you need data privacy, and their key sizes are between 40 and 256 bits. Okay, so let's say 256 is basically 2 to the 256 power, which is a pretty huge number. Some common algorithms, DES, which we don't really use anymore, but triple DES EDE, that's still trustworthy. RC4 is a symmetric crypto system, which we can't really use that anymore on the World Wide Web. AES is pretty much the US government standard that we should use, AES 128 and AES 256. For example, if you use Amazon Web Services and you encrypt data up there, or Google, they're going to use AES 256. And there's others, Seal, IDEA, Blowfish, Twofish. Sounds like a Dr. Seuss book, I know, and then there's Serpent. The next category is asymmetric key crypto systems, and these are primarily the ones that HTTP Secure or HTTPS uses, and these are going to generate a mathematically related pair of keys or a key pair. Think of them as fraternal twins, okay? So they've got a public key and a private key. Data encrypted with the private key needs the public key to decrypt and vice versa. Asymmetric encryption is also known as public key encryption, or you'll hear it referred to as PKI, public key infrastructure. RSA, which is very common on the internet when you use HTTPS. There's also DSA, El-Gamal, there's Diffie-Hellman, there's elliptic curve Diffie-Hellman, and elliptic curve DSA. These are all asymmetric key crypto systems. Here's an example of getting confidentiality with an asymmetric key crypto system. Let's say Alice wants to send something and she wants to keep it confidential, okay? And she's going to send this to Bob, right?
what she's going to do is she's going to go get Bob's public key. And so early on in the TCP exchange, Bob will give that public key to Alice. She'll take Bob's public key, she will encrypt that information with Bob's public key, send it over the network, and then Bob will decrypt it with his private key. And on the internet, one of the most common methods we use is the RSA crypto system to do that. Another one that's gaining popularity, especially with mobile devices, is what's called elliptic curve DSA, okay? Elliptic curve DSA. So you might be seeing that used more often as well. Now, what if Alice wants to send Bob some information and she wants Bob to have a high degree of confidence that she's the one that sent it? So she wants to use asymmetric key crypto systems to authenticate the origin, okay? Well, what she's going to do is she's going to use her private key, her RSA private key. She will encrypt it. Bob will have obtained her public key before this started, or maybe he already has it from a previous communication, and so she sends the information over to Bob. It's encrypted with her private key, and he can use Alice's public key to decrypt it, okay? And so here's how we use these public and private keys for a couple of different services. Another cryptographic mechanism that's actually not encryption and decryption is hashing. And hashing is used for data integrity, and basically it's kind of like a checksum but on steroids, okay? So a hashing is a one-way mathematical function that's nearly impossible to reverse. So think about a big jar of marbles that you drop on the floor, and think about how difficult it would be to get those marbles back into the jar in their original form. Or think about some coffee beans that you send through a grinder, okay, to get some coffee. That's a one-way function. So to get integrity, we take data of an arbitrary length, let's say an email message, and we send it through this one-way hash function. And what the result is called a fingerprint or a hash, and it's going to be fixed length. So it's going to be the same length every time, regardless of how big or long the original data is. Then we take that fingerprint and we attach it or append it to the message, and that's how we get data integrity. Now, you might hear the term HMAC, okay, because we use HMACs for a lot of security services. All an HMAC is this: to get better integrity, okay, we take the data and then we interleave a shared secret key, one that both parties have. So that secret key gets interleaved with the data, it goes through the hash function, and then we take the fixed length hash and we attach it or append it to the message. So we're not going in and we're not taking this data and encrypting it. We could with something else, but this is just an integrity mechanism that's used in a lot of security services. Now let's talk about HTTPS or SSL/TLS, which, by the way, can use all three of those mechanisms I mentioned. It can use symmetric keys for its session keys. It can use asymmetric crypto systems for its, its integrity and its confidentiality and other mechanisms, and it can also use hashes as well. Now, SSL was created by Netscape way back in the 80s to add security to one of the first popular browsers, the Netscape Navigator. And with HTTPS, otherwise known as SSL/TLS, a cryptographic key exchange happens when you first connect to a website. Then all the subsequent activities are encrypted. Although anyone can see that you visited a website, they can't see the web pages or read any of the data that's transferred to or from that website, at least theoretically. If you see a padlock on your browser, then you know the website is secure. If you see a green padlock, then that means that particular domain, let's say www.pearson.com, if you go up and let's say you purchase something, then that means they've got an extended validation certificate. So they've jumped through extra hoops. They've gone through extra steps to get their domain name validated. Now these are intended to verify that the SSL certificate presented is correct for the actual domain name, because the entity has gone through additional verification processes. Here's an example of going up to Pearson's Inform IT, and here's my AWS Cloud Security Live Lessons. If you're interested in security in the cloud, I highly recommend it. But notice that this up here is just using www.informant.com. There's no padlock at all. But if you were to go and click on this little button and say, hey, I want to add this to my cart, you would go to another page, and that, of course, is going to be using SSL TLS. And specifically, to be honest with you, it's using TLS, Transport Layer Security, which is the new version, 1.1 or 1.2. Now notice that you have a padlock up there, and not just any padlock, but a green padlock, which means that this particular informant.com, they went through extra security for extended validation to make sure that you can feel confident that you're actually at informant.com's HTTPS website. So HTTPS web pages are secured typically on the internet, especially with the commercial sites like Amazon and PayPal and all the biggies. They're using Transport Layer Security 1.1 or 1.2 encryption, and they're using really strong cipher algorithms. So if you notice back here down below, you have a message, and it says, this connection's encrypted, and it's using TLS, which is Transport Layer Security. That's good. It's using ECDHE, elliptic curve Diffie-Hellman ephemeral, which means the session keys, ephemeral means the session keys aren't stored anywhere, okay? They're just ephemeral, and they vaporize as soon as this session's over. They're using RSA. They're using, for their symmetric crypto system, to create data keys, session keys. They're using AES 128 GCM. GCM stands for Galois Counter Mode, which is extremely strong, using Galois fields. And then you've got SHA-256. That's the HMAC I talked about, where you have the hash plus the secret key, okay? So the secret key is created using AES 128 GCM, and that secret key is combined with the SHA-256 algorithm to create the cryptographic hash. And notice that we've got TLS 1.2. So that's an extremely strong security suite, and it's one that you probably want to use if you ever have an option up on the internet when you use HTTPS. So HTTPS uses certificates. They use X509 version 3 PKI certificates. You have a bunch of these loaded into your web browser, okay, or your operating system with a bunch of different certificate authorities like GoDaddy and VeriSign and Intrust and Thought and Microsoft and many others. And this is an asymmetric crypto system where a web server presents a public key, which is then decrypted using the browser's private key. And an HTTPS certificate is issued by a recognized security or certificate authority, a CA, which again, GoDaddy, Intrust, VeriSign, Thought, THAWTE, which certifies the ownership of a public key by the named subject in the SSL TLS certificate. Okay, in this final lesson, I want to get you started with the Wireshark tool, which is an invaluable tool, a packet sniffer that you can use to evaluate and analyze a whole lot of different types of traffic. And it's really a great next step for you as you complete this TCP/IP series to kind of get your fingers a little bit dirty with the stuff that's happening under the hood. So you can see obviously they have a thing called SharkFest, okay? We're going to go up here to wireshark.org and click on this download. Now it depends upon what system you have. I have a 64-bit system, and I'm going to go ahead and get the installer for Windows, but obviously you've got other versions and older releases you can use, but I'm going to go ahead and get the newest 64-bit version, and I'm going to download this. It's going to go to my downloads, okay, so If I look up here in the upper right hand corner, I can see the status of that download. Now I'm going to go to that folder, the downloads folder on this system, and I'm going to double click on that executable. Okay, I've got the Welcome to Wireshark 2.6.4 64-bit setup. You can also see in the background I've downloaded a couple of files, a DHCP.pcap file and a DNS.cap file. These are capture files. And I got these from the wiki, the Wireshark wiki. I'm going to show you that here in just a moment. But I went ahead and downloaded these. I'm going to click on Next. And it tells you basically you've got a 3-part thing to this license agreement. I'm going to go ahead and agree. And I'm going to download Wireshark, which is the main protocol analyzer. T-Shark is a text-based network protocol analyzer. There's plugins and extensions and a user's guide. And so I'm going to go ahead and download all of that. You can obviously expand this out and see, some of the plugins and extensions we're getting and some of the extra tools that we're getting. Okay, edit cap, merge cap, raw shark, other things that are there. And if I want to get secure shell dump or UDP dump or Android dump, I can also check those off and get those as well. I'm going to click on Next. I don't want a quick launch icon. Okay, I've got enough of those going on, but I do want to have a Wireshark start menu item for sure. And you can see the associated file extensions that come along with Wireshark. You can see here's the cap file, so that's going to be good. There's also a PCAP, PKT, okay, and others. This is where I want to install it, program files /Wireshark. It's also going to ask me if I don't have WinPCAP to go ahead and install that. So I don't have a currently installed npcap or WinPCAP, so we'll go ahead and install this extra program here as well. You really have to have that. Now I could also do USB cap if I want to use stuff that's on a USB to capture traffic from my universal serial bus. It's experimental. It's also kind of cool if you're, an amateur hacker or whatever, but I'm going to go ahead, since it's experimental, I'm not going to install that. This will take a while, so I'll catch you up on the backside. Okay, so I'm running the Wireshark Network Analyzer, and notice at the bottom where it says Learn, you want to go ahead and start digging into the user's guide. There's also some quick questions and answers. I'm going to go take a look at the wiki here in a second. That's a wealth of information. But notice that right now I'm actually using my local area connection. So this is the local area connection on my workstation I'm using, connecting to my broadband router, to my service provider, and they use IP version 6. So if you are using the local area connection on your laptop and you're, let's say, in your office, or you've installed Wireshark to the system at work, be careful, okay? I don't want to recommend that you run this at work, okay? It could get you in trouble. It'll look like probably some type of reconnaissance attack is going on. You're probably going to get an email or a phone call from somebody in the security area. So let's don't do that. If you do it at home, like if I were to do this right now, choose this connection and click on Start Capturing Packets, I would immediately start capturing packets. I might want to open up a browser or maybe an FTP client. I might want to go and do a telnet session or maybe use PuTTY, something like that, to do a secure shell session. I could see a bunch of stuff. And by the way, I would see probably at least a dozen different protocols and services on my network. Some IP version 4, a lot of IP version 6, okay? ICMP v6, IPv6, I would see TLS version 1.2 and 1.3, okay? And again, a lot of HTTP activity. Now, I'm not going to do that. I don't want to expose my local area network information out to the public. So if you don't mind, let's go take a look at the wiki. So I'll click on that. And so here is the front page of the Wireshark wiki, and it gives some general information, how to, prepare Wireshark to, start installing it and building it. I'm kind of showing you that right now. How to successfully capture on the Ethernet, how to capture on a wireless LAN. So this is a great tool for both. However, I wanted to show you some sample captures, and I actually have it opened here on the side. Let me go ahead and close that. Click on Sample Captures. Sample captures for your edification. And if you'll notice, they've got some sample captures that are just kind of randomly thrown in here. But notice we've got some that show different viruses and worms. Okay, from a security standpoint, you can see some traces that were done of some cracks that were done of cryptographic algorithms and protocols. We also can see specific families, like you can look at ARP and reverse ARP here. You can start learning about the way layer 2 switches prevent loops by learning about spanning tree protocol. You can look at Bluetooth. I mentioned UDP Lite to you earlier on, so you could take a look at that. For you people that are working on a Microsoft environment, you might want to learn about SMB and the Common Internet File System, CIFS. TCP, just a bunch of TCP, obviously that'd be a good place to look. There's HTTP, Telnet, Trivial FTP, which is a more streamed down version. You can also look at some routing protocols that we learned about. BGP, EIGRP, OSPF, and RIP version 1. So we also learned about the Simple Network Management Protocol, SNMP, talked about Network Time Protocol, so you get the idea. This is really a good place to come to. You can also see some peer-to-peer protocols that you might want to learn about, like BitTorrent, for example, and the list goes on and on. Here's PPP, our good friend. We learned about that quite a bit. Here's PPP over Ethernet. Talked about that as well. So you can build on a lot of the information you learned in this series by using this tool and looking at sample captures. So a really great utility resource for learning and building on your TCP/IP knowledge. Now, if I close this up, one thing I can do is I can go and open up one of those CAP files or PCAP files, right? So let me go ahead and open up this DHCP, and I can see here a simple, DORA process. Okay, here's the DORA, the DHCP discover, offer, request, and acknowledgement, something that everybody should know about. And if we notice that the source, the host that's looking for a DHCP server, will often use the any or the all zeros as the source because they may not know their IP address, right? So they're going to, and probably they don't. Often with DHCP, if they already have gotten a lease before from DHCP, they'll often try to use that same IP address that they got in the previous lease, okay? That's one of the ways the DHCP works. But this is like a brand new device on a network, so it's sending out a broadcast to discover a DHCP server. And when you select one of these lines up here, I got 4 numbered lines, you'll then start to see kind of the TCP IP stack here that's going on. And you see the raw information down below. But notice that we've got a bootstrap protocol, and that's what this is the old bootp protocol. Okay, but we still see it referred to as the bootstrap protocol because that's what's happening. This system is picking itself up by its own bootstraps and getting some information, right? So we can see that we're looking for other information here. Here's some of those options that we mentioned. Okay, here's option 53, option 61. Option 50, requested IP address. So and this is what I said earlier, if it had already gotten a previous IP address in a lease, it would probably have that IP address in here. Notice that we can go down into the stack here, see the UDP. Notice that, DHCP uses UDP port 67 and UDP port 68. Okay, and that's pretty standard. Obviously, this is going to be using the IP protocol. Protocol UDP is number 17. We even can get down into the frame. Obviously, the destination is a broadcast MAC address, and the source is the MAC address of this host, this client. Ultimately, there'll be an acknowledgement. And if we click on this line number 4, we start to see now, we know the source and destination MAC address. Okay, we can also see protocol information, IP version 4 that's coming in. And we can see some other information coming down into the options field. So notice that when we finally do get the DHCP acknowledgement from the server, I mentioned these values. T is the IP address lease time, right? And we can see that it's 1 hour. So that's a pretty short lease, but you can see a short lease in certain situations. So there's T1. T2, I mentioned that to you, the rebinding time. So we can also see here's the subnet mask option 1, and I mentioned that to you as well. Now, this is not a very robust DHCP server. If it were in an enterprise environment with a Microsoft DHCP server that also is a DNS server, you would most likely see the DNS server in here. You would most likely see the default gateway, the router, NTP servers, and a bunch of other information as well. Okay, this is just a pretty simple DORA process: discover, offer, request, and acknowledgement. So one thing you're going to want to do is obviously you can scan your own home network if you want to do that, or you can obviously go and download a bunch of those different capture files and PCAP files from the wiki and really start taking the information that you've learned in this live lessons and really start running with it and building on this foundational knowledge to really see the different kinds of behaviors of all these different protocols and services. All right.
Well, congratulations on completing the TCP/IP Fundamentals Live Lessons video course from Pearson. In this course, you gained a ton of knowledge about foundational concepts and core services of the TCP/IP protocol suite. This should start you on your path to further your information technology career. If this is your first time through the course, I really want to recommend that you go through it again. At least the areas that you feel are not your strengths from an experience standpoint, or maybe some of those areas that weren't clear that you want to reinforce. Now, this should also serve as a great reference tool going forward as you pursue other IT technologies. Hopefully, you enjoyed watching this training as much as I enjoyed producing it. So on behalf of the entire Pearson Live Lessons team, I want to wish you success with your technology journey, your IT career, and life in general. Take care.